again, welcome everyone to the OSI² Build workshop. Happy to welcome you here at the PTB in Berlin. Some of you have been here already the last 2 days because we already had some exciting discussions around the system, but more to that in a second. Why are we all here, or why do we want to have this type of workshop? So I guess you're all somehow involved or interested in this OSI² low filter MR scanner, which you can see here on the slide. So it's a cheap or relatively cheap system for around 20,000 euro material cost. It's a portable system, magnetic field strength around 50 millitesla. And the idea is to do head and extremity imaging with that. And I think the most exciting part about it is that it's an open source project. So we are trying to generate open source hardware and open source software components through the entire system as much as possible. So this is a collaborative effort. There are currently of this OSI² scanner, there are currently 3 versions of this first prototype, one in Leiden University Medical Center, which is the original version, then one here in Berlin and one actually in Uganda. And there's more information under the links. There's a lot of information still missing under these links. We are giving our best to slowly fill this up. But just a few words. So why do we want to do that? We believe that if we do it in an open source way, this has a lot of impact. It has impact in terms of reproducible science. It has impact in terms of affordable devices. It has impact, educational impact. And we are exploring a little bit this field. We are basically exploring how much we can push it towards a medical device. Because in the end, the diagnostic information of MRI is very valuable, and in the end, many people around the globe cannot access this technology. So such a collaborative effort might be a way to overcome some of the current hurdles and to really focus on the core of the technology and the core of the medical imaging capabilities. Okay, having said that, this workshop here in particular is organized as part of the Open Lab MedTech project. What are we doing there? So basically, we started an open source laboratory at a hospital, and where the idea is to develop and rebuild open source devices within the medical context. Can be as simple as a 3D print for for example, to help some surgical applications, different things. And a part of that is also the construction of an OSI² system, construction and optimization. So of such an MRI scanner that we want to place there. There will be also knowledge transfer over workshops, so such as this workshop here, or some open lab days. And again, we are exploring a bit the concept of open source medical technology, trying to involve early clinical staff in this process. And of course, a lot of networking that's through this lab in the hospital, which is not a full-scale fab lab, so to speak, but it's more a hub. So you know where to go. You can ask what's available, and through this larger community outside of this lab, you might find solutions to some of your problems. If you're, for example, a medical doctor with some idea, and maybe there is already somewhere a solution towards that. So this is the Open Lab MedTech, and this is big efforts and mainly led by the organizer of today's meeting, or the main organizer of today's meeting, which is Häuer. So thanks a lot, Martin. for doing a lot of work in the backgrounds to make this happen today. So maybe just a quick... Yeah, so it's fantastic that Martin is here and fantastic that we can sit down together. So this is one project that we have. Then I also want to mention another project that just started actually last 2 days, where we had the kickoff meeting, which is also around this open source MRI system. So even even if we are a little bit behind, let's say, spreading the news, what we are doing, but there's a lot of stuff happening at the moment in the background. So in this project, we will build some more scanners. Of course, everything open source, but I think the nice thing about it is it will be also fully characterized. There will be some optimizations performed. There will be comparison to other low field systems in terms of imaging performance. And I think one thing that is very interesting and very impactful is that we will start providing some technical documentation for certification. And this will also be published in the public domain. So a very important blueprint that is missing at the moment. And people are very exciting actually about this. It's ambitious, but again, it's a great team. There are 19 partners, and so we are very optimistic that we can provide some impactful results during and after this project. Having said that, so if you think of if you're interested in building such a system or to join these efforts, don't do this alone. Just dock onto this existing wave that we have here, and I think that's you will benefit, we will benefit, and everyone else will also benefit. Okay, so that's the short intro. Thanks for that, and. Welcome to the workshop. How do we start it? Maybe I will just show briefly the agenda. Do you have it somewhere open, Martin? Oh, here, wait. There it is. Okay, so that's our plan for today. We will, in a second, we will do the introduction of participants. And then how we imagined it at this stage that we will basically have all the modules of the system, or as much as possible. We try to have enough time for discussions. So if you have questions, ask questions, and there are no stupid questions. It's a relaxed event, okay? So it's really about if you have questions on how to rebuild, how to use, what are the challenges, whatever, ask them. And then we can also have some discussions, and actually we will try also to fix some technical specifications for the next iteration of the system that we are doing, which will be something that's hopefully a little bit better documented than the current one that we have online. Okay, fantastic. So with having said that, I would start the introduction of everyone that's here at the moment. And maybe we just start with you, Martin.
And let me go that way. Yeah. Yeah, hi, that's Martin. I think we've been in contact with almost all of you. I'm working in the background with the GitLab structure and communication a little bit. Licensing, the basic open source infrastructure stuff.
If you want to speak, I think you just need to press this. Yeah. Awesome.
Yeah. Yeah. Hello, I'm Danny. I've designed the gradient amplifier and the RF amplifier that's in this scanner. And yeah, very.
Hello, I'm Jan, and I'm working part-time here at PTB for mainly open source hardware as a developer.
Hello, I'm Markus Prier. I'm from the Research Campus Simulate of the Otto von Guiridi University in Magdeburg, and I developed the Okra tabletop MRI system. Okra is the open source console for real-time acquisition that we also want to use here, mostly the Okra One board. I developed the hardware and the software for that.
Yeah, good morning, everyone. My name is David. At PTB, I'm more doing image reconstruction and most recently built a console based on Spectrum cards. And with BrainLink, we developed an acquisition platform, which I'm going to present later on today.
Good morning, everyone. I'm Sebastian Littin from the University Medical Center Freiburg. We do a lot of work on gradient coils and gradient coil design, and you'll be hearing a bit about gradient coil design later on. We are also involved in the AIM project that Lukas was talking about on the software side, and with that, I'm handing over to Ben.
Hello, Ben Wilhelm, also from University Medical Center Freiburg. I'm a computer scientist and will be working on software integration.
Okay. Good morning. My name is Laila. I'm studying medicine in the charity, and I heard about this project, and I just want to listen and ask if there's a free place with me.
It's good to you. Hi, I am Berk Slemek. I work at PTB, and I mostly doing console development at the moment with Spectrum cards.
Hey, I'm Axel, a member of Maker Community and a member of Health Hackers in Erlangen. As a volunteer in different rescue teams, I'm very interested in the different field tests and the introduction to the people that want to use that machine. So I'm quite passionate about it.
Yeah, hi, my name is Patrick. I'm also from PTB. To be honest, I'm not really involved in the low field project, but I do a lot of things about the open source Pulse programming using PyPulseq, or more specifically the Python version of it. And this is why I'm here.
Hello to everyone, my name is Tomáš Rizal, and I'm from Czech Tech University in Prague, and we are interested in this project, so we come along to learn more about it.
Hello, I'm David Vrba. I'm from the same department as Tomáš next to me, and I would like to only mention that we are super excited by this project.
Hi, I'm Tom Reilly from Leiden University Medical Center. We built the first OSI² system. We actually have two. Just showing off a little bit.
Hello, my name is Wouter Teeuwisse. I'm a colleague of Tom's, designing the hardware mostly. And I'd like to take the opportunity. I have a scale print of a bit of the hardware, so feel free just to grab it and have a look later on.
Hello, everybody. My name is Martin Maxener. I'm a computer scientist visiting from the Free University Berlin, from the Dahlem Center for Machine Learning and Robotics, where I'm involved in, as an engineer in open source hardware projects and several. So I'm interested in this one as a different project that uses similar techniques.
Awesome. You came right on time for introduction. Just come in. Yeah. Great. Maybe we can. So some more people are joining, but maybe in the online participants can say one or two words and why you're interested in this project.
It's a bit hard to hear at the moment, so
maybe just sorry, just a second. Let them maybe sit down because it's from acoustics will be better. Okay, so online.
Hi, good morning all. This is Jewel James. I'm a master's student in SRH University in Berlin, and I'm super excited to attend this event because I'm considering to develop a business model for a low-field MRI. And I'm here to understand this project from a technical perspective.
Thank you, Joey.
Thank you.
And then there's Stefan.
Hi, can you hear me?
Yes.
Oh, excellent. I'm Stefan de Plessis. I'm from University of Stellenbosch. I'm currently working on building a small low-field steam, a low-field MRI system designed by Tom, Andrew, and team.
Awesome. Thank you, Stefan. Then we maybe start with Baki. Can you just do a short intro? And there are some new people here that don't know you.
Thank you. Baki Karaböce from National Meteorology Institute of Turkey. I'm meteorologist I work in meteorology for 20 years to 30 years almost. So I am the head of medical meteorology laboratory at UME. We make mainly calibration. We try to establish the traceability to medical measurements and calibrations. And this will be our MR project. Will be our first study, first project. Thank you.
And then we just go around. So Ahmed, can you, just a few words.
Hello, I am Dr. Ahmet Baş from Istanbul University. I'm a radiologist, and I just started to learn about low-field MRI systems. Thank you.
Hello, I am Hüseyin Sözer from TÜBİTAK UME Magnetism Laboratory. We are involved in work package 1 in this project. Thank you.
Hi, I'm Alessandro Arduino from INRIM, the Italian Meteorological Institute.
Hi, I am a colleague of Alessandro. I come from INRIM, and that's the first time we try to work on low-field MRI, and we will be involved in the AIM project in WP1, radio frequency coil design, magnet characterizations, and other things related to this.
Hello, everyone. My name is Vittorio Basso. I come from INRIM Torino, and my field of research is magnetic materials and measurements.
Good morning, everybody. My name is Oriano Bottouscio from INRIM, Italy, Torino. I'm working particularly on electromagnetic field modeling.
Awesome. And then there's, I see Frank. Frank can also say a word or two.
Okay, I'm Frank Seifert. I'm heading the MR technology group here at PTB, where all the stuff is centered a little bit.
And Niels.
Hi, my name is Niels. I'm from Dortmund, the Fachhochschule, and we are replicating MR reference system.
Awesome. I think then we are through with the introduction round. So thanks a lot. I would try to get the power over the camera and put it into the room. Good. So now we can maybe start directly with the first presentation, yeah? Martin, are you ready?
Yeah.
Excited?
Exchange.
Yeah, we changed seats, yeah.
So yeah, good morning. First mention of the day. This is the speaker seat. So if you have a talk, you will sit here in this seat at one point. I'm sorry for the microphone situation because the other microphones do not work online, and that's why we need to use these. You already figured out how to use them. That's good. For the slides. Again, markdown slides. Here we go. So online can see the same. No. No, they should.
Yeah.
Perfect. Thank you. So yeah, good morning. I'm going to talk a little bit about contribution management, how we imagine this for OSI. But first, free Wi-Fi. There is an access point. It's the same password from yesterday, but it's not working. So feel free to copy it and try it out. We're working on the solution. There seems to be something odd with the central system. So yeah, let's see. If you need internet connection or anything, just come to me and I give you a hotspot. So contribution management. We want to work with a single source of truth. Also a point where everybody refers to, and that is our GitLab repository or the GitLab group for OSI. So you have seen that. There are all different modules here and gathered in reasonable groups with sub-repositories. Yeah, and there should be also a landing page down here, but it's not loading. Yeah. So that's where we will work, where all the modules will be, or at least referenced from there, so anybody can find them from there. We can also open some private repositories in case we don't want to go public yet with some of these. So if you have a relevant repository, please send it to me so that I can, link it there. So licensing. In short terms, if there's no license in the repository, there's no rights for the users. So we need the licenses. And in order to keep the licenses compatible between our repositories, there's a list of recommended licenses. These are the licenses for the AIM project, the European project that Lukas briefly mentioned. We can as well use them for OSI because they have been inspired by OSI. But of course, we can discuss a few. For instance, in software, if it makes sense to use a copyleft license instead of permissive ones. But this can be figured out with me. So if you have any issues or concerns about licenses, please just send me a mail. And then the actual collaborative development plan. We use Git. I think most people in the room are familiar with Git. For the ones that don't, it's a tool for decentralized version control, and it allows us consistent versioning, even if we do retrospective bug fixes. It does so because it also allows parallel development without interfering with ongoing processes. It's fully open source and it works on all platforms. And other people using it too, like the Open Flexure microscope, that is a 3D printable microscope from the University of Bath, where also the wrapper-up printer comes from. So that's their repository for the stage of the microscope, sort of like the main frame. And you find the CD files, the license, README, and so on. And what's special about Git is that it keeps the whole history. So you can go back to any point of time. You see always who has done what, and then you can see the difference between the two versions in the past. You can as well see here, have it visualize the different parallel developments ongoing. So if there is, for instance, here it was, they changed the resolution of an image, and then you can compare the two and see how large they are now. And if, and go back. Here. And for OSI, I suppose that we have one repository per project, so everything that should be versioned independently should be in an own repository. And per repository, there is at least one maintainer, so a person of contact that also maintains the repository and makes sure that everything is consistent in there. We can have more developers, but at least one maintainer. and use the licenses which are recommended to make sure that the repositories are legally compatible to each other. I've also written a guide for the branch management. So that is based on the case that we want to do MDR documentation for a certain module. So it explains how the versioning works, and basically says that that the MDR, so the clinically certified variant, is based on a technical version. So it always comes out of here, and then it is the technical version plus MDR documentation. And so also is the assembly. And this is all managed using branches in GitLab. We can dive into detail here if you want to, but my personal preference would be to talk this through with the maintainers of each repository, because these are the ones that then manage the branches. Yeah, and goes up to this. It is an approach to keep it as simple as possible, even though it may look a little fancy. But the other projects are doing it a lot messier. So I hope this one will do the job for us. And again, this is just a suggestion. If you want to manage your repository in another way, please do so. The only thing that we need in the end is consistent versions.
Excuse me, a question about it. What is the reason for this choice? And it seems still quite complicated, and especially the forking for the MDR version. Why is it necessary?
Okay, cool. I haven't dived into it yet, but happy to do so. The basic idea is, or maybe I start with the versions. So you might have figured that the version has 3 digits: major version, minor, and patch. Major is that external interfaces break. So if you have a console and it has an interface and then you can connect it to another device, if you change this interface, then you change the major version. So meaning that everything of the major version should be compatible. If you add features and don't change anything of the external interface, you change the minor version. So new feature, new minor version. If you just do smaller fixes, bug fixes, for instance, then the patch goes on. And for hardware, we have the scenario that hardware stays out there in the market for a longer time. So even like 10 years after, we may want to do bug fixes. And that represents in the branch management. The main branch is the branch between major versions. So whenever you have a cool new idea for a new interface, you can put it in the main branch, and then it will be there until we will start a new major version. However, we usually may want to work in the branch of the current major version, release candidate 1. So from here, all the release candidates under major version 1 escalate. And this is one for release 1.0. So we work on that, then we think, okay, we've reached a stage where we are happy with the design freeze, then just maybe some last fixes in the documentation and so, and then it goes into the release branch. Why we have a separate release branch is that we have a consistent chain of versions, because we might not have this here. And if you do later on a bug fix, it looks the same. Development goes on here, and then 5 years later, we find, oh, this needs to be fixed, do that, and push it there too. I try to keep it simple in the graph. If you do that in a real scenario, it looks a lot messier, but I just wanted to visualize the structure. And for MDR, it's similar. MDR escalates or is based on a release. So we choose this one should be MDR certified, then we fork it. Because when we fork it, we work in an own repository. We have our own issues there. We can take different permission managements there. Other people can work with it, and we're very free there. If during the MDR stuff we figure that the design should change a little bit, there's a bug to fix. The design changes all happen again here, because it's always based on this technical documentation. So bug fix happens here, new release, and gets merged into the fork again. And once we are done, whenever that will be, this will then get into an MDR release branch.
Maybe just a comment on that, because we just come from a 2-day meeting discussing a lot of other things as well, and there is a bit of redundancy here. But for this workshop, so it looks a bit abstract. Learning by doing, basically, what we will do. Yeah. So I think the MDR certification stuff for the standards rebuilds, this is not that important. And there will be a structure set up with what Martin said, with maintainers, etc. And then I think we will just start to get used to a certain workflow, and it's hopefully then obvious also from the GitLab repositories how this workflow is to others that want to join. Yeah, I also have a hard time to follow the graphs, so I think we will manage. Just Martin made a lot of thoughts on that, so there's a plan, there's a master plan, which is good, and I think for others that will join, then it should be much simpler in the end.
And there will be scripts, so you don't need to remember all of this, and don't be afraid to make mistakes, because the scripts will do that for you, especially merging everything back to main and the others. Does this answer your question?
Yes, partly. Follow up, what is the difference between RC1 and RC 1.0?
This one is then only 4 patches later. Because here the development goes on, so 1.1 or 1.2 might be published already, and then much later on you do a bug fix for previous version. But the main working branch will be this one between features.
And then why is the forking necessary for the MDR version?
It's not necessary, but I would recommend it. So the fork references one specific design, and having it in a new repository keeps our issue management cleaner. As said, it's all a suggestion. If you want to do it in the same repository, please go for it. Yeah.
Just trying to learn what your thoughts are. Thank you.
I mean, you can also like open Flexure. Where is that? Here. No, it's not here. It's somewhere there. Open Flexure does it all with feature branches. So in the main repository, they're working with 32 different active branches. If you can merge that and handle that, feel free. At the end of the day, we just need consistent versions. Cool. More questions?
Not necessarily a question, but a slight concern, because you have information flowing back from the release branches back into main branch. And I would just like to point out, coming from a software engineer background, that has high chances of giving you nightmares.
This merging back from...
Yep.
Yeah.
Information flow, one-way information flow is no problem, but two-way information flow can give you nightmares, especially with lots of people interacting.
I mean, you mean from the release candidates? Because from the release branches, there's no flow back.
From RC/1 back to main branch, and from RC 1.0 back to RC1.
I see. Okay. Yeah, I would like to discuss this through, because this came originally from the software board and then was adapted for hardware. In the end, we need the information again in main, because this is what we have through different versions. And yeah, so if we want to develop a new major version, then we also need all the bug fixes and stuff inside there. But if it's something specific, so if this is not relevant for main, then we also don't need to merge it back. But yeah, well, happy to have a coffee about that.
Sure.
Cool. Yeah. Issue management. Also essential. I'm very happy to replace email threads with that. So we have these, it's a sort of a ticketing system. And you can, that's new. SD card extender for the Red Pitaya. Yeah, so you technically just post what you want to change or issues or that you encounter or features that you want to have in the system in a specific project, make a description, and then people can work on that and also further comment. And it's documented. People can refer their changes to it. It just works a lot better. You can assign it to people. The point of issues is you can also, if you feel like this is not the right place for this issue, you can change it and push it to different repositories. The point is, especially in engineering, we're very used to discuss these things in email threads, and that is an issue because they're intransparent. Nobody else than the people in the email thread is reading them, and they are potentially lost forever because you get a lot of emails and try to find this in a year again, and they're not tracked. So you may have discussed something, but there's no real follow-up, and there's no tracking until it's actually implemented. So please, if you want something to be open and transparent, involve people and have it documented. That is a reason why I use issues also in private projects and have it implemented. At the end of the day, please use issues and not emails. Yeah, in general terms, if you ever run into issues using this infrastructure, Git, open source licenses, Markdown, which is used for the documents itself, please feel free to reach out and I will do my best to help you. And then something that came up during these days that I want to pitch again is a community communication channel. And I recommend Matrix for that. That's up to discussion. Yeah, but we are already starting to form small signal groups and more mailing lists and these things. But like that, the community runs the risk to scatter a lot more. So there is a Slack channel for OSI, and yeah, I think we're not extremely happy with that. So I proposed Matrix, and that's something that we should also decide as a community where we want to communicate, and then it's also a lot easier to reach us and to organize this development. Yeah, that from my side. Any questions from here?
Yeah, thanks, Martin. Maybe can you maybe just make one or two comments on the licenses, just that it's clear why we recommend these. So it's not that we want to say do this, do that. It's more that the work you do is compatible to the work we do.
Yeah. So all of these are open source licenses, of course. And they try to be domain specific. So for hardware, we use the CERN open hardware license that has been developed specifically for hardware. A lot of hardware projects use software licenses or the Creative Commons, which also works as a general license. And this just includes a lot more legal perspectives that you might have with hardware. So it technically also works as a patent license, although nobody's using it as such. For software, the same target-specific or domain-specific licenses. What we use here in the AIM project, mainly permissive licenses. That means that they can include it in anything else. So regardless of what license any other project have, you can always incorporate them. With the hardware license, it's a little bit different. There it says you can incorporate it in anything, even in proprietary projects. However, if you make changes to the hardware itself, then you need to publish it open source again. And this is a construct that should work for us for all the different repositories.
Yeah, so we have the advantage that, I mean, for hardware, this is something we started from scratch in a way, and in software, there are a lot of software tools that use already permissive licenses. So it wouldn't make sense to now go in parallel with some copyleft licenses and leave the other communities. That's why I think this distinction. But for hardware, we can try to have as much as possible open over a longer term. So that's what the CERN OHL, and there are not many open hardware licenses, and I think this is probably the best or the only one that's very well usable. Yeah. And the other comment, so to the Matrix channel, so we will switch to Matrix. So far we were in Slack, and there were some mixed. The experiences were mixed, so we try it again with Matrix, and maybe now we can get a little bit get this going a little bit more. So even though Martin doesn't like emails, so far we could handle it very well with emails, but we also realized that the group is getting bigger and bigger, and then we do have some issues with this this type of communication. So we will try and give it a go for Matrix. Yeah.
All right, more questions? Maybe I got one. So for the hardware open source stuff, when I design an electronic circuit board, something like this, what do we need for publication? Is it only the manufacturing files, or does it also include the complete project with the source code?
The source. We actually need both, because on the one side you need everything that one would need to develop the project further. So of course also the source code, but especially in hardware you might have file formats that are attached to proprietary software like CATIA also, and so that people can at least access the information and do something with it. Then also the export formats. So both, yeah.
So just to share a personal experience, very relevant to you. So you put you open sourced your OSI² boards, but the CAD files themselves, the project files from Eagle are not in that packet. The 5-volt voltage regulator can't be bought at the moment, and there's no drop-in replacement for it. Okay. So there it would be nice to be able to have those project files and make those changes and then put that back into the community, okay, without having to bother you about 5-volt regulator is not available.
Yeah, in general terms, it makes sense to have the source code only in the GitLab repository, and then the export files in the release. So this is then a frozen version of the development, and people can just download the stuff from the release, because otherwise you will need to keep the export files also updated all the time, and Git is also not very good at handling export files. Yeah.
Yes, one thing to note about Matrix, if you are concerned about privacy and these kinds of things, I do recommend checking out Synapse issue 1941. And to evaluate if this is the technology for you. It may be, it may not be. But
happy to have a coffee, Bonal. Yeah. I will need a lot of coffee today.
Yeah, just about the coffee. Anytime this is like, if you want, just stand up. Again, relax. Yeah, so it's not a one-sided event, and you don't need to wait for the coffee break.
There's also very good shoes. Just, yeah. Yeah, you're the next one.
Yeah, is there any question to this part? Okay, if not, then I would suggest we continue with the program, and we start with the next point, which is actually about the hardware and about constructing the magnet, which is me then. Aber jetzt hast du Freigabe beenden. Ja, weil ich im Browser war, du musst es ja eben mit einem... Ach so. Ja. Ja. Yes, can you send him...
the box link, yeah.
Yeah.
Mm-hmm.
And then I need to start the recording again, or how is it?
know that the recording is on.
Oh, the recording is continuous.
Yep.
Okay.
It's shared?
Mm.
Oh, I can check it.
It is not.
Yeah. And then here. Oh, cool. Yeah.
Okay, good. Then I will. Yeah. This one here, right? Yeah. Okay, so let's start. We will start with the magnet construction. Again, for some of you, there will be a little bit redundancy, but I tried to put some more slides on actually the work items. So how do we build the magnet for this this system, and then also some ideas or progress towards an next iteration and the reasoning why. Just to mention the magnets that we have here, it's based on permanent magnets, and you have a certain arrangement of small cubic magnets. If you put these magnets in a certain orientation very close to each other, what happens is that on one side you have constructive interference, on the other side destructive. So on one side you have a field, and on the other side you have very little field. And if you take this and put it into a cylinder or sphere, then you get a relatively homogeneous field inside. Since you cannot do that very well in this configuration here, and in reality you have to discretize things, you lose a little bit of this homogeneity as well. And also, if you want to have a larger volume, not only a slice that's homogeneous, you need to have not one ring, but you need to have multiple of these rings, and then you increase your area of homogeneous field. And this homogeneous field we need for imaging. And having this basic, so this is this Halbach arrangement in this form. And then if you do it in a more clever and optimized way, as has been done by Tom O'Reilly in Leiden, then you end up with such a magnet design, which consists of 4,000 small cubic magnets of 12 millimeter by 12 by 12. And then you have these different rings, and you optimize the ring diameter and arrangements of these magnets. And this gives you, in the end, a magnet that has an inner bore diameter of 13 centimeters, has a B0 field of around 46 millitesla, and a pretty good homogeneity below 1000 ppm over a 20 centimeter sphere. Length is around 500 millimeters. And taking these individual magnet pieces, then you can create a cut file, and this is the one that you can download at the moment, and start fabricating it to then position this magnets. Then from the cut file, you can of course construct these magnets, and you can use the slightly different techniques and materials. So here are two examples. So this is the first. Tom is not here at the moment, but Wouter is the first one, yeah, or of this version, the first one of this size, yes. So there a plexiglass or PMMA was used with laser cutting. And then you have magnets which are neodymium iron bore magnets. You can use different grades, so then your eventual B0 will change slightly, but not dramatically. And then on the right side, for example, there's a slightly different material that was used, and this is a version that was CNC'd, so not laser cut, but CNC'd. Then what else do you need? So you put the magnets, you need some glue. Again, depends on the material, so acryfix or some epoxy. And then you have some shim inserts. This is the white thing here outside, where basically you will homogenize the fields after construction. And these trays are 3D printed. And then again, you can have different materials, PLA, ABS. And then what else do you need? You need some threaded rods, some screws, some nuts. And you have such a magnet. The weight of this is around probably around 100 kilograms. So it's for an MRI magnet, it's not too large. But you can see already the wheels here, so you can push it around. It's relatively convenient. So how is this process? You start populating the magnets, and then you have this gluing process, which you need to prepare the lids a little bit. You might need some, or it's handy to have some additional 3D printed tools to distribute the glue evenly. So in this particular case, it's epoxy, or if you have another glue, then you maybe need some UV lights for curing that it's a little bit faster. Then what makes sense is quality control. I will come to that later. But your magnet might not be perfect, so it's good to just double check if you get the field that you want. Then you have an assembly step, which you can see here. So you put one ring over the other, and they are positioned here with this nuts on this threaded rods. And then you basically put all the rings together, and you double check the distance, that it's at the distance that you want to have it. And once you're done, you measure the field of the magnet. For further processing and for further homogenization with P0 shimming, but this will be the next presentation by Tom. So what machines do you need? So of course, either you let it fabricate somewhere. So I didn't write it actually here, but of course you need initially you need either a laser cutter or a CNC machine. The version that is uploaded is the CNC version. Then for the field mapping, you will need some Hall sensor or other magnetic field probe, and ideally some mapping system. What we used and what's pretty useful is this also this open source positioning system COSI measure, which you can find more information under this link. Okay, so maybe just a short summary of this. Building time 1 week, but depends also how many people you have available. It's always good to not do it alone. It's relatively safe. Here just very, very funny setup that we had for the measuring. So there was no space, so we just put it at the tab. Of course, that's don't do that. But apart from that, it's relatively safe. Of course, these are magnets, so you can squeeze your fingers a bit, and this might lead to having some bruises. But it's apart from that, it's relatively safe. And also other parts from the process, of course, you need to be aware not to sniff too much glue, or if you use certain materials, better use some mask. But these are the standard things you anyway have to do in a workshop. But apart from that, it's relatively safe to make these magnets. Then it's relatively well reproducible. So the ones that have been built, they all have an initially roughly same homogeneity, even though they were used with different production methods, also different magnet suppliers, etc. Next thing is watch out for dead magnets, and this also comes to the magnet supplier. So the magnets can be from different batches. We had the experience also of having magnets that were not magnetized properly, but randomly distributed. So this is definitely a source of error. But apart from that, the other normal variations, they can be pretty well compensated later on. So yeah.
I just want to add a point that you mentioned it briefly, but it's very important that when you're ordering magnets, order them all from the same batch. You have some variation within a batch, but you can really have big jumps in magnetization between batches. So get them all from one batch, and then it's not a problem. If you start mixing batches, they can vary as much as 5 to 10% average, and that would potentially be quite a big problem.
Yeah, no, thanks a lot, Tom. I think for the build that we did, we also had magnets from different batches. But yeah, it's a roll of dice. Yeah, so to be sure, and the magnets are not cheap. Try to get them from one batch. Yeah. Then also watch out for production quality of the rings. It's and there can be several issues. So it's if you do it yourself, then of course after if you start the production and milling of the rings for this project, you first start with one, right? You do the machine settings, and then you have a relatively good tolerance how your magnets are fitting in, and then you're happy, and you leave the machine as is, and then you start your production. If you don't change your tooltip on time, you will lose this, and then you will figure out that each ring gets tighter and tighter until you are not able to fit it anymore. So this also happened to us, and this is also when you have sometimes when you order it outside. So just keep that in mind. And then in this process, from our experience, so with this design, there was a bit too much gluing and a bit too much screwing. So this is basically the part which takes the most. So the gluing and this adjustments of all these nuts. So you have 12 threaded rods at the outside, 12 at the inside, and each ring has basically 2 nuts per threaded rod. So it's a lot of nuts, and it drives you nuts. So if you do this, there's a little bit hidden here, but there's a Dremel, very useful. You should get that. Saves you a lot of time. But for the next design, what we plan is basically to get rid of this gluing and adjusting the nuts part. So the modifications that are intended is to have a shorter compact magnet, first of all, which gives you a little bit, let's say, a better position of if there's a head in the magnet over the whole field of view. Then some other little things that is nice to have if you can also put the gradients outside or has a little bit more space outside. Then what I mentioned is easier construction of both magnets and gradients. I will come to that in a second. Recyclable magnets ideally, and then washable materials or disinfectable materials. So what's to shorten the magnets, Tom did some simulations. So this is here this original design with the 4,000 magnets. And then if you optimize further for each magnet rotation, you can improve homogeneity to some extent. So you make it shorter, but you don't have actually losses in homogeneity. So you can see this on the right-hand side here. So there is a more standard rotation of these magnets. And here you can see there's something a little bit more wild going on here, but it's intended. And then, so if you again take this magnet positions and then create a cut file, you in the end up with something like that. So this is this version 1 that I was just talking about, and this is this next version 2. And it's a little bit shorter, so 60 millimeters shorter. And then there are some other things that we will try So no threaded rods. We have screwed lids. And some other things that are convenient to just have a single lid design for rings, for example. Okay, so for the next one, how it looks like from the side. So you have here this, instead of the threaded rods, you have some bars, 6 and 4 millimeters. There's this thread then at the end, so it will pull this or fix the rings on this one side. And then between the rings, you will only have then distance holders. And then you have this larger magnets in this foot here on the front and on the back. And in the front, you basically nearly end with the magnet, so that's that you don't have that it's as short as possible to be able to position the heads then in the ISO center. We started with the construction of that to see if this is feasible, and here you can see our CNC setup here.
Your pointer is not on the screen. If you want to share it, use.
Ah, okay. But the online participants will not see that anyway, no? Yes. Good point. Thanks. Okay, a little bit late. Sorry for that. You didn't see all my mouse movement. But I hope you got the point. If not, then just ask. Okay, so here's our CNC setup, then some first rings. Then here you can see such a ring with a lid that's actually screwed on. So you can, if you make mistakes, you can still remove the magnets, which are not cheap, and correct it. And then some first setup. So we don't have all the rings yet, but seems to work. Files for that will be uploaded, as soon as we are able to. Good, and then just because the magnets is not only the magnet, but it's also a part of grading coils. And in the first version, this was very nicely designed with this segmented grading coils. But it was also not easy to construct and to connect. And so what we thought might make sense is if we basically have one former or one cylinder that we input, and just no additional soldering connections, and then just a clear cabling outside. And so some first simulations with this open source tool to optimize for grading coils, which is CoilGen. And then you can make a cut file out of it. So this tool exports directly STL files, which you can then post-process in your cut software. And then, so this is, for example, there are 2 gradients in there. And if you add a third one, then you effectively end with a bore size of 290 millimeters. So it's a few millimeters smaller than the version 1 system, but it should be hopefully suitable to do everything that the first version is able to do, plus the simplifications in the construction. Good. So I think this was my last slide. Yes, this was my last slide. So about the magnet construction, and if you have any questions to that or any suggestions, then please raise your voice.
I have a question. I once helped with assembling a magnet. It was with a 1-inch cube magnet, and it was a bit more challenging and dangerous. So for that, we use a tool, a 3D printed tool, where you can rotate your magnet in position and prevent it from sticking to the next magnet with your fingers in between, maybe. So have you ever used in the beginning maybe tools like that and later stopped using that?
1 inch, can you remind me how much that is in centimeters? Just 2.5, yeah. So we had another project, we had around 2 centimeter magnets, and there is a difference to the 12 millimeter ones here. So I think for the 12 millimeter, you don't need an extra tool. You can squeeze your fingers a bit sometimes, and it also hurts if it's 100 times during the build. But there's no tool necessary for the 2 centimeter magnets. Depending on which magnets, so some of them are really difficult to position, and then you also need extra tools. And also for finger squeezing, I think we had also some gloves. So 2.5 then is even more powerful. So yeah, so what I referred to with the safety part was to the small magnets. If you go higher, it gets more complicated.
Also for your eyes, you should probably take care because they can shatter. But the point you make is actually good, because we now, on the new build, we will have 50 millimeter long magnets, and the force will be 4 times higher than on the 12 millimeter magnet. So that's something to also take into consideration.
Yeah, that's a good point. Maybe, yeah, we have to test maybe if we need some tool that it makes it a little bit safer. Also, we have this, but yeah, no, we will need to check that, because we also have these very thick rings. So maybe, and they are a little bit easier to hold, no? So we will see. We will see how that is actually.
If you have all the second version stuff, how long it will take to produce the stuff then, in comparison to 1 week that you announced?
One week. I mean, it's just a rough number, because I mean, this one then will be maybe 1 week, but less people. So I think for the first one, the depends on how you do it. I mean, for example, the epoxy needs to dry. Takes a while, so you cannot take the very fast drying epoxy. Unless you're very optimized with your production process, but you need and then you need to make sure that you have enough space, and then maybe you need to measure the fields. Someone needs to put the magnet. So if you do that alone, then I think it's maybe even more than 1 week. And then some tasks really require maybe a second person to help out. No? So, but for the new one, if it's really if you can push the magnets in, screw the lids on, push the rings on the bars, it should be relatively fast. Yeah.
It's also a bit of a question of the word. I struggled with it yesterday. I still can't say it today, but you guys know what I mean. Because there's other little tasks that Lukas didn't mention, but that do take a lot of time. And one of them is even simple things like coloring in the magnets, because the orientations need to be correct. But that's when you're working with 4 people, one person can be coloring in magnets, one can be filling in the magnets in the ring, and one, so it's also, it's not just because it's easiest to stack the magnet that you will save time, because it might mean that the para is less optimal. Parallelization.
I have a question concerning the dimensions. So also at the kickoff event, we saw that there is still a lot of, like for head imaging, for instance, unused space in the magnet. And you already mentioned that you decreased the size a little bit in the length. Were there considerations to further decrease it, but like half the length of the magnet, or would the field then be not good enough to? So would it be possible in general? Did you consider that, or? Yeah.
So the magnet, this magnet is 50 centimeters long. From our experience, that's probably 8 centimeters too long. We're 4 centimeters off center, so effectively. But if I try to keep the same field performance and make the magnet 8 centimeters shorter, so you can get 4 centimeters closer to the middle, that doesn't work. The field, you can't get the same field performance. So we're playing it a little bit safe, also because the project that we're on is funded for 3 years. So we don't really have that much time to
do it wrong. So the aim of the shorter version as it's designed at the moment, so 6 centimeters shorter, is that's the most that we can do while keeping the same field performance. And what we'll probably end up doing in Leiden is, because we don't have to build one of the systems, is we will look to see how short can we get while still able to get full brain coverage.
I got 2 questions. The gluing first, you reference in the new system, the lids don't get glued anymore, so they're screwable. So question is, what actually needs to be glued, and can you really maybe totally get rid of the gluing process, or what really needs it? And the second is, you mentioned just for checking out the magnets, you need a field map device or CNC style or XY style gantry for that. Is it also possible to just hover with the probe manually and see, okay, the field goes in the right direction?
Yeah, so first question with the gluing, I don't see at the moment where we would need glue, which I think is good. And then second question, with the hovering, you probably could do that as well. So I think what's probably the best strategy is, normally you get the magnets anyway delivered in like a grid, like a stack, and then if you have programmed your field mapping device to a pass, you just can quickly see if there is any. Yeah, and then you don't need to do it after you populate the rings. No, so you just do it before actually. But measuring each magnet, we did that just to see how much they vary before, and if you really want to do that more or less precisely, it's a lot of work.
But maybe one comment on that. So I also joined that one building session in Leiden with Lukas. One reason we also did it, I guess, was to check if the magnets are really in the right direction. And if you have a very clean circle that you do inside this ring, we could see sometimes that there was like one magnet or so which was oriented the wrong way. And I think if you just do it by hand, you probably have such fluctuations that you would not see if there is one wrong oriented magnet. So I think there's another benefit of doing it with a CNC machine.
Yeah, that's a good point actually. So yeah, humans do errors, and if it's a lot of magnets, it's also possible that you orient them wrongly. Or what we also had, that you maybe have the that you have the magnet orientation wrongly written on the magnet. No? So that can also happen. No? So it's this quality check in between is quite useful. Yeah. Yes.
But it's the same machine that you need ultimately for mapping the field for shimming.
Yes. So. And it's open source, not too complicated. Yeah, that's true.
Another question. Is there any developing for another way? In accelerator magnets, you usually measure the field of each magnet, and then you place the magnets in a way that the inhomogeneities are more or less cancelled out. So is there already development going on in that we measure each ring of the magnet and then we place them in a certain order to get the best homogeneity?
Yeah, I don't think I'm not sure if it was done in a build. I don't remember, but there was a paper definitely on simulations doing that, where they also showed that it's actually better if they are not homogeneous, but inhomogeneous, and then if you can distribute them, which of course could be a strategy, but you have 4,000 magnets, which you would need to characterize first very well, to then be able to do your shuffling. And then you have still some other tolerances in the build process that go into that are maybe your uncertainty. And probably the better strategy is you just have a couple of shim iterations afterwards, as it's at the moment. So you basically take cheap magnets, have certain uncertainties, but then you measure the fields, and then you try to correct for that, and it seems to be good enough. And probably, of course, if you want to reach certain homogeneities, maybe you need to do a bit more of weightlifting. But I think at the moment this works pretty well, right? Tom, what's your?
Yeah. It depends. So there's different approaches. So NMR people will sort their magnets out, but they typically, two reasons. It's a smaller system that they can build to tighter tolerances, they because they have a smaller number of magnets, it's less of an arduous process. The question with us is sort of multiple. Each ring is unique, so you can't just move the rings around. So it would have to really be on a magnet basis, which obviously would take a lot of time. But the other question is what is actually the major contributor to field inhomogeneity? Is it the magnets or is it the construction process? Because if it's the construction process, then there's no point measuring the magnets before you put them in. And my feeling at the moment is that the major contributor is the construction process rather than the magnets, because there's so many of the magnets that the idea of using so many has always been that it kind of cancels out or averages out imperfections.
Can you try just using a mic? Thanks.
So, in the first version, rings seems not identical, but second version is the same diameter. Are they identical, or why the difference in between two versions?
So it's a difference in the design approach. Fundamentally, what you have to do with magnets that are this short, because that's the problem, is that you have to compensate for the magnetic field wanting to drop off towards the edge of the magnet, right? So as you move towards the side, that the field will decrease, as you would have for a finite length solenoid, for instance. So on this design, the way the optimization was done is you have smaller rings on the outside, and smaller rings are associated with a higher magnetic field strength, and then you have bigger rings on the inside. The new design approach does things differently. It also drops the magnetic field, but it drops the magnetic field not in the middle. So that's effectively what we're doing with the bigger rings, is we're decreasing the magnetic field. With the new design approach, instead of making the ring bigger, what we're doing is we're effectively rotating the ring away. And what you end up with is a sort of a field in the middle that depends on the cosine of the angle that ring makes. And that's also an effective way of decreasing the magnetic field. And the benefit there is also that your ring no longer has to be bigger, because a bigger ring will have more magnets in it. So that was one of the original motivations behind using this design approach, is that you can actually not have this variable ring diameter, and it saves you a lot of magnets. So I think the slide that Lukas showed, I think it was exactly the same. Well, it was a better field performance. It was the same length magnet, and we had 20% fewer magnets in there. And that comes from not having this variable ring diameter. So each ring does look identical, but the rotation is different for each ring. So it's not, you can't swap them.
Orientation of the magnets in each ring is different then?
Yeah, it's symmetric. So around the middle, like basically this ring and this ring will have the same distribution, but this ring and this ring will not have the same distribution.
maybe I got another question for the shimming. You do this with magnets also, right? And not with like iron plates?
Maybe Tom,
to your hats.
maybe Tom can do the presentation on shimming first. You want to swap if there's... Oh, yeah.
Ask you, you said that you uploaded the CNC version. What is the difference in the file between the CNC and laser cutting version on a CAD file? Is it the same file? Or?
The file is different, slightly different.
So what is different there?
I mean, on the laser cut file, you have the ring and you just laser through it, right?
Okay.
And then you have two lids on both sides.
Okay. Yeah.
And on the CNC version, you have a pocket for the magnet.
Okay. So you don't go through it in the CNC.
You don't go through it, and you have just one lid on one side. But of course, the overall construction changes a little bit because of this, because then you need to shift it a little bit.
Yeah.
Yeah.
So I think we're ready to go. I'll talk about not necessarily focus too much on the algorithm, but the main building process. If you have questions on the algorithm, yeah, so I won't focus too much on the algorithm. I will talk briefly about some of the parameters that you can adjust. At the moment, the code is intended to be open source, but it's a bit of a mess. I hope to clean it up in the next few weeks and push it online, along with some example data from the various systems that we've worked on. So in the previous presentation, Lukas showed some of the various magnet design efforts and construction efforts that we've undertaken. This isn't sort of a side view of the magnet that we've built at the moment. And on the right, we have simulated field distributions with both the field strength of 46.3 millitesla and a certain inhomogeneity over 25 centimeter diameter spherical volume, which is usually how we define it, sort of a spherical region in which we describe the magnetic field in terms of ppm, which is ppm. When we talk about homogeneity in terms of a ppm, it's the maximum value in that field, in that region, minus the minimum in that region divided by the average. So we design a magnet with a certain target inhomogeneity, and then for a variety of reasons, we never reach that. So the individual magnets that we use to build the magnet array will always have a slight variance in the magnetic field strength, as was mentioned in the discussion before. This gives a certain additional inhomogeneity. It's not too bad. It's an extra 3,000 ppm if you have a 2% pure random variation of the magnetic field strength. You can also have that the magnets themselves are not magnetized in exactly in the correct direction. This is quite a lot more significant field perturbation, but it's on the order of 9,000 ppm, which for people doing high field is horrifying, but actually on low field it's not too bad. And this is with a random distribution of 2 degrees, which is again in line with what we would expect from uncharacterized, somewhat cheap magnets. What's much more significant comes from the manufacturing process. So if you have a 12 millimeter magnet and you CNC your hole at 12 millimeters, you're going to struggle very much to get the magnet in the hole due to friction, and you also have a slight variation on the magnets themselves. So it might be that your magnet's 12.05 millimeters, and then it's definitely not going to go in. It's a relatively binary thing. Either it goes in or it doesn't go in. So you always have to make the holes a little bit bigger than the magnets themselves. You want to do this as little as possible. Because when you put the magnet inside of a hole that is slightly too big, and you put the neighbor of the magnet in, you're going to see that the magnet is able to rotate within that hole. And because we use a hole back configuration, our magnets follow a very strict rule on
their orientation, and also that means that the torque that the magnets exert on their neighbors varies with a very well-defined distribution, namely this 2-phi distribution. And if you look at what would happen if you have a 12 millimeter magnet in a hole that is 12.1 millimeters, you're going to get an error because that magnet can rotate from the ideal position of that magnet rotation. And because it's periodic, that error is a huge contributor to B0 inhomogeneity. And the B0 inhomogeneity that it produces follows a very, very specific distribution. So if we go back to the previous slide, we see that with a 2%, 2-degree error, we get a significant inhomogeneity of 9,000 ppm, but the distribution looks fairly random. If we then look at what we would get if we have this periodic error in the magnets, it's a smaller error in terms of degree, but the inhomogeneity is three times as big, and we get this very specific pattern. So we do actually correct for this in the CNCing process. So we actually, depending on the position inside of the ring, we actually counter rotate the magnet holes a little bit so that we should get the desired angle. And this does work well. We actually did it the wrong way around, so we actually made the problem worse on one of our systems, and which is again the need for shimming it becomes very clear. But these little things sort of have to be accounted for, and is also why characterizing every single magnet is not necessarily the best use of time, because these kind of errors are quite a lot more significant. The other thing that Lukas mentioned was dud magnets, and this goes a little bit to the question of Marcus. Can you do this by hand? So these measurements are on a circle of just, I think, a 30-centimeter circle with a field probe, and then we measured over that circle, and you see this is for a good ring. You see a very sinusoidal field distribution. And if we look at where we are with a dud magnet, so a dud magnet just means a magnet that's not properly magnetized, we see a small dip in the field distribution, and it's actually mainly on the non-dominant component of the magnetic field that this is obvious. So this is a very subtle effect, and I think if you did try to do those measurements by hand, it would be almost impossible, if not impossible, to spot those, because I think you have more variation from the shaking in your hand than you do from the effect of that magnet. But actually, if you look at what this would do to your magnetic field distribution, this would be a significant error. So this is something to look out for in the process, also because it's quite it's a very strong local effect, which is difficult to shim. Yeah. If you, and that's probably a better way of doing it, or having some automated way of doing those measurements. Yeah, because.
Sorry, question.
Yeah.
On the magnitude and the Y line in the green and blue, why is there in all of them like a dip at the maximum?
It's a good question. I don't know. It's yeah. I sort of. With finite length holeback arrays, you do get elliptical iso contour lines. So lines where the field distribution should be the same. We're measuring over a sphere, so this might just be the way in which you're cutting the ellipse. But that's could easily be a wrong answer.
And still, an addition, like measuring the individual magnets beforehand, you will pick out the dud magnets, but you won't signal magnets that were inserted in the wrong way.
Yeah, which is it's also a good point, and that's also always double check or triple check. Have somebody else double check, because after 4,000 magnets, those last few, you're much more likely to make a mistake than on the first few rings. So if everything goes well, this is sort of continuing at this point on from Lukas's presentation. We go on to the shimming process. So in order to shim, so with shimming, we basically mean you have mechanical shimming for people who do mechanical work, which is basically trying to make things level. And that's what we also try to do. With shimming, we try to remove the imperfections in the magnetic field to try and homogenize the field. But in order to do that, you need to know what the field distribution looks like. This is something that you can only do after construction. So you need to map the magnetic field. There's a pointer. Okay, you need to map the magnetic field. So Lukas and his team wasn't. I did not expect there to be audio. So this was developed the cozy measure with Lukas and his team back when you were not here, or was it here? A long time ago. Don't talk about how long ago it was. It still works, and it's proven to be very useful over the time. But you don't have to use the system. I would argue that the system's probably overkill. We've been looking, or the group that we work with in Uganda has looked into adapting 3D printers to also do this these kind of measurements. Sure. I don't know which is closer to. Is Magdeburg closer to Berlin or to Leiden? It's could have. Yeah. Okay. And then you attach a Hall effect sensor to the cozy measure system, and you map the field in that way. We've personally tested two different ones. The Alpha Lab probe they call it the high precision probe. It's not as high precision as the Lakeshore, but it's about 1/10 of the price. So both of those do work. We then fit spherical harmonics to the field distribution. I don't remember if I put a slide on spherical harmonics in here, but it's basically a way of Maxwell makes a prediction of if you don't have any field sources within a region, you can actually very accurately describe the magnetic field in that region using some solutions to Maxwell's equation called spherical harmonics. And that's a very exact match, and it's a very efficient way to help reduce noise in the maps. And on the next slide, I'll also show that. And this actually allows you to get away with a slightly less sensitive probe because the spherical harmonics will help you sort of interpolate the data points between what the probe can offer. What's very important is that your temperature, that you're in a temperature stable environment. Very important. Especially as the homogeneity of the system improves, the dominant term can actually start coming in from the environmental temperature drift, affecting the magnetic field strength. So the magnets will change, I think it's 1,000 ppm per degree temperature change, 1,200 ppm.
Sorry, I did one question.
I'm sorry.
Oh, sorry. Ah, damn it. Please go ahead. You will this first.
What is the temperature? Some 23 degrees or some 20 degrees?
In our lab, Wouter, what's the temperature in our lab? Yeah, it doesn't matter as long as it's been stable for 24 hours. It doesn't matter too much, but it does take 24 hours, if not more, for the magnet to stabilize completely. The other way, which I don't do at the moment, but a way of handling this would be to basically have one reference point that you just sample every 10 minutes or something like that. So that every 10 minutes you would go back to the middle of the magnet and measure it, and then you can see how that evolves over time, and then you could correct all of your data in that way. We don't do that at the moment, but the last data set that we got was so bad that actually I think we should start doing that.
How long does the measurement take?
Depends on your resolution, to give you an annoying answer. It's about 1 second per data point, 1.5 seconds per data point. So we, with the latest measurements, we didn't measure over in the entire sphere. Again, because we can use the spherical harmonics, you only technically have to measure over a spherical shell on the outside of that region, and that hugely improves your scan time. But then for personal comfort, I always do like doing the full sphere measurement just in case. But it's technically silly because the spherical harmonics work so well that it's completely unnecessary. And often I do the data fit on a shell anyway. So I think, yeah, it's just me being. Off the top of my head, I don't know. We do a 5mm map on a 25cm sphere. And that would take, I think, on the order of 16 hours if you do the whole sphere, and it's about an hour if you do the shell, I think, or maybe a couple of hours. Yeah.
Which order of spherical harmonics are you using for fitting? And did you ever run into numerical issues? Because for really high orders, what you're basically doing is you're getting like really, really high terms and counteract them with others. And it's like a really big positive number, really big negative number for actually describing something quite small. And the numerical issues for higher orders are at some point really a big problem.
Yeah, so typically we go up to 15th order, maybe 20th order, but at some point you're just fitting noise. Not had issues with exploding solutions for extremely high orders because we never interpolate outside of the volume. For some of the image correction that we do, that is an issue where you don't necessarily have all of the data points. So there I would typically stay to, I think, 5th or 6th order. But for the shimming, because we're just trying to get the data to be noise-free or as noise-free as we can, then it doesn't really matter. At least that's our experience. So this is an example of the spherical harmonic decomposition. The field on the top is what we measured. Then in the middle is the field that's been decomposed into its spherical harmonics, as we call it, or basically the result of the spherical harmonic decomposition. And we see the difference between the two data sets. And there's a few interesting things. Obviously, there's a lot of noise in the difference, which is good because that's what we wanted to get rid of. And then we also have sort of these bright regions here, which we attribute to minor temperature fluctuations. And because the minor temperature fluctuations almost act like a field source, the spherical harmonics don't fit those. So it's actually also a nice way of getting rid of subtle temperature fluctuations. If it gets more extreme, then it also starts potentially fitting into the spherical harmonics.
I'm sorry. You said you need a temperature stable environment.
Yeah.
Does it only have to be temperature stable during the shimming process and can then ship it into a different environment? Or will you have to do the entire shimming process again if you have shipped the thing into a different environment?
Very good question. So it technically only has to be, at least from the shimming perspective, it technically only has to be stable during the mapping, not during the entire shimming process. We treat temperature variations at the moment, we treat it as a 0th order term. So basically that the whole field shifts up or down and the distribution doesn't change. As long as the distribution doesn't change, then you don't need to do any reshimming. What does influence the distribution more is the external magnetic field. So the mapping that we're doing here, probably 5 meters to the right in this image is our 7 Tesla MRI scanner, and that's probably quite a significant contribution to the background field, more so than the temperature fluctuations.
Maybe just one comment. So if you would use different materials for the shim magnets as for the normal magnets that have different temperature coefficients, then but this whole temperature stuff, it's probably still something to really check, like how strongly the field variations are, and also how strongly inhomogeneity is. And then you also have things like inhomogeneous temperature distributions, most probably due to either grading coils or a patient head or positioned in the magnets. But these are things that still needs to be characterized, investigated on how much it really affects imaging in the end.
So I showed on the very first slide, I showed the magnet simulations and that we simulated a homogeneity of 3000 ppm. Like I said, I did the correction the wrong way around. So instead of getting a field that is somewhat close, we ended up with a field that had quite a severe B0 inhomogeneity of 25,000 ppm with that very specific field distribution that I described earlier. So if we try to do imaging on this, we can sort of estimate the line width that we would get, which is an important measure for people doing MRI. And we get a full width at half maximum of around 10,000 hertz. So this would be entirely unsuitable for imaging. Just to give you an idea, Wouter, on the 7 Tesla, which is notorious for having bad B0 inhomogeneity, this would be on the order of 2-3 hertz, maybe. Over the entire field of view of 40 centimeters. Yeah. So obviously we have to fix this. So the way that we do this, which is now getting to the point of the talk, is we do this by shimming. So shimming is done slightly differently on low field than it is on high field. On high field, because for the field itself is already more homogeneous because they don't have to make the magnet so short. But also because the field is stronger, they use iron inserts. The field itself then magnetizes the iron, and then that gives a small perturbation to the field. At low field, the magnetic field is not strong enough to fully saturate the iron inserts, which makes it very difficult to do an optimization if they're not fully saturated. And then also because the field itself is also lower, the field produced by a piece of iron is not strong enough to correct the inhomogeneity. So we instead of using iron pieces, we use small magnets to correct the inhomogeneity. And like I said before, it's very important that this shimming is performed on measured magnetic field. This is not something that can be pre-computed. But what you should do is you should not assume that you're not going to need shimming, that you're very good at building magnets and that you're going to build the perfect system. You're not. So you have to, from the very beginning in your magnet design, think about where you're going to be putting your shims. And this is also an iterative process. So when you're designing your shim system, make sure that it's easy to remove, which is also why on this system, we put them on the outside on these plastic trays so that we can always adapt them quite easily. So the shim calculations, the calculation is all done in Python. Like I said before, it will be open sourced, but I'm just a bit too embarrassed to put the code out there at the moment in its current state. There's a lot of code in, well, it's not that much code, but there's some code in there. But the important thing are these 7 variables, where you just define the size of your magnets, the remanence field of your magnets, so basically the grade of the magnets, where you're going to be putting the shims, which is somewhat decided by the position of the shim trays. You can have maybe plus or minus 1 millimeter, but really this should be fixed. And then you do have to define where you want to be putting your shim magnets, like along the bore. So the shim trays have certain positions that can be filled. So there are certain values that this can take, and this is something that you definitely should sort of a trial and error thing to see how much do you actually need. And then again, in the mags per segment is basically, I'll get to that in a minute. These last ones are basically, again, defining within the ring, where do you put the magnets? And then the only other thing is you have to read in your measured B0 map. I can't spell measured, apparently. And the program then calculates the optimal shim configuration. So this is really failure on the spelling. I was clearly tired yesterday. So this is the initial field map that we're putting in. This is not the one that we had in the original slide because this is the sort of the second or third iteration, which is why it looks differently. But the algorithm then calculates field distribution from the shim magnets that basically gets added to the main field distribution to then cancel out as much of the field inhomogeneity as possible. So the script then returns basically the characteristics of the new field. So we have the initial homogeneity of the map that it's read in, the homogeneity after the shimming, and then the reduction in the standard deviation. And the reason we report the reduction in standard deviation is because that's quite strongly correlated to line width. Whereas the homogeneity in terms of ppm, it can be 1 or 2 data points that completely explode your homogeneity in ppm. So at some point that breaks down as being a useful way of looking at the field distribution. And I'll show that for the later iterations. And then it also produces a plot, and more importantly, it produces some text files which describe the orientation and the position of all of the shim magnets inside of the shim insert. We then take this text file, which is the XYZ position and then the angle. We load it into FreeCAD, where we have a macro which basically plots those that magnet distribution. So again, just make sure you fill in the magnet size correctly in all of these things, but then it's a relatively straightforward process for producing the magnets. Then on to the construction stage. So we have white shim trays, Lukas has black shim trays, no reason other than we ran out of white plastic. The shim magnets themselves are placed in plexiglass holders. You can 3D print them. Our personal preference, or our personal feeling, is that 3D printing is less accurate than laser cutting. And also 3D printing takes a really long time, whereas laser cutting is relatively fast. And then we place the shim magnets on the trays on the outside of the magnet. So this was this filling of this ring. You'll notice that some of the magnets are some of the trays have fewer magnets in them and of different sizes. This is an old shim algorithm that we no longer use. So on basically going forward, all of them will always have 7 magnets in them with 6mm magnets. Again, this also makes the construction process more consistent. So this is after the first iteration, we go down from 25,000 ppm to 6,000 ppm, and our line width improves from 10,000 hertz to 3,000 hertz. So, progress, but still a long way to go. So it basically comes down to the iterative nature of these shimming algorithms, where we basically just repeat the process. We once again put the magnet in front of the robot, map the field, run the shim algorithm, get a different distribution of magnets, plot it, build it, and repeat it again and again. So this is the second iteration. So we go down from 6,000 ppm to 4,000 ppm, and we see again the line width is now getting to a point where we can actually use something. So this is 300 hertz, and the last iteration is also a little bit to show you where the ppm starts to break down as a useful measure of field performance, because between the second and third iteration we go from 4,000 or there's only 15% difference in ppm. But if you look at the line width, we go from 300 to 100 hertz. So it's a factor of 3 improvement in actually the relevant number. I did run it for a fourth iteration, but then the line width goes from, I think, 118 hertz to 107 hertz, and I ran out of energy, so I didn't build that set. So some general notes on the shimming. There is a limit to how good the shims can be. Typically, this is equal to the initial simulations of the magnetic field. So the shimming is not going to be able to make your 3,000 ppm simulation into a 100 ppm simulation, but it will be able to correct the errors that are introduced during the building process. It's very flexible in terms of what magnets that you can use. So I know, Stefan, if you're still listening online, this is a relevant question to you, or a relevant answer to you, and it's come up a few times, is in the code, you can just define the strength and the size of the magnets that you have. You know, if you try to do this with 3mm magnets, you can do it with 3mm magnets, but instead of filling in 4 of the shim tray positions, you might have to do 10. The algorithm doesn't care too much. So just kind of use what's available to you. Don't stress about it too much. Also, don't try to get it perfect the first time. The shims themselves, you will have errors in the shims yourself that you build. So the shims that you construct are not going to be identical to the shims that you simulated, in the same way that the magnet that you construct is not the same as the magnet that you actually built. So 3 or 4 iterations are typically needed. Also depends how good your initial build was. And in the code, just try to adjust the number of magnets that you're using, where you're placing those magnets, and then see sort of what is an optimal configuration. My recommendation is, on your first shim, don't do too many shim trays, because I did it wrong about 5 times in terms of field orientation. Like what was important was that the coordinate system of the mapped field exactly matched the coordinate system of the simulations. If it doesn't do that, you're only making things worse. So in the end, the first shim iteration that I did only filled 2 of the shim ring positions, just because otherwise you're spending way too much time doing it wrong every time. Also, you know, there's the difference in shim performance between filling in 4 ring positions and filling in 32 ring positions is not that huge. So don't get carried away in that regard. And with that, I think I'd like to end and ask if there's any questions.
We already have our first comment from online.
So I will read the question. If you had a little conveyor belt going under a field probe in your lab, it could be set to mark the side of the magnets on one side. Warning for duds or inverted magnets would be a fairly easy thing to design and good for quality management of manufacturing at low cost. Agreed. Sounds like fun. It's open source. Please build it, Julian.
I have a question. How long will take one iteration of the calculation of?
It depends on the resolution of the field map. So if I was running some of the simulations to make the plots last night, 10mm resolution, which is probably identical in performance, so a 5mm resolution took maybe a minute or 2. It also depends on how many shim trays you filled, but it's not huge. No.
Another quick question to the optimization. Does your algorithm also in the further iterations take magnets away, or is it just adding magnets?
It's always adding magnets.
But it's not like iteratively also taking some away again.
No, because we glued them in place in the shim tray, so it would be we would have to remake the shim tray in order to remove the magnets, which is not ideal because you could introduce errors that way as well. Yeah. I know on high field, so I think the question comes from high field where you can screw in iron pieces and then remove those, but because for us everything is sort of glued in place, that's not an option.
Tell me, you said that you laser cut the holders. How you did it in Uganda? They had the laser cutting there as well, or if not,
no,
what was the procedure?
It's a very good point. They do have 3D printers in the lab, so there will likely be a 3D printing.
What is then the difference in timing? Like how long it took you there?
That is a very good question. I
mean, what is the time you can save with laser cutting compared to?
So I can't remember the exact time it took to print one of the shim trays. I did try it at some point. I feel like it was about 24 hours to print the 12 shim trays that you would need for one, and it takes about half an hour to laser cut.
You also got active shimming, right?
No. With the gradient coils.
With the gradient coils, right? When you end up in this 3000 ppm range, how strong are your DC gradient currents and what gradient coils you all use for like higher harmonics and stuff?
So we don't do higher harmonics using active shimming. On the improvement, it depends. So we're talking about 3,000 ppm here, but actually the relevant number for MRI purposes, like I mentioned before, is the line width. The line width improvement with active shimming depends on the object size. The bigger it is, the less effective. On the head, it's usually a factor of 2 or 3 improvement in line width that we see, and that is typically 0.1 millitesla per meter on the gradients. So that would be 0.2 amps, 0.2 amps.
If all shimming rates are identical around,
yeah,
all are identical.
Yeah.
One further stupid question to Lukas and you. Other labs in other fields have reported that they use like active heating of the magnet to keep the temperature stable. Is that something you ever considered, like at a I don't know, reasonable temperature of 36 degrees? That might also be an option.
So we typically would avoid that situation because of energy draw. Yeah, there is something to be said for it, but I mean, our energy consumption is very small, and we would sort of like to keep it that way. So in theory, we could probably run the entire system of a single solar panel. And I think once you start heating things up, that becomes obviously more of a problem.
Yeah, I think all the temperature stuff is not that easy to implement in the end. But I think it's a nice idea. But probably the first way to go is to see what all these fancy other correction methods and deep learning and whatever can do, and then we can still see if it then makes sense to heat it up.
This is within reason, so I think it also, we've also always used these systems in our lab, and there's if the temperature changes more than 5 degrees, then that you start having, or really for some of the coils we're building now, if it changes more than 2 degrees, you start having issues with the coil bandwidth. So I think we'll have to see how this actually works in the field. I think for now we're just enjoying the fact that we're relatively stable within our lab environments.
And maybe another question from someone who doesn't know it. How much, if any, of the inhomogeneity of the field can be accounted or worked around later in software in the image reconstruction part? Does it have to be perfectly homogeneous, or is there some wiggle room that you can correct for if you know exactly how it looks like?
So there is definitely wiggle room. Yeah. Without going too much into the MRI physics, I think just based on feeling, I think if you're within sort of 1,000 ppm over the region that you want to image, then you can correct for it in post-processing quite easily. If it gets much more than that, then you start running into shading issues in your images and sort of not being able to excite the sample in the way that you should, and then the whole thing becomes a little bit more complex. But it's as long as there's just small image distortions, then there are ways that you can map that using your MRI scanner itself. So you would get a real-time image of what the magnetic field looks like, and then you can easily correct that in post-processing as well. Because we also have to do the same for the gradients anyway, so that there are standard ways of doing that. The gradients not being perfectly linear. So, yep.
All right. I have good news. The Wi-Fi works again. So if you want to use it, yeah, it's the same password as yesterday and the days before. If you don't have the password yet, please approach me. And now we could do another coffee break, or we could go directly to Dinh. All right. Did I find the presentation first? Download here. The gradient. I didn't. Okay. I thought I did. So let's see. Oh, here. Coil. Here. Cool. Here. Yeah, okay. And now.
Thank you. Different font. Okay. So I was asked to tell a little bit about the gradient amplifier, how it is built, the circuitry, and how you can build your own copy. And so that's what we're going to do. The gradient amplifier receives 3 signals from the spectrometer, which are analog signals. Of course, they have to be amplified to be able to drive the gradient coils. And on the left, you can see a typical signal that is sent to the amplifier, or actually to the coils in this case. The gradient coils, as it was meant in the design specifications, is a typical value of about 180 microhenries and a series resistance of 0.4 ohms. And that gives me a bandwidth of 350 hertz. And the desired current that goes to it, the intended current, is within plus or minus 15 amps. And we want 7 kilohertz bandwidth. So that's already a lot more. The voltage coming from the spectrometer is within plus or minus 10 volts and 16 bits. And, important here is output resistance. 16 bits get me a dynamic range of 96 dB at least. And that sets a limit on the noise that is allowable within the 7 kilohertz bandwidth. And especially also at 2 megahertz for our magnet approximately. The electromagnetic interference, which comes from noise, is important. Now, it should be possible to power it from batteries, so low power losses and a robust design. So safety is first. There are lots of fuses for a battery power device. That is a must. When you switch on the amplifier, there's a limit on the inverse current. There are large capacitors inside, so you want that. If you accidentally reverse the supply voltage, that's protected. And if your battery is drained, it will automatically switch off to save the battery. There's an overheating thermal shutdown in case maybe your fan or something fails or the cooling is not proper. If you want to get more current out than intended, it is limited. And there's a clamp on the input voltage to protect the input circuitry. And there's electrostatic discharge protection. Now, the amplifier is designed around a nuller. And a nuller is a building block. It's a 2-port. It has an input port and an output port. And in any case, any output it produces, it has 0 input, no current and no voltage. And it's a bit a miracle device. Not really useful by itself, but if you use a feedback network around it, you can make a desired transfer function. And that can be with that the source and load impedance have no influence. So the type of amplifier that I want. So I have a driving voltage source And the magnetic field is proportional to the current. So I want a voltage to current amplifier. Now, the feedback network here is R1 plus the wire that is connected to it. And here you can see that since the current at the input of my nuller is 0, that means there's no voltage drop across the series resistor there. And that means that there's no voltage drop. So the entire V in arrives at the input of my amplifier, so it's independent of my driving source. Now, no voltage difference at the input port means that the V in is also across R1, and that sets the current. And in series with the output is the gradient coil, and so that has to carry the exact same current. So also the coil itself has no influence on the transfer here, which is nice because the bandwidth was way too low, and that's already solved here. Now, you calculate what resistor I need, and it turns out I need about 150 watts, and that's even more power loss than in my gradient coil itself. So for a battery-powered device, that's not a solution. So what if I do a smaller current with the amplifier as before, and then a current-to-current amplifier? So bottom left, you can see the current source with its output resistance R3. Now at the input of the nuller, there's no voltage drop. So that means the other side, the minus port is also at ground. It's called virtual ground. So that means that across R3, there's now no voltage. So the output resistance of the current source has no influence here. And since no current can flow into the nuller on the input port, all the current has to go to R2. Now the left side of R2 is at virtual ground. And that means that both resistors R2 and R1 have the same voltage. And that's where my gain comes from. So it's the ratio of R2 and R1 that sets the output current. Now, the combined current can only go to the output port of the nuller, and that is in series with the gradient coil again. So the advantage here is that now R1 can be made arbitrarily small, and therefore there's as low as you can power dissipation. And also there's now more voltage room left from the power supply to the gradient coil, which is nice for fast responses. Downside here is that any real nuller that you implement has a bit of offset voltage at the input, and that converts to a current. And so, yeah, that's something to look out for in the design of the nuller. Well, since the driving source is a voltage source and it has a series resistance, maybe I can convert it to a current like this. So R3 is my 200 ohms here. And on the right side, it is connected to virtual ground still. So that gives me a current, and that is then amplified and goes to the gradient coil. But now I'm loading the source. And also if you have a different spectrometer, maybe with a different resistor, you get a different gain. And so that's undesired. I want my gain to be independent of what you connect to it. So independent of the source impedance. And also, if there's a common mode voltage present on your driving source here, the input voltage, that will also be converted to a current, which is not what we want. This is then the final topology of the amplifier that is built. So at the input, there's a differential amplifier with a unity gain, and that senses the voltage across the two wires of the driving source. And you can see the VCM, the common mode voltage here, that is in series with ground, is subtracted. This is completely cancelled. So only V in arrives at the top of R3, and that is then converted to a current through the resistor, etc. It's converted. There's a current gain. And series again is my gradient coil. So in green is the implemented nuller. So you can see it's independent of the common mode voltage. Gain doesn't depend on source and load impedance. And since there's 15 amps running through my gradient coil, you don't want any part of it to flow back to the input or neighboring channels. So that is already solved here because the input impedance of a differential amplifier is extremely high. Downside of such a differential amplifier is that it adds noise. And luckily it's not so much that I won't be able to reach my desired noise specification. This is then the implemented circuit. So just quickly, In red is the differential amplifier. In green, the nuller. And it is completely controlled by the feedback network in yellow. And new here in blue is the monitoring, where you can monitor the current as you are operating it. And that's what I'm going to tell how you can build one. So you can download all the production files and a bill of materials. And the design files you need to create the front panels and other plates that are there. Some board manufacturers can also assemble the components on there for you and even order the components. And then I always look out that, for example, there are some very precision resistors there that have a very low temperature drift. And I just heard that it's not so relevant anymore since the magnet itself is drifting a lot. I used 50 ppm resistors in the feedback. So a board manufacturer might say, oh, I have the same resistance value laying around, maybe with a different temperature coefficient, and will easily replace that if you don't say you should use the part that I say. This is what the board looks like, and MOSFETs and the transistors, the true hole ones, have not been soldered yet, because they need to be soldered or they need to be mounted on the heatsink. And also important here is if you solder your board yourself, first screw the connectors to the bottom and solder afterwards. Otherwise you get a lot of stress on your solder joints. You might break the PCB. Now then the heatsink requires a little bit of drilling and tapping to mount all the components on there later. So be careful that you don't damage the flattened surface, because it's made very flat to have minimal air gaps and minimal air pockets. And if you scratch it or make dents even, then you get less cooling.
Sorry, I have a question. Is this hand soldering? All of them are hand soldering?
Oh, yeah, we did our board hand soldered. You can, so if you want, you can ask your board supplier to do that for you. But we have specialized equipment for that, SMD stuff and an oven. And, I would not recommend using a solder iron to solder all these parts. So the back of the MOSFET is the cooling tap, but it is electrically connected to the drain, which is the output of my amplifier. And all the amplifiers are on the same heatsink, so they need to be isolated from each other. So I use a thermal sheet that you can just buy and cut in 50 by 50 millimeter squares, but that increases the thermal resistance. So to lower that again, I use heat spreaders that distribute the heat over a larger area and then conduct it to the thermal sheet. This is what it looks like after assembly. So the screws that you mount here need to be isolated. So you use shoulder washers to maintain isolation. All the screws there are fastened with 0.75 Newton meters, and that is the optimal torque for the cooling of the MOSFETs. And so we want all the screws at the same torque. Then the components that are mounted on the heatsink need to be connected through the PCB, so you need to bend the leads. And here on the bottom left, you can see how not to do it, because there you create stress on the package, and it can cause cracks and ultimately lead to its failure. So in the second picture there, you see how to prevent any stress, mechanical stress on the package. Now to get even better cooling, there's some thermal paste on the MOSFETs, but that is conductive, so be careful that it doesn't flow to the mounting hole. Otherwise, it won't be isolated again. If it happens, by the way, you can just measure it with a multimeter and clean it with a little bit of alcohol and try again. So then you loosely screw all the MOSFETs and transistors on the heatsink, as you can see here. And then you place your board over and connect it, mount it to the spacers. And then it's properly aligned. And now you can fasten through the PCB. There are larger holes where your tool can fit through, a screwdriver or a torque, whatever. Then you tighten it at the 0.75 Newton meters. Check again that no thermal paste leaks through. Don't solder it yet because there are temperature sensing resistors on the bottom of the PCB that hover just above the packages of the MOSFETs for monitoring. And they need to make thermal contact. So for that you can use gap pad. That's slightly sticky. So if you place that on top of the resistors, then you can turn the board around and it will stay there. Don't use the thermal paste that was in the description before, because that is conductive and creates a parallel resistance with the temperature sensing resistors. So don't do that. Then the board can be soldered. So you place it back on, including the gap pad now. It's always best to, so first you make sure that it's properly screwed onto the spacers, and then cut off the leads. And lastly, solder all the leads, because that's the way you get the minimum stress on the packages and the solder joints. Then the enclosure. So you need a little bit of milling and drilling on only the left side. And there are notches on the bottom there, that is shown in yellow. They need to be flattened, they are bent inwards. And otherwise your heatsink won't go flat against the inside. For the power supply filtering, there's a ferrite holder. It's a 3D printed part. You print it twice and press M3 nuts into the cavity. If that goes a bit difficult, you can use a screw and pull it from below into position. Now, next you slide the ferrite on and do it carefully because ferrite is a very fragile material. If you drop it, or it will easily break, but even at shock, mechanical shock, it can degrade. So handle it carefully. Fix it with a little bit of RTV and then put two halves in each other, and now you can put it onto the bottom of the enclosure. There are also the relays, the heatsink and the capacitors. This bottom plate, by the way, is also ordered from Shaver with all the other panels. There goes my voice. The ground is in a star point configuration. And that's important. You don't want to have any of the 15 amp currents from one channel being able to influence a neighboring channel. And it's also important for the supply voltages itself. So this is how it is implemented. So the larger strip here is the ground, star point ground. And it's screwed directly onto the big capacitors. Here I used stainless steel bolts. But later we found that brass gives better conduction, so it gives less voltage drop. And also, if you are assembling this, make sure that the polarity of the capacitors is correct. Thank you. Because if you have a reversed, if you connect that reverse, then there's gas building up inside, and it can even lead to an explosion. There's a safety vent there, but it can really blow up. Then, from those strips, the supply voltages to the PCBs is connected with other strips that go over some of the other voltages. So to do that, there are aluminium rings underneath. And if you do that on both ends, it safely goes over the other voltages with no problem. And also here, all the screws are brass because it gives you the least resistance. There's a ground bracket. This was the best photo I have, but ground bracket that connects the enclosure to the star point ground. That's over there. Then for the reverse polarity protection, there are some diodes that need to be connected to the strips. So to do that, there are solder lugs available. Cut off the left lead here. That's important because if it bends down, you make a short circuit. So don't forget it. Now next is just assemble the front panel and the back panel. Speaks for itself, I think. And follow the wiring instructions. There are lots of pictures available and a list of all the connections that need to be made. Make sure that you maintain the star point configuration, so don't change this scheme. Now, then proper assembly of this type of connector sometimes goes wrong. So what you need to know, you use this tool that is shown here. And the way this works is you just place the wire on top of the connector and press it all the way through. So on the left, you can see that it didn't go, the pin didn't cut through the insulation layer properly. So it might make a connection, but could lead to failure after some time. And maybe there's some contact resistance or just comes loose after a while. There's ESD protection at all of the BNC connectors, which is shown here on the left. It's soldered directly onto the connector. And on the right, you can see a ferrite bead for extra EMI filtering, high frequency filtering, on each cable. And the inrush current limit is done with a relay. The relay is open at startup, and that allows that the capacitors can be controlled, charged with a controlled current. But if you open the relay, it produces a back EMF voltage. And that needs to be clamped. That's not internally in the relay itself, so that needs to be added to the wires. And I can show you here. Here in this wire, there's the relay. It's in a heat shrink. And together with the wires that are connected to it, and the brown and the white wire here. And same for the other side. Now, power supply can be a regular power supply. Off the shelf, there's one in this scanner as well. It's the same power supply. You can also power it from batteries. But important is that there's no local common ground at the power supply. So that would interfere with the start point configuration. And also the fuses are in the ground leads. So if you have the local common ground, if one fuse blows, then the other will take all of the current, and just the stops after that, that is blown too. Then there's a cover. So since the small resistor that is in the feedback network makes it very sensitive to input offset, and input offset is temperature dependent. So there's a cover that goes over it, and there are even paper covers directly onto the amplifier channels, just to prevent air swirls, and that makes the biasing mostly very stable. The input is already a lot stabilized in the circuit, but biasing still depends a little bit on air swirls. So that's solved this way. And then you can bias the amplifier. So all the channels need to be pre-biased at 200 milliamps. So what you do, you can access the trimmers through the perforated strip here. And you set them all to 0, and then notice what the remaining current from your power supply is, and then add 200 milliamps by adjusting one after the other of the same channel. And if you then also apply a small sine wave at the input, you can see there's some crossover distortion. When there's a 0 crossing, you can see the signal is distorted. And that is gone once it's properly biased. So then you can see that it is properly done. Now, then we did a noise measurement. I tried to measure the noise current because I thought that was the most important. But I wasn't able to do that. I don't have equipment that can measure it, but I could measure the voltage on the output, noise voltage that comes from the noise source that is shown here. And it was measured to be at about 50 dB over the thermal noise floor. So that means that my shielding inside of the magnet needs to attenuate about 50 dBs to prevent any influence. So you can see here how it can couple. So there's the gradient coils and the RF coil, and they form a transformer. And also there's capacitive coupling possible. So the shield in between should block that, but unfortunately it didn't do that enough. So filters were added at the output of the amplifier, a notch filter, exactly at the intended frequency. And that now almost implemented all of the attenuation that we needed. The last few dBs needed to come from the shielding inside. And then we did a measurement, and now when it was switched on with filter for the first time, so Tom was measuring the noise before and after switching on, and now we couldn't even see any difference. So we were not even sure that it was connected properly. But now we could do nice measurements with it. And that's about it. Wish you good luck with your MRI project. And if you want to know more about the whole circuit design, that's described in this document. It's also available. And, and I have one question that I always get. Can I get more current? Usually just after delivery. This way, by the way, it was the other way around. It was, no, I can do with half the current in the first amplifier. But since the whole transfer function is determined by the feedback network, you can change that. So the best order to do that, R3 has the least influence on the rest of the amplifier. So do that if possible, but at some point you will run in the limit of how much current the differential amplifier at the input can generate. So then you might need to increase R2, but that is the dominant noise source of the feedback. So you will get more noise then. And if that's still not enough, you could lower R1, but then you're in trouble. So just try to do R3 if that's possible. But if you go to a higher current, then also all the other components need to be suitable for that. So that must be checked. That's it. Any questions?
So I'm going to turn around the request, and what if I want to go to higher voltage instead of higher current?
Yeah, so there are some components in, they need to go to the amplifier. So there are some components there with limited supply range, especially, for example, the input buffer. So it can go, I think, up to plus or minus 18 or so. But that sort of components put a limit on how much you can increase the supply voltage. So, and 1.8. Yeah. And then double for the symmetrical power supply. So that's a limit, but if you want to go higher, and since the input only goes up to 10 volts, the signal coming in, so I don't need the higher voltage there, so I could reduce the voltage locally, and for the rest of the amplifier, make it higher. That's but cooling becomes an issue, so you need to check all the other things in the design to make sure that it's still properly working within specification. But the op-amps that are used inside design put a limit on the maximum voltage. Yeah.
There's also a question from
online.
So there's an overview of tools and skills that are needed to build it.
Sorry, the tools? Skills, yeah. Yeah, so that's a good question. So especially for equipment that might even later be used medically. So good quality soldering is important. And there are some grades in that. So if you're just a electrical hobbyist, then you don't have the proper tools, then maybe you should ask your board supplier to do that. So what you at least need is either a way of dispensing the solder paste onto your PCB. So there are sheets available where you can just put it all over the PCB at once and then place the components. You might want to need a microscope so you can see that it's properly positioned. And an oven to solder everything, because hand soldering is really not an option here. So if you do that, you create too much thermal stress on the packages, and that just degrades the lifespan. Yeah.
Okay, but there's no overview yet somewhere.
No, there's no description. No. True. Yeah.
I got several questions. Like, what are the specs right now for the system? You say up to 18 volts, but what did you drive it right now? Like 12 or
no, so
15 or?
Yeah, so 15. It was intended to be battery operated. So depending on the voltage you use, you can even adjust your biasing for it. So car batteries typically say 13 volts or so.
Okay, so at 15 volts, how many amps then? Plus minus 10 or?
15 always.
15 amps.
Always. Yeah.
Okay.
Yeah. Doesn't depend on the supply voltage, except that once you go to a very low voltage, then you get slewing because the voltage you need to increase the current rapidly in the coil just is limited.
So how did you tune the several channels to the different coils?
Yeah, that's the reason why I chose to make it a discrete amplifier. So I use a phantom 0, if that says anything. So here, this is where all the frequency compensation is done. And that creates a 0 in my S domain. And that pulls away the poles from the right half plane. That makes it stable. And the way they're positioned right here is a Butterworth transfer. So that's a very nice transfer for a coil. And I chose it such, the position of this 0 here, which comes from this coil. I chose that for the range of 20 microamps up to 1
milliamp. See your
milliamp.
pointer at the moment.
Oh, sorry, it's not shared.
Why?
Oh, now it's even gone on my screen. Uh-oh, now it's going to crash in 10. 9, no. But it says here the pointer is on. Now, so the 0, which is the circle in the plot on the bottom there. There. Thank you. Is positioned such that for the range of inductances that I need to handle, that I always get a stable transfer. And now you can see on the blue transfer on in time domain on the bottom, there is no overshoot and it looks nice.
So do you have a trimmer resistor or you have to adjust the inductor?
No, also no adjustment, just like this, and it can handle the entire range.
Okay. And then you also got LEDs, status LEDs at the front for each channel. So, because how did you surveillance the channels if you have like overheating or something?
Exactly. So the resistors that are hovering just above the MOSFETs, that is signaled by these LEDs. So if one of the channels gets too hot, then that channel will be signaling.
Is it auto reset himself, or did it stay?
So you can only enable the amplifier or switches off with the power button, but it switches itself off and keeps doing so until that situation maintains. So if it's still too hot, it will always just shut down the amplifier.
When it cools down by itself, then it switches on again?
No, you have to do it.
Okay.
Yeah, it's a flip-flop that's inside and remembers that there was an error and will not switch on by itself. And there's even other errors that are checked. Was it? I forgot what. There were some other checks in there that also disable the amplifier. And in the same way, if that error is solved, it won't turn back on. Status LEDs are only signaling the temperature. So those go off when the temperature drops to a safe value. Yeah. It's back online again. Yeah.
Something for the specs that we also need to think about.
Yeah, so on purpose. So it was a brilliant choice. So we wanted to make it possible to power it from car batteries.
The main problem, from my experience, is most likely the first stage, because these have like these voltages for the what you need, and the end stage is most likely can higher voltages then. So most likely you can. Is it possible to just put like 30 volts on it and then make a linear regulator for the?
That's exactly the question as before. So this amplifier is precisely what you say. So that limits the supply range that you can handle, but you don't need that large supply range at the input, only at the output where all the stays before that. And if you can decouple that, then you can.
But is the circuit already separated in this regard?
No, not as it is now.
Okay.
No, it's so it's a single supply rail. Yeah, this goes over whole amplifier. Yeah.
Yeah, thanks, Danny. That's a very nice amplifier.
Thank you.
And I just want
There's
to
always
advertise
some-
for Danny, that design document that he's made for the gradient amplifier is unbelievably interesting and extremely detailed. And it's a I think it probably sets the gold standard for what we want to do in terms of documentation in this project.
Agree, completely agree.
It was done during Corona, so I had a lot of time.
And we have, so Danny he's worked on quite a lot of the electronics for our system, including a preamplifier, a low impedance preamplifier that unfortunately we're not using at the moment because low impedance turns out it's probably not the way to go. But again, from a preamplifier design perspective, he's created a similar document. So it's very, very much appreciated by the community, I think.
Thank you.
I don't know if we shared that document, the preamp document. I know some people have it, but I think we should just make sure that it's also available online.
No, the preamp not. No,
I haven't seen it yet.
The gradient one is available on GitLab,
yeah,
but not for the preamp one, but that should be rectified.
But it is not used yet, or?
So no, it's so it can come up in the RF coil discussion, although I don't specifically mention it. The reason we were trying to use it as a way of sort of cheating the system, that we could broaden the bandwidth of the RF coils without introducing noise introducing losses. But it doesn't seem to be as effective as we'd hoped.
As you hope, yeah.
Yeah.
Okay.
So actually we end up with slightly more noise. Slightly less signal than we would with a normal 50 ohm configuration.
Yeah. Okay.
But I'll show you some of the it will come up later. Yeah.
Maybe one more question. So the 18 volts supply, this is without a problem for the current design?
I have to check for all the components. So there are
the current consumption at zero input power does go up quite considerably if you
that's
if
one
you
thing.
increase the voltage. So the power consumption of the system at rest does considerably increase.
There's normally about 200 milliamps here, but if you have set that at some supply voltage and then lower that voltage, you get more current running in the output stage. And that's one thing that's a bit disappointing in the design.
Would that be an issue, or what's the gain of currently we are, I think, at 13 volts to 18.
So the gain would just be more voltage overhead on the preemphasis, on the voltage preemphasis.
Yeah.
I would say it's only an issue if your supply voltage changes while you're using it. So if you bias it at the voltage that you are going to use it at and stay at that voltage, it will not change. But if you are doing it with batteries, which when the voltage drops, they start to get more, draw more current, so they are drained even faster.
Okay.
But it's there.
Okay, for the now I got it, for the battery operation. Yeah.
So the main limitation for low voltages is if you have high resolution images with, if you want to have long sampling rates, then your bandwidth goes, I don't know, down or up. At least the gradients go very high, the phase gradient and the readout gradient. And if you have this, what current you can push depends on the resistance of the gradient coils. And then if you have these high resolution images, the voltage that you need to push like 9 amps or 10 amps, if you have like 2 ohms of resistance, then you only can push like from like 12 volts, you only can push 6 amperes of maximum current to the coil.
You mean that the biasing takes away all of the range that you have in your supply voltage? There's nothing left for the gradient coil.
No, I think you're looking at it from a static perspective, which is that which is certainly true that the ultimate limit is the fact that the V equals IR. But obviously we don't want to wait forever for our gradients to ramp. Of course. Yeah. So then the inductance of the gradient coils. Yeah. So that's where the voltage pre-emphasis comes in and is very important because it allows you to reduce the it's obviously you can scan faster because your gradients come up to strength faster, but also having a lot of overhead on the both the voltage and the current allows you to also shorten your phase encoding gradients considerably, which reduces your echo time, which again allows you to scan a lot faster. So the voltage is much more important than the V equals IR. So it's sort of the whole interplay between gradient inductance, gradient resistance, gradient amplifier voltage, and output current. I mean, at the moment we're able to produce images with the gradient amplifier as it is, and it's always like Danny says, you know, the moment it's finished, it's like more current, more voltage, and it's because
you have a very inhomogeneous magnet, and to compensate for this, you need higher gradients. This is
we don't scan up particularly high gradient strength. So the typical acquisition bandwidth is 20 kilohertz, which is lower than high field systems would use.
Okay, yeah. And your image gets not distorted.
No, we could drop it, but then the echo time goes down. The echo time goes up. The echo time goes up because the acquisition time increases. So it's again trying to find a balance in there. I think with the current gradient amplifier, at least on the previous magnet, we could even image at 50 kilohertz, but the SNR goes down.
Just thinking a little bit from the technical specifications document. Do we want to keep it at this, like considerations of battery power supply, which I was not thinking, to be honest, about, or the question is if you want that, or if we say, okay,
drop it,
drop that.
My feeling at the moment is to drop it, also because I mean at the end of the day, okay, you would have to look at the entire system. I think it doesn't at the moment. It doesn't make sense that it's very very cool that it's battery powered. It's but at the moment it's the only part of the system that's battery powered. So it's a little bit silly is maybe a little bit of a negative word, but it doesn't fully make sense that the one system that would really benefit from having more voltage is the one system that we're sort of tying down by sticking to the battery. So I think I think this is something seriously to consider. Either we make the entire system battery powered, which I mean it's possible. I mean we can the spectrometer can be battery powered. The RF amplifier is, again, if we move to a lower power model, is something that could easily be battery powered. We could run a laptop off a battery, but it's not where we're at the moment. So I would say, honestly, if at this point, I would say probably let's see what we can do by moving away from battery powered and perhaps raising it to 30 volts or something like that. It's and whether that's a minor modification to make or not, I think that's probably where Danny's input can come in, or Marcus, you also have some experience in this field.
Yeah, no, I completely agree. I think it will be much easier if we don't have this option, but maybe it's also just a question to the group if there is any veto on that, because I will then put it as remove the battery powered option from the technical specification document. And then the next question would be, so how do we proceed? We can take this design and see what we can squeeze out in terms of voltage, and proceed like that, or we can say we keep it as is. So without the battery powered option, but considering the whole scanner. But now we fix it to the supply voltage of this 13 volts, or do we want to see what we can?
Is there something you cannot measure now the way it is, and what would you gain? So if it really helps a lot, then it's worth the effort. And otherwise, if you can already do all the scans you need, then yeah, maybe leave it as it is. We'll focus on other things maybe. That's
I think at the moment probably it's the biggest limitation on the system is the voltage overhead on the gradient amplifier in terms of improving the scanner performance. Also in terms of reducing the acquisition times on scans. If we're able to reduce the echo time from 20 milliseconds to 14 milliseconds, we're scanning 30% faster. And I think if an acquisition can go from 10 minutes to 7 minutes, that's from something that obviously I don't want to downplay it, and I'm not the person doing the electronics, but for something that's potentially a relatively minor modification of the system, then I think that it's worth thinking about.
But how much should you need then? I mean, how much voltage, for example, to get this 30%? Like, what would be
I think that there we would have to look at some simulations or some calculations.
Yeah.
On because it also depends what we're going to. It directly interplays with the gradient coils. If the inductance on the new gradient coils on the new magnet is less, or the resistance is less, then there is more room to maneuver there as well. So I think there this is. This is not a unique. This is not this is something that can't be viewed in isolation. I mean, it's a direct. The gradient coil design and the gradient amplifier design really go hand in hand, much more than with other parts of the system.
Yeah. So what I would suggest is we at least for this for the next reference system build, we keep it as is, and maybe in parallel, because this will probably take a little bit more time. And maybe in parallel, once the gradient coils are designed, and we can maybe see what can be done. But for this build, we probably just stick to the current specs.
Yeah, I think also maybe input from Baki would be much appreciated here. Ultimately.
What are the specs of your?
So this gradient amplifier has 24 volts plus minus and 10 amps because it uses the OPA 549 chips in there.
Yeah, that's also a good idea. Definitely. Yeah, we should give it a try.
Just to be sure that we're talking about the same. So the supply voltage is plus and minus 15 volts.
Yeah.
Okay.
Yeah, Baki, maybe because you have to build them, maybe.
My colleague couldn't attend here. He will mainly involved in this amplifier production. My idea also to keep this current situation. I mean, not to replace batteries. But we will discuss with him, and I will discuss with you.
Yeah, because I mean, some tiny modifications need to be done anyway, right? Like the filters need to be probably somewhere inside the casing, and maybe also some other the enable signal or the re-enabling digitally or something like that. I mean, there needs to be anyway some tiny modifications. And probably if it's safer that we have this we have this 3 stable amplifiers within this 1 year time frame that we have to actually build the whole system, this whole 3 systems. Probably it makes sense to just focus on these tiny modifications, but the main design, keep it as is.
But for the batteries, if you take like 2 12-volt batteries and make them like one for plus, one for minus, why don't you use like 4 and make plus minus 24 volts out of it? So this you can use batteries later too. It's just a little bit more batteries.
Yeah, just a bit more annoying.
But since there's no use case for the batteries intended right now, I think we should definitely drop that. That's my personal opinion on that.
Just go to a normal power supply.
Yes.
With the voltage you like.
Yes, maybe, I don't know if there's a DC-DC converter on the input stage, if that's something that would make sense for powering it with, I don't know, any type of wild generator or something, just to make it more stable. But other than that, I think it's a great design, but we don't need the battery option from my point of view.
I also just from an MDR perspective, is it something where it's easier to have the power supply integrated into the gradient amplifier? I mean, there's quite a lot of space inside of the casing at the moment. Obviously, the power supplies will be substantial.
We will need to change them.
Yeah, it's quite high power, and I think my feeling is that MDR would be happier if everything is sort of integrated into the enclosure rather than.
Yeah, I mean, at the moment we have a knob there, or we can change the voltage. I don't think they will like that.
These little things come into it. But Danny, you also have quite a lot of experience with MDR, right? You've had quite a lot of experience. Well, you've had some training for dealing with MDR.
By the way, this supply you can disable the knobs on the front, so you can just set the voltage and you cannot change it afterwards.
Maybe we can sit down and find some few minutes in a coffee break or so, and just to as we did yesterday, to fix the document for the gradient amp, and talk about this, and then
because the most easiest part is to put like switching mode power supply in the gradient amplifier, which has a voltage range for US market and European market, like 110 volts and 230 volts, and then just have a IEC plug for the device, because this is also international standard and you don't need to apply extra for US market and for European market.
So the first version had exactly that. It had power supplies built in, but they were obsolete after just half a year. And that was a bit annoying. Then I thought, okay, maybe to prevent that next time, keep the supply outside. And I thought maybe also for MDR, I don't know for sure. That's, because I can also imagine that all the safety, if that is handled in a proper power supply, and you only go with a low voltage to the gradient amp, that might also have advantages.
Yeah, I think maybe let's, in the interest of time, and
I think because the next talk is Ruben, who's doing it online, and I know that he has later on another talk. So,
hello, can you hear me? Good morning.
Hello. Yeah, screen is free again.
Hello.
Welcome, Ruben.
Good morning.
Thank you for coming.
Pleasure. It's a pity I couldn't make it in person, but it's great you enabled this option. Can you hear me?
Yep, perfectly well.
Yep. Cool. Awesome. So good morning, everyone. I'm here to present a work that is not mine. It's from Dinh de Gans. But I think it's good to give the view from the side of a rebuilder, because we reproduced it, and I think it always brings a different perspective, and hopefully it's enriching. Let me share my screen. Can you see my screen?
Not yet.
Not yet. Let me see what's this. Entire screen. Built-in display. Share.
Oh, now it's loading.
Yeah. That's
you got it.
Yes. Cool. There we go. So this part of the workshop will be about the radio frequency power amplifier. And then here I just wanted to highlight who was the real worker and the mind behind that is Dinh de Gans from TU Delft, that you have in the room. Unfortunately, I won't be able to meet him today, but next time. And myself, I'm Ruben, and I did this reproduction of the power amplifier at the PTB. Now I'm based in San Sebastian, in the north of Spain. First, where can you find the info to reproduce this work? Here you have the link, and it's in GitLab. And you will see there are quite different folders, because even if it's a single instrument, it has substantially different parts to it. That are the PCB, more the electronics, and also some mechanical components, like enclosure, and for the capacitors. You will find all this information in this GitLab. And it's good that, for example, we did reproduce it, let's say, on the distance, remotely, because that made kind of a proof of, it guarantees that it's possible, all the information is there to be reproduced. And there were some back and forth at the time of reproducing of bits that were missing. But I think quite most of that information is in these folders now, in small text or README files. To make sure we have the working principle clear, but I think you will understand quite a bit of electronics and this component. In this case, we are amplifying radio frequency signals. They are AC signals. It won't work for gradients, and are pseudo DC signals. And it also has an enable, and the enable is important because it quiets down the noise. On one hand, it also saves power. So we need these two inputs: an analog input that is going to be a radio frequency input. Let's see if I can bring up the pointer. This bit here, and then we need a TTL signal that it should be from 1.5 volts to 5 volts to make it work, to make whatever we are bringing it through the radio frequency path be amplified with quite a lot of power, because this is something, it's a monster. It's 1 kilowatt power amplifier. I think you can make a whole body system with this guy. Okay. See if now we go to the construction. See if I skipped something. Sorry. No, good. Here I divided the components through a logic of they come together to when we are building them, and also the folders that are defined to find the information are more or less in the same order. So we have the PCBs, and in the PCBs we have mainly one, that it is this green guy. It is easy to solder on top of it. You don't need any very special soldering station with quite a thin tip. It's all doable. And then there is another PCB that is, we will call it PCB, but it's very simple. It's just this PCB on top and this PCB on the bottom. They can be handmade as well, but when you are sending to print the other PCB, the big one, is good to get this one done as well. And this is for a transformer. These PCBs, they help with the construction of a transformer. Oh, sorry about that. Press the wrong button. I used quite a high quality pictures, and now I'm paying for it. There we go. Here we are. Then we go to the heatsink. The heatsink goes behind the big PCB, and its purpose is just to dissipate the heat, because this is a powerful amplifier, and you see it's quite a big fellow. It is this guy here, and it's not a simple heatsink. It is a simple, but it needs some work on it. It needs some holes to be able to connect the PCB and some of the chips, so it dissipates properly. So we will go through that as well. Then there is a transformer. We need to work on raising up the voltages, and for that it's quite a crafting opportunity to put together some good knowledge on radio frequency. And then we have the capacitor bank. And basically it is because although it is a 1 kilowatt system, it doesn't drink 1 kilowatt all the time, and it mainly takes advantage of that this power is needed in short periods, short pulses. And this is very important to remember. So if we will be driving this in continuous wave, it won't work. And thanks to the capacitor bank, we can store the energy and ask it in very short pulses and time. Short times of microseconds, and we don't need a lot of energy to be taken all the time from the grid. And then the enclosure, that it is also an important part. It also takes quite some work to put all the peripheries and interfaces on it. The first thing we will need to do once we know that we want to do it is to buy the stuff. And here I made a short list, and we have 2 boom lists that we will find in the GitLab. And then apart from that, we have to remember, we have to order the PCBs, and we have to get the holders for the capacitors. They can be 3D printed. That was our option. They could be also CNC machined, and very kindly, we have been provided with both CAD files for 3D printing or the files for machining, for the information for do it with a CNC machine. And for the CNC machine as well, we will, perhaps CNC, perhaps other methods, we can cut the copper plates we have seen in the previous image for the capacitors. And then, of course, cables. Cables are not included in the boom list, remember that. Otherwise, you will get a surprise at the end. But they are, in general, they are quite common cables. Some of them for the monitoring parts, they have multiple cables that you may need to buy them. And I'm not sure of the budget anymore. It has quite a price, and because the prices have changed quite a bit since we built it. But we can update on this later if maybe someone knows the current price for the components, but that's about what it will take. Let's go with the PCBs. For building the PCBs, you see it's quite straightforward. It's pretty much one side of the PCB that has to be built. And here we have been provided with schematics to understand the function of each part, but it can be assembled quite quickly. Then there are other components that they need some crafting. And for example, that is, this is a thick copper stripe, and then the capacitor. The capacitor, the transformer. That's also a PCB base, but we will talk about that later. Other than that, here you can see that the power transistor is engraved in a hole through the PCB and is touching directly the heatsink. And there you need a bit of crafting as well. For these little copper legs, nothing difficult. It's just a bit of time and enjoying as you go. The transformer, it is to continue the old good knowledge of making radio frequency transistors. It's based on ferrites, and then you just need to put a wire through. You solder a copper plane through the ferrites on top of the PCBs, and then you are good to go. It's important the direction and the number of turns, and we have been provided with a file. You can see here a picture of the PDF that Dinh has prepared with different of the systems of these parts, how they have to be, how many turns they have, and how they have to be connected. In this case, for example, before I mentioned the copper stripe, is this little light here, and then you have 2 other transformers or ferrite-based constructions with different numbers, and they refer different number of loops. They refer to this guy on top and this guy on the bottom. And I found very useful this PDF for sure to know how many loops, to make sure I got the concepts right. But looking at the pictures together with the files and PDFs and datasheets, there is a generous dose of pictures from the construction, the original construction from Dinh. And looking at those pictures, you can also see how the direction of the wire goes, in which end of the ferrite the cables have to come up. And I think it's a very good complementary information. From the transformer, we go to the heatsink. As I mentioned before, it is a commercial heatsink, but then you have to make some holes. Here is those are some small tubes on top of the holes, but you have to make the holes. You can either send them to be drilled on a CNC machine, for example, but they have to be threaded. So that I know the CNC machines I have access to, they don't thread. We did everything by hand, also the holes. And to make the holes by hand, we are also provided with a PDF with the distances of the holes here. We have all the different holes, and there are, I think I remember, two different sizes, maybe perhaps three, but mainly two, M4 and M5 thread dimensions. And we did it by hand with a ruler, put them in the right place, make the hole, and everything fell in place nicely. It was nothing complex. We also need to make some holes on the sides, but also the same, nothing difficult. Moving forward to the capacitors, the capacitor bank. This is, they are very big guys, and they have to be held in place because they have quite a risk on them. And these copper plates that you see here, they are important. At the beginning, we didn't have the time to get them manufactured, to get them machined, and I substituted the plates with some thick wires, like pretty thick wires. I don't know if it was 6 millimeters cross-section diameter. But like I thought that these are generous, but they were actually limiting the performance of the amplifier because the energy could not get retrieved as quickly as it should. So get these capacitors, get these copper plates on top. They are important. You could, like in our case, we were rushing to see if it will work, substitute it with cables, but at the end you will need the plates. And here you see the plates. You get a file with the dimensions and also I think a file for the machining. And for the capacitors, as I mentioned before, you get the 3D printed CAD files and 3D printed CAD files for 3D printing or for machining with other techniques like CNC. If we go with the capacitors, remember that you shouldn't touch them recently after turning on the power amplifier, and actually you should only touch them when you have discharged them. That can be done with a resistor, a kind of a power resistor, and short circuiting the both poles of the capacitor, because you can get a very decent shock with them. And the last bit is the enclosure, and last but not least important. And actually, something that surprised me how expensive the enclosures are. One would think it's just aluminum parts brought together, but I think they may have taken 20%, 25%, or maybe or something like that of the whole price of the amplifier. I think it was 300 euros if I get it, if I remember it right. And the enclosure, you have two parts that have to be tailored: the front and the back. And it is because you have to carve the holes for the different LEDs and different peripherals. And in order to do that, you are provided with some files that are proprietary software. It's for free. You can download it for free, and it's from a company that does the paneling for you, does the cutting on the panels for you. That's an option. That's what Dinh did, and you could also use that software to transform that to another format, and then do it with a CNC or with another provider. There you are not forced to use the same company, but originally the files are directing you to do it with that company. And now we have everything together, and I wanted to reproduce with some images something that is very well described on a PDF. Dinh has prepared a kind of a way to start testing the proper working of the PCB. And when we are going to do that, we always start with as little power as possible. But first we have to get the voltages right. The first thing that we have to do is to go for this component that we see on the image, and with these two potentiometers, adjust the voltages. We have 8 volts, minus 5 volts, and plus 5 volts. If I remember it right, the 5 volts is fixed, that's guaranteed, and then the 2 potentiometers are for the 8 volts and 2 for the minus 5 volts. And that you do it by adjusting and measuring on the outputs that you get the voltage you want. After doing that, the next second thing to adjust is the power supply. And this is another power supply. This is a power supply. This is a big guy. And we set it to the minimum voltage. It's about 30 volts. After this, we test that we first connect something at the output of the amplifier. That's important. It has to be, this is not that common to have. It has to be a load that can handle quite many watts. If you have something that it is 1 kilowatt, fantastic, because it's something we will need to test at the end, that the power amplifier keeps working up to that power because it's designed to go to that power. So it has to be, if you have a load of 50 ohms impedance up to 1 kilowatt power. After that, the first thing we are going to do is to do the first power on. And to that, we first connect this P1 connector. And then we should see that in this LED, the system is telling us that the voltage is not right. That is because this system is monitoring that the voltage is what it's supposed to be, and if it is not, which I will explain later that it happened to us, and it's likely to happen to many people, then you will have this alert, this LED telling you, oh, something is going on, that it cannot hold the DC voltage, that it should be 56 volts. In this case, it's telling you it doesn't have the right voltage because we have adjusted it to the minimum voltage, the 30 volts. So everything is as it should be. Then we go and increase the voltage a little bit more, the same way we did it. It was in the minimum, now we bring it a bit higher. And we should see it on this indicator. This indicator is basically reflecting the voltage that we are adjusting here. After this, we start biasing the transistors. Or in this case, I think it's some op-amps that have to be adjusted. The thing is that they need a bias voltage, and that is adjustable. And the voltage can be adjusted with these two capacitors. We have, in this case, it's a push-pull configuration, so we have two big transistors that are driven independently. So we have to adjust the bias for both the legs. And when we are adjusting it, we can measure on this R14 and R17 the voltage we are getting. And we were recommended to have 2 volts on those resistors. After that, it's time to turn it on. So we press the button. It's an exciting moment. And once we have turned it on, we start testing. We will start introducing an RF signal. So remember, this is a small signal that we have to amplify. A small signal in this case is recommended to be pretty small, and a frequency that we know that the amplifier is in working regime of the amplifier, because this amplifier, if we go for 100 kilohertz, for example, I think it wouldn't work well. So it has to be 1 megahertz, 4 megahertz. It does an excellent job, but don't go too low and don't go too high on the frequency. Sorry about that. The next thing to do is, once we have the small signal, that was a continuous wave. I forgot saying, you just generate a small sinusoidal signal. It's the time to pulse it. This is a very important moment, because pulsing it means really turning on and off in a short time. Otherwise, the amplifier will stop working because, as we said, it will drain too much power from the grid, and it's designed to work with for a limited time from the capacitors. And yeah, this is what I was mentioning about. And if we go for long continuous wave pulses, long pulses, or continuous wave conditions, it will drop the voltage and the system will stop working, and we will see it on this LED, the one here. Okay. After we have tested that we get something at the output when we are pulsing, it's time to bring it to the final working conditions, that it is power, rising up the voltages. In this case, it's an intermediate state. We are not gonna go full gas. And what we do, we put the power supply to the final voltage, that is 46 volts, is all it can give, this little guy. And we do it again where I did the arrow, there's a screw, and we bring it up. We should see the indicator as it's in the picture, and we should see that this LED, monitoring LED, is not giving light. So now everything is telling you its system is ready to work. The bias voltage of the potentiometers that we set before to 2 volts, now we are going to bring them up a little bit more. That means this capacity, these potentiometers, we have to adjust and check here that we have more or less 2.5 volts in both of them. Once we get this, it's time to do some testing with this more power. And in this case, we are introducing already a bigger signal. And we introduce higher voltage AC signal, and then we should see this. And there is a question mark here because if you don't see it, it's time to double check some things. And finally, it's time to test how high it can go. And you can also test the linearity. Generally, it has a fairly good linearity. As you go with higher amplitudes at the input, it generally maintains a constant gain with respect to the output. And here we have some reference that it is, we should see this 632 volts peak to peak. That's a lot, watch out. And the input signal at that time, this maximum input signal is in the system of Dinh, and also in the system that we reproduce from Dinh. It's more or less around 1 volt peak to peak, the input signal, is a signal that we are introducing. And then you will see whether the signal looks distorted or not. When you see distortions, those potentiometers that we have been adjusting here, we are setting them to 2.7 volts. What is happening there is that we are adjusting the bias because we have a transistor that has to kick in and the other transistor has to stop working. And we have to kind of bring them to the sweet spot where one stops while the other one starts, and the wave respects the shape. And that was the talk. And that was, I don't know if I respect the time. I didn't track it, sorry, but now it's time to discuss. And luckily we have Dinh in the room, so probably I will bounce all the questions to him. Thank you for your attention, and special thanks to Dinh.
Thank you, Dinh. Are there any questions in the room? Oh, sorry, Ruben. So many names. Yep.
So I got 2 points. First of all, I saw that your enable also works with from 1.5 volts, right? So this amplifier also should cover low voltage TTL, right? With the 3.3 volts, which is like very important because the TX gate or the blanking signal comes from mainly when we use the red Pitaya from the GPIO pins, which are CMOS, so 3.3 volts. This is very nice. And the second is what I saw in your building is like you have a lot of custom parts, like the transformer. Is it possible to use other standard parts for it, or is this a part that needs to be like specially built for this amplifier?
That's a good question. Danny, yes, please.
Yeah. So the reason for that is a custom-made transformer because I couldn't find any that fits my purpose. So, but I know that assembly of it, especially with the transformer that is on top, the common mode transformer, is a bit hard to assemble because it is made with a ribbon cable. And what you need to do is get every other wire connected to each other and then go through. And that is, I think, the most difficult thing because you can make a mistake. And if you do reversed, it's not working properly. So we have been thinking of maybe doing it differently. And the ribbon cable normally has a special connector that goes on it, that you just crimp on it. So maybe there's a way if you can just shift it one pin and connect it to the other side, something like that, or maybe reverse it. I don't know yet, but that was something we were thinking about but never implemented.
But there are no standard parts like in the range.
No, so I really had to look hard for the type of ferrite. So this core that was used is the only one that I could find that is good enough. Especially since there are lots, there's a high current going through, which makes a high field. But also within the frequency range, it needs to be able to operate there. And that's more difficult for lower frequencies, because then it will saturate more easily. And this core is the only one I could find that can handle that. And if you just buy an off-the-shelf transformer, usually these types of numbers are not specified. You don't know for sure which material they use in their transformer. And so therefore I couldn't take that gamble.
So I have a couple of questions. And again, unfortunately, Ruben, I really appreciate your presentation. And I think for the workshop, it's perfect. But the question will be aimed mainly towards Danny.
You did well, Ruben.
Of course.
So sort of in line with the question of Marcus and sort of your answer to Marcus. The power is overkill for, as it turns out, the power is overkill. I think you're well aware of this, and we've had some projects to try and sort of come up with a different design. But I think this one has so far been the most reliable design in terms of various performance parameters. So you mentioned that the current is an issue, but if we say, hey, instead of a 1 kilowatt hour of amplifier actually turns out 100 watts is sufficient, does that make the purchasing of components and the selection of components easier?
Yeah, you would really simplify the amplifier. So for example, you wouldn't have the necessity for the difficult transformer anymore. Then you might be able to use it just off the shelf transformer. 100 watts to a kilowatt is really a game changer.
Yeah.
So that would simplify the amplifier a lot.
Yeah. And would that be a significant redesign if we say, hey, we keep the gain the same, we keep everything the same?
So you don't want to keep the gain the same. You really want to lower it because you only want to get to 100 watts. So you have the same input signal and you have to amplify it to a less amplitude.
Yeah.
So and that also has the advantage that more gain at the output of the amplifier, there's an amount of noise that depends. Usually it's calculated from the input of the amplifier. Input noise is usually the same, more or less.
Sure.
Nanavolt or something. So if you have a lot of gain that you don't use, then all that noise is injected into your MRI scanner and you don't need it.
But sort of the question was more in the interest of time in the project where we have to have finished the system in sort of a year, redesign as little as possible.
Yeah.
Does that make sense to...
So again here, so the whole gain depends on the feedback network.
Yeah.
So just change the resistors and you get less gain.
Okay.
But that would leave you with a more complex transformer still, because if you don't want to change that, but you can reduce the gain just by choosing other resistor.
I thought Dutch people are more direct. I will reframe the question Tom actually is asking. So Danny, how much time would you need to redesign it? And are you willing to do that?
So now is 2023. So 5 years. No. Yeah. A few months. Yeah, but if I continue on what's already there, so I don't have to start from scratch, and it's true. But, just like getting more current of the gradient amplifier, it's easier said than done. So you just change the resistor, but there are also other consequences. But in this case, we're going down in power, so that probably less a problem.
Then so, and if you even have support from Turkey that can help you in the process, it probably is even less time, right?
So for Danny, just to update you, in Turkey, they're going to be, as part of this open source project that we've been awarded, Turkey will be rebuilding and characterizing a lot of the electronics. So I don't know if you knew that, so that helps with this. Yeah.
So Danny, thanks a lot. I mean, we'll contact you a lot. I mean, we will come.
Okay,
and, yeah.
But this would be really cool because I mean we can also just rebuild this one here, but I think just the noise it makes when you turn it on.
This was my next question. Did you ever measure the noise output of the amplifier?
No.
I mean noise, acoustic noise. I mean acoustic noise. You mean
electrical noise?
Yeah. Okay, yeah. There's both two issues. So the one was built in Spain, Valencia, I think. And this guy found a new fan. I don't know if, probably I know the type somewhere. Maybe he said it in an email, but that fan was already a lot quieter. This fan.
Was that you?
That was really. Oh yeah, that's okay. No. So we were emailing then. Okay. Yeah. But that fan was already a lot quieter, right? That fan that you used was already quieter. Or not? Not so much. Okay. But no, sorry. So there's a lot of noise coming, loudness from the fan, the cooling fan. And I thought you found another type that was. Oh, still. Okay. Yeah. But it is designed for the full power. So depending on the maximum time you can have the amplifier on, you get lots of dissipation. And that is what the heatsink is designed for. And it's always cooling that capacity. But if you're going way below that, so maybe you could do the fan dynamically, that only if the heatsink heats up a lot, that it is switched on or so, or throttled or something like that. It already reduces the noise a lot, probably.
But the electrical noise?
Yeah, so I didn't do a measurement on that. But, and also, I found that now, it's the idea I had. I don't know if it's really true, but I think that noise from the amplifier is most important when you are listening. So when you're receiving the signal, and then there needs to be no noise. Exactly. And what I do to do that is amplifier, if you don't put any signal in, is still producing noise. So I completely shut down the supply voltage of my all the output amplifier. So it's not noisy because there's no power.
But did you enable because this goes with the blanking, right?
Yeah.
You got the blanking signal for transmit.
Yeah.
And then you switch off completely the power supply.
Ruben, if maybe you can show the diagram with the colored sections.
Sorry, I will try to find the schematic because I cannot zoom in the diagram.
Okay. Yeah, exactly. But then you still have noise. Yeah, and so I just removed the whole power supply. Yeah. So that's nanosecond work. Yeah. There's a plot that Ruben also showed.
Can you see the screen?
No.
Can you see the screen?
Not
No?
yet.
No. Ah, yes, low. Yeah.
Now it's loading. Yeah, we get it.
Yeah. So it's
Oh,
this
yeah,
guy,
this is fine
right?
as well. This is the whole diagram, right? So in the top left here, so there's this differential stage there, yeah. And the MOSFET on the right, I can see the molecule that, yeah, to the bottom a bit, below. There, that MOSFET on the right. That's too much, no, sorry. So this is that MOSFET. That is clamping, just switching the supply voltage to ground. And therefore, and that is the biasing strip that is drawn there, it is just at 0 volt. There's no supply at all. And there's no way of leaking any noise from the power supply or active components to the output. And that is done by fast switching by that MOSFET over there. And if it switches on, then there's the differential stage that's there, acts as a supply regulator, so it's more or less a linear regulator. And as the large capacitors drain, the voltage is kept constant at that output. So you don't get any droop in the gain.
This has all been measured.
And one other remark. So you mentioned that the supply voltage can be regulated. Just leave it on the space, please. So you can regulate the supply voltage a bit with the resistors, right, with the primers. And on the bottom of this page, there's a remark there. And it says what the supply voltage should be. It's not -5, as I remember.
Yeah.
Yeah.
Yeah. This comment here.
Yeah. -4. Yeah, that's it. Yeah.
All right. Lucas, I think we have a problem. You put -5 on yours.
It's because of the limited supply voltage for that op-amp. No. Maybe you also showed a scope image where the pulse, the RF pulse, is enabled and then switched off.
Yeah.
This one.
This one, right?
Right. Yeah. So here at startup, you can see if it's coming up, it's controlled, and then switching off immediate. And you can see the green line is the measured AC, probably. The supply voltage. So there's a little bit of ringing and it's completely damped. That's also in the circuit. So it doesn't keep on ringing afterwards. It's also noise that it could inject maybe in the measurement. And so yellow is the RF. It's just completely gone immediately. And yeah, so that's it.
So I had an architectural question. So this has got a 60-volt power supply inside. We have so AC to DC power supply. The gradient amplifier will have 2 AC to DC power supplies. Is there any, especially if we drop the power on the gradient on the RF amplifier and increase the power on the gradient amplifier, does it make sense at some point to go to one set of AC to DC power supplies for the entire system, especially if we also have the spectrometer on a voltage that could sort of handle within an acceptable voltage range? Does that make sense to do that?
Have a single type of power supply, but maybe not connect them to each other.
You would keep them separate.
I would like that, yeah. Because otherwise,
the only disadvantage is that we lose a bit this modularity approach.
Yeah, but perhaps gain in efficiency and cost, right?
Yeah, reducing the bill of
the
materials.
power supplies are quite expensive.
Yeah, also, yeah.
Shouldn't
and if
be
you
more.
need less power, then they become cheaper, probably.
Yeah. That's also true. Yeah.
Jacks into panels, and then you have like one
That's kind of how it is now.
That's what we have here.
Yeah.
except not with the banana. leaves, but,
About
no.
the power supply, I would have a suggestion from France. There is OwnTech developing some open source DC-DC converters that are galvanic isolated, for example, and might be useful for that case. Each part can handle over a kilowatt and is in a Eurorack format. So it should be quite easy to implement it as a modular system. We could simply take a look at the website quickly. If you go for OwnTech.
I think, again, in the interest of time, these detailed discussions maybe we should do afterwards, but I think it's a very cool suggestion.
Yes, go for it. .org, I guess. There we are. Under technologies, Twist, I think, is the name.
Next talk is going to be on the gradient coils. The stage is yours.
So, yeah, thank you guys so much for even after still or after 2 really busy days, it's still quite fun to be with you guys. So yeah, I was asked. It's still really fun to be with you guys. I really enjoy. I was asked to talk about gradient coils, and yeah, I'll give a quick overview of gradient coils in general, talk a bit more about gradient coil design, and already give a glimpse into gradient coil manufacturing, even though Wouter is going into more detail on that later on.
Online cannot see the screen. That's my bad. Yeah. And then... Yep.
Okay. So I'll start off with gradient coils in general, a bit more about gradient coil design and about an open design tool, and then a bit more on gradient coil manufacturing, and you'll hear more from Wouter then later on. So to gradient coils, what are gradient coils? I would like to start out for people that are not so familiar with MRI, what is actually necessary that we get an NMR signal. So of course we need a sample, which is our signal source. So in low field, it's usually 1H if people don't do hyperpolarization or any crazy stuff. We need a magnet for our polarization, and this is usually in the, it's a static field in the millitesla or Tesla regime. And we need an RF coil for excitation and an RF coil to do the acquisition, so to receive our signal. Usually there are also some shims involved to shim out inhomogeneities of the magnet or of the stuff that is brought into the magnet, but this is usually not an issue at low field. And with this, we basically have an NMR spectrometer, so we can detect a signal from our signal source. And what I'm going to talk about are the gradient coils. That's an additional set of coils which is used for signal localization. Shown here is like a sketch of a coil setup which is used in superconductive systems. And the gradients are like the main key that enable for imaging. So it's really what makes NMR, what makes an MRI out of our NMR system. And like in research, we go up to like, or even a bit higher than 300 millitesla per meter. So that's quite strong. And usually there is a switching frequency involved to that, which is in the order of like 5 kilohertz. So what does that mean, a gradient field? So we're talking about a spatial variation or a variation of the magnetic field in space, which is overlaid with our B0 field. And because we just alter the strength of our B0 field, we usually just care about the Z component, so the magnetic field component along the main magnetic field. And with this, we induce a local variation of the Lamont frequency, and then we get a linear relation between our object and frequency space. And this is what then enables us to excite a homogeneous slice profile if we play out a frequency selective excitation pulse. And it's also in imaging what enables us to use a Fourier transform. Because we live in a three-dimensional space, we usually use 3 orthogonal gradients to encode our 3 spatial dimensions. And of course, our gradient field does not stop just at a really constant strong term, but it extends beyond the main imaging region. So we've already heard in the magnet design this morning, they were talking about ppm, so parts per million. So really, really accurate. And just to give you an idea, when we talk about gradients, we usually don't care so much about accuracy. And this was just an image acquired, I'm sorry, not at low field, just at a usual clinical scanner. And if we acquire a large field of view, just crank this up a bit, we see that some parts in the corners, someone went there and cut them off. No, of course not. It's distortions, and the distortion correction is active. And if we switch off the distortion correction, we see that our image is distorted at the edges. And if we move away from the isocenter, we even have more distortion. And usually we are talking about multiple percent, like 5 to 10 or even 15% of deviation from the optimal field. So for these fields, for the gradient fields, we are not in the ppm regime compared to the main magnetic field. And like the main message I want to I want to give you here is that all gradient fields are non-constant to some degree. In gradient coils, what we want is usually the gradient area, so the gradient or the area under the curve in this pulse diagram. So on the x-axis we have the time, and on the y-axis the amplitude. And what we are usually interested in is the gradient moment, so the area under this curve. Because this relates to the accumulated phase, so the phase we induce while switching, and this depends on the gradient amplitude shown as g here, and as the time. And it also relates to the spatial resolution, which also is the gradient strength times the time. So the gradient moment is what we really care about. And usually we want to have a high gradient amplitude, so a high maximum value, but we also want fast switching. And for high gradient amplitude, we can either have more windings on our coil if we have more space, which is in our case a lot of times the restriction, or we need higher current. That was the discussion we already had earlier. This is where our amplifier limits us. The other end is the switching, that we want fast switching, and for that we have to overcome the inductance, the inductive load of our coil. So we need a higher voltage. And in coil design, there's usually a trade-off between efficiency and slew rate. So that was like the discussion going on about the amplifier earlier. So to gradient coil design, I thought just after lunch I have to show some formulas to get you guys awake. No, I'm just kidding. The gradient coil design is usually done with the so-called boundary element method, and what we want to do is we want to optimize a surface current density, and usually we don't do that directly because we want to later on transform that into a realizable design. And for that, we are not optimizing the surface current density, but we are calculating or optimizing the so-called stream function. So if you integrate the stream function, you get your current density. So the rotation here of your stream function is your surface current density. And of course, we can express this somehow, that we get a sensitivity matrix, and this sensitivity matrix now relates each point on our or each minimum node here to a associated magnetic field. And with this, we can now set up an optimization function that we want to minimize. So basically, we have a target field, and if we subtract the field that we generate from our stream function with a target, we basically should get 0. And we usually have some other terms here that we want to optimize something else. For example, we want to reduce the power or the inductance of our coil, and these are regularizers. And these are like the points, the knobs where we can optimize or where we can actually change something in our design. We've implemented, so there are few openly available software repositories. I hope I didn't forget any. And the thing I'm mainly talking about here is CoilGen. So how can you do a coil design? You have to define, as always in life, you have to know what you want. You have to define your basic properties, which is the current carrying surface, where your currents can be or where your stream function is optimized. So you have to define a size, shape, and resolution. And you need to have a target, what you want to optimize for. It's not only the type of field, but it's also the size and the shape and the resolution. And this may not only be on the main, as a main target, you might have like secondary targets for a shielded gradient coil or so. And what's really important is the main field direction, because as I said earlier, we care about the Z component, the component which is the same direction as our main B0 field. And there might be additional constraints like torque balance, force balance, or anything else. And the open source software I'm talking about here, CoilGen, is a flexible design tool which has all of this integrated here. And just a quick idea about the boundary element method again. So CoilGen allows you to generate a triangular surface mesh, or you can also input an arbitrary surface mesh, also any crazy shape, not only like a cylinder. And the stream function is then optimized on boundary elements. So we have a triangular mesh, and we basically describe the currents which flow around one node here, which is shown in one color. And this is like the basic optimization, and this is how we solve our problem here. And in CoilGen,
a quick question on that. So the tool allows you to read in an STL file, and then an STL file itself is a triangular mesh.
Yes.
When you load in an STL file, is that triangular mesh, is that directly what is then used in the boundary element method, or is that reinterpreted?
No, it's directly used. So what we've been done was using, for example, also Blender to generate a arbitrary surface mesh, or also in the beginning there was no mesh generation in CoilGen. So usually we use like a mesh generated in some other place or from some other CAD software.
So then the resolution of the STL mesh matters.
Exactly.
Okay.
Exactly. And what you then get here is an interconnected coil design, and you have some post-processing options to really not only get ISO contours of your stream function, which approximate the surface current density that you want, so a coil design, but you can also get interconnections of your coils that you really get a windable current or wire path that generates the field you actually want. Okay, so how does that actually look like in CoilGen? I'm just showing some pictures here. I'm not really going into the code, but you can download the code on GitHub. And this is basically, if you run the example, something pretty similar to what you get. So initially, you give in a target field and your mesh. And if you do an optimization, you get your stream function. And this basically represents what I've shown before, or is correlated to the surface current density. And what you have, or what you can tune here, is your regularization parameter. So your regularization parameter is basically a trade-off between efficiency and accuracy. The problem is, if we state this problem here, it's an ill-determined problem. So we have not the same number of equations which are defined. So it's either an over or an underdetermined problem. And usually there are infinitely many solutions, and we want to find solutions that are not wasting too much energy. Let's put it in that way. And with this regularization parameter, there's no like perfect way of finding one. It really depends on the way how you state your problem. So usually what you have to do is to optimize a few designs and play around with your regularization parameter and get an optimal solution, which is efficient, but also where the deviation is not too large. So in CoilGen, this solution, this stream function is then projected onto a 2D surface and discretized, because this is now the way how we generate our field with a discrete design that we find our equally spaced isocontours, and for interconnecting them, it's projected onto a 2D surface. And then in the next step, there's a topological analysis, and a path where the interconnections could be made is determined. This can also be done manually, but if you just run the examples, this is basically done automatically. And then interconnections are made within groups and among groups, to really get a design that can be wound with one single piece of wire. For really implementing that, it's then projected back into a 3D object, and you can see here that there are return paths which are just going on a different surface away from the main surface here. For like a Halbach type magnet, as we've one sitting here, the designs look similar to that. And so these are basically just the discretized stream functions. And these are the interconnected designs. And this is basically what you get from the examples of CoilGen, which are on GitHub. Just one word to GitHub. It was not me doing the implementation here, but a student in our lab. And he really did a pretty cool work. So he's just writing together his PhD thesis, and I'm quite proud of the work he has done here. Of course, you can then go ahead and implement your design. And 3D printed. We ourselves, we haven't implemented a low field design ourselves, but helped others for generating designs. And this is just one example which has been printed by Niels, who is also sitting here in Dortmund. So I already talked about implementation. Because the question came earlier, or maybe I'll talk about that later. Let's dive into gradient coil manufacturing. So how can you actually get get your design implemented? So how can you design and how can you realize your complex wire path? One possibility is to use printed circuit boards, PCBs, and another one is to wind your coil on a 3D printed or milled carrier. There are also other approaches, but most of them require some more advanced manufacturing techniques. So they are being used by major vendors, major manufacturers, but I'm not going to talk about these today. So for printed circuit boards, PCBs are just quite established, so you can just send off your design and a few weeks later you get back a high quality design. It's quite simple to work with it, it's cheap and precise. The main drawback is here that for larger coils, the cross-section is quite limiting the current we can actually give into. One of the first open source tabletop systems was built at MGH, and we were also involved my colleagues were also involved in the design here. In the center, you see design of the Okra gradients. So the hardware is also the control hardware, and the other stuff. Also, the implementation of this gradient system was done by Markus. And another example is like a specialized, dedicated design that we've done together with a group from Munich for nitrogen vacancy diamond NMR experiments. So yeah, if you have your design here, you basically just have to define the width of your wire tracks, put this into your favorite software for generating PCBs, make your Gerber files, send them out, and basically you are done. The next are 3D printed carrier structures. And what we have been doing in the past few years was using a powder bed inkjet head 3D printer, which uses some type of gypsum. So this works quite well because you basically have, if you infuse it with epoxy, some type of artificial stone. The big drawback here is that the materials are quite expensive. The build chamber is quite limited. Yeah, the machine does not really work so reliable, and you have to have quite a thick structure. Otherwise, you just don't get it out of the printer. What I really can recommend for implementing coils are Litz wires for using a 3D printed carrier. I also brought 2 samples which are laying down there. So if you want to take this in your hand, you're welcome to. You can also pass them around if you want. Because with Litz wire, this is quite easy to handle for a design. Because it's quite flexible and doesn't like snap out of your gradient coil compared to a solid wire. And what we usually do is use some vacuum infusion with epoxy resin to just keep the stuff in place. During the workshop or during the past 2 days, I had a couple of times the question, how do you get a 3D object out of your path? And what worked for us the best so far, or quite reliable, was using Blender. Blender is also an open source software where you can input your wire track and from that generate a 3D object, and then use another CAD software to basically subtract from a solid your optimized wire path. So some manufacturing take-home messages from my personal experience. For me, building hardware was always really, really fun and rewarding. On the other hand, it was also always quite tedious and exhausting. So if you implement something, plan for a first try. Use established connectors, methods and stuff if you find something documented or see how others do it. However, also question established practices, because not everything people do always makes sense. Check and double check for ferromagnetic parts. This is also important for low field, but it's even more important for higher fields. And try to measure before casting because debugging in hardware is always a bit more tedious than software. Yeah, someone knows what I'm talking about. And especially if you cast a coil, basically there is no way of return. You just have to rebuild it. As a quick summary, so gradients are like the main ingredient which make an MRI out of an NMR spectrometer. All gradients are non-constant to some degree, so the stream function is a good way to approximate your surface current density to do your optimization. In most of the stream function methods, boundary element methods are used. And with CoilGen, there's an established pipeline for open source pipeline for coil design, and we're currently, I'm actually not that much involved in that, but there's currently some active work going on to translate CoilGen into Python, that it's not stuck. That it's not stuck in MATLAB. For your coil design, there's usually some post-processing necessary, but there's also a lot already being done in CoilGen. And there is a variety of methods to manufacture and implement your gradient coil. So with this, I'd like to thank especially Philip, who's all the way on the right up there because he actually wrote CoilGen. Of course, funding, which just started. And if you want some further reading on gradient coils, I would just point you to these two papers, which give a quite good overview about the theory and like current implementations. Thank you.
I have a question. On your gradient PCB, there was a hole in the center, probably a via. Do you need to process that to make it capable of running the high current?
So usually it's not only one via, it's multiple vias to really get the sufficient cross section. So one via is definitely not enough there. So you need multiple.
Maybe you add some solder tin in it or so.
That might be one idea to do that. Yes, the idea was here that the space on PCBs is also quite limited. So usually for small gradient coils, you want more turns. And for getting more turns, it totally makes sense that you have, you cannot see it in all of the designs here, but for the X, you can see that the same spiral which is going in is going out on the other side. So you have like twice the turns and get like double the inductance, and you have to have like a second surface for your return paths anyway. So it totally makes sense to use this.
I would ask how difficult it is to connect the Litz wire to the connector.
So we have some RF Litz wire where the insulation can be burned off with solder. And what I've used so far was always like we have like a really old solder bath. It's like it looks like a soldering iron, but there's like a small bath on top. Or on the front. You should not tip it over, otherwise your solder is gone. It takes quite some time to heat up, and you should use it under a fume hood. But with this, I'm basically just stretching out the individual wires and can just get tin to all of them at the same time. However, if you take or if you feed your cables out, through the soldering, this is actually a built-in fuse. So it's like a safety feature. So your coil burns there. I found that out.
I got a question. It's maybe not that important for the Hallbach magnet because it don't got shielding coils, how I understand it, right? But the shielding coils, you calculate that there's to the outside, we want to avoid eddy currents, right? So is this also the mesh that you use there? Is this also a 2D surface for the 0 point? Or because we have these pole shoes in the tabletop, and they are made from 1 centimeter of steel, right? And if you just use the surface, I imagine in the steel further, then the field goes negative and also adds eddy currents, right?
So we can definitely talk about a contract for giving you some advice on like for conventional superconductive magnets, you usually care about the coldest cryo shield. That's like the surface that you define. However, most manufacturers do a way more detailed analysis later on to really not only look at the field which is generated inside, but usually it's a combination of the field which is generated inside the cryostat and from the main field to see what's going on there. It's a 2D surface, yeah.
Does the CoilGen tool, is there anything, let's say hypothetically, we would want to create second order, third order shims or a 0th order shim for field stability? Is that something that, I assume it's something CoilGen can handle, and is there anything that should be considered in that case from your experience?
So in the examples, there is a Z2, so a Z squared field in, and you basically can define with X, Y, and Z any field. So something I thought about, because the X gradient is so hard to design, might also be, we don't have to necessarily align our gradient axis with the spatial dimensions X, Y, and Z. We could also use X plus Y and X minus Y as two fields and just distribute the, so that's really advanced. So if you cannot follow, I think that's fine. So use X plus Y and X minus Y and Z to basically distribute the inefficiency and the inaccuracy to two channels.
That's a really
so you
cool
basically
idea.
just rotate your gradient system.
Yeah, and then the power dissipation, because it goes with the square of the current, would actually go down if you can average it out.
Exactly.
That's very cool.
Great. Sebastian, yeah, thank you for your presentation. It's very nice. This picture on the left side, is this Y gradient, yes? Or how do you...
If I remember correctly, I think that's the Z2, a shim. It's a quadratic field, so it's a shim field.
Ah, shim field.
Yeah, it's not a Z gradient. It's a Z squared for shimming. Mhm.
Okay, okay. And the place in the coil is, where is the place for in the coil?
So for the one on the left and for the one where you see only one PCB in the center, like where 11 is pointed to, it's in between coils. So it's like a biplanar system. So you have two stacks of PCBs, and in the center there's a small field of view. So Markus has shown the system yesterday, and there was like the tube you put in, and that's like the distance between the two PCB stacks.
So in the center, the blue lines represent this. So imagine this is a two-piece disc magnet, and the discs are on top and on the bottom, and the outer lines are the shielding coils, and the inner ones are the primaries, and in between goes the sample.
Okay. I think in the interest of time, I would just hand on to Wouter.
First of all, I made a mini print of the model that's over there. I took the original files as the rings are in there, and I just reduced them to 30%. So this is the true stuff. I will hand them out and you can just pass them over. Also of the parts of the gradient system. And to my surprise, actually, all the bits that stick out, indeed in the mini version also work to click them together or not. Didn't expect that. You can just hand them over.
Sorry, yeah.
I go start there.
Thanks. And our cameras now.
So on the parts that are being passed around, the different colors indicate different gradient channels.
Yeah. White is the Z, blue is the Y, and orange is the X gradient.
Yep.
Okay, then it's really awkward to sit down giving a talk, and there's good news and bad news. The good news is, start with the bad news. The talks I saw this morning, they all got covered, or they cover bits and pieces of my talk. The good news is I had the idea not to fix on the actual design and how to mount it, because I thought like things change over time, and that was a good decision because I saw so many things today already that are next gen as compared to this particular design. So in the black magnet there is the design I will use as an example, but my focus is on the process of designing it and what you encounter during such a process. So there's many constraints if you want to turn a electronic or digital design of a gradient into a practically usable design. And here are the constraints. So we are fighting for space, and you need to make, it's really in that particular design, it already is about every millimeter that is available you need to use, and that makes it pretty difficult. Then of course, like, you design the gradient system, but you have to get it into your magnet. And at the particular phase that we were in during this design, it also seemed likely that we might be discontented with the performance and had to take them out and replace them with a newer version. So it was kind of mandatory to make it relatively easy to take the system out and put a new version in. Then, of course, you're going to use it, actually use it. So you have the magnet there, you have a subject, the subject sticks the head in and then lies down. And if you then say, like, can you move a bit upward, please? What do people do? Well,
you're not really speaking into the mic. So.
Yeah, I'm not used to it. Okay, so what do people do if you ask them to move a bit? They put all the stress on their heels, hollow their back, and half of the weight is on the back of the head, and then they start moving. So the actual mechanical stress is also something to take into account. Now, then for the coils, they need to be in a fixed position, and you don't want them to move relative to one another and also not relative to the magnet. So there's a challenge there. And then, of course, it seems kind of a futile thing, but yeah, wires do come out and you have to feed them to the gradient amplifiers. And that really was something of a challenge there as well. Okay, I will go over these points and start with the original design. This is all from SolidWorks we work in. And yeah, the fight for space. Now, this is a cut through a vertical plane. And as you can see, and that had to do with the design of the magnet that was already discussed today, we can distinguish two outer sets of 3 rings that have a smaller diameter, that is to increase the field strength at that particular area of the magnet. And we have a center part that has a larger inner diameter. Now, if I make a kind of more schematic view of that, so this is a cut through the middle of the magnet, and we look at it from the side, and you see the wider central space and the narrower front and rear area. Now, there is one constraint, and already it was mentioned a couple of times, the X gradient is the most difficult one. And to make optimal use of the field it generates, we make it as long as possible. And indeed, we did have some experiments. Can we make it shorter? No, you cannot. So we are forced there to introduce the gradient. And I here show you the shell of the X gradient as a thin layer that stretches over the entire length of the magnet. And this is really a thing that you need to do in this design. Now, we want to keep the bore, so that the tunnel of the magnet, as large as possible, and there are various reasons for that. One, it's the comfort for the subject that lies in there, because the closer the wall gets to your face, the more claustrophobic it is. But there's other very good reasons to keep it wide, and it is that the lining of the bore, there's a conductive sheet there to shield interference, electronic RF interference. But the closer you get with this shield, and that's what happens when you make the diameter smaller, the closer this shield gets to the coil, you lose efficiency in your coil. So you want it as wide as possible. So what do we do with the X of the Y and the Z gradient? Well, it's pretty obvious. We put them on the outside. So this is the setup that is hidden inside that particular board. Now that introduces another problem. Of course, every solution comes with its own problems. How do we get the gradients in or out? And we start, of course, with the the 3 channels in yellow, green, and red. How do we get it in? Now, one of the options we do have is first remove one of these triplets of rings that have a smaller diameter, take it off, then just the entire setup with the 3 coil channels, the gradient channels, you just slide them in, and then you get this set mounted back on the scanner. The good news here is that you can totally join all the segments even of the different coil channels, but also the coil channels themselves together before you put it into the magnet, which is kind of convenient because you can approach it easily from the outside and build it as you go. The bad thing is, though, you have to take your magnet apart. And just remember the issues this morning about magnet design. You build your magnet, put it together, then you get this probe and you measure the field distribution and change your with that. Just imagine taking 1/8 of the magnet apart and then reintroduce it again. Then you might have to do this all over again, which is not nice to do. So that's what we decided then not to choose. And we went for the second option, and that is to split. And that's why you have these smaller parts of the gradient system. We decided to split each channel in 2 or 4 parts. So they are small enough to just feed into the magnet, mount them there, and then join the elements or the quadrants together afterwards. So first the Z, then you add the Y elements, and the X is you can slide in. Yeah, so what is good about this or what not? I said, like, as a header there, it's more complex, but with a question mark, because it also has advantages, and it depends a bit on how you use the system. If you want to change your gradient system every now and then, maybe, if a new improvement is made, then it's really easy to get the gradient system out. If this is not the intention you have, maybe the other option is favorable. Okay, then the other constraint is the mechanical load and also how to get rid of heat that develops. So for the mechanical load, all the demands we have is like they should be rigid. And we chose to 3D print them with PLA, which is cheap. And when you are prototyping, it's really nice to use, but it's relatively soft. And especially under mechanical stress, you can pretty easily bend it, and you don't want it. So the shells are relatively thick. Then again, mechanical forces like the weight of the subject or other forces, you need to kind of catch and also divert them to the other part, meaning being the magnet, that is much more rigid. I'm quite amazed about the magnet. Like, you took it to London, right? And what we did, we transferred our magnet quite a number of times and did kind of stupid things with it in a way. Keeps up really great. So this construction with the rings, and it's really rigid. So that's the way to go if you want to solidify or make your gradient system more solid. Transfer all the forces, the mechanical forces, to the magnet, and you're fine. Then again, it also needs a very tight fit. So if the subject in the scanner does move about, then your gradient system is not moving as well, or during scanning maybe even that it starts vibrating. You don't want that to happen. The easy bit up till now is the dealing with the heat. It's very easy to kind of criticize the design of the gradient shells that go around, because I just put a couple of holes in there with the idea, okay, let's get rid of the heat. If truly heat was generated in the gradient system, I wonder whether that is sufficient. But yeah, hey, that's the next level. the way we operate our gradient system right now, I don't fear it. Maybe if we get stronger amplifiers or more heat dissipation, yes, it might become an issue, especially because of the plastic. If it gets hot, it gets softer and maybe less rigid. Okay, so the solution to take care of those mechanical forces are like, and you maybe already seen it in the mini prints, is that on all these, do I have a pointer?
Yeah, but if you use I think it's easier if you use
the mouse. The mouse.
Because then the online people can also see.
Ah, okay. Yep. Yeah, sorry.
But then
It's there already?
See the pointer there.
Oh, I see the pointer there. Yeah, okay. So you see all these cams on there, and basically they are meant to build pillars, just to conduct the mechanical forces. And if I cut through the system again, you can see that here, this is a cut through a single ring, but its neighbor here carries a pillar up to there, and this little cam on the Z gradient also continues on that, and we start building these pillars. Like if you add the Y gradient, it's continued, and finally the X gradient. So you can see that from all the way down there to up there, there's a pillar, and there and there. And that's every 4 centimeters, there's a pillar, and there's many of them. So really, if you put in the first quadrant of the Z gradient, you have to force it a bit, and you just smack it in there, and it goes bang, and it's really truly solid, which is a nice platform to build the Y gradient onto, and then the X gradient. So there's other constraints if we talk about the positioning of the gradient system, because you don't want any translation or rotation, and there shouldn't be too much play so it can wiggle about. That's quite a challenge to get right, and it requires a tight fit. So it can be a precise job if you insert the quadrants, because if they are skewed a little, then it immediately gets stuck. But I think the present setup works really well. Of course, this all changes with the design that is now like standing over there. The new design of the magnet that Tom also talked about, because then the inner diameter of all these rings is identical. So that gives you the opportunity of joining all the gradient channels together and then slide the entire unit in as one piece. This is a bit of an explanation for people that are not used to work with MR. So why does this positioning needs to be so strict and also solid? Because it will lead to image distortions and all kinds of trouble. And if you take a careful job of adjusting everything, get your sequence right, and then the gradient system starts moving about, it's very hard to get a reproducible image quality. So there's lots of cams, and you saw them on the print. So there's cams to stop the rotation of a part of the gradient system, and they are all over the place. You need to know where they are when you mount the stuff, because you need to pay attention that they fit in the right position. Yeah, and then there's the wiring. Wiring is also kind of tricky. And of course, if you were to pick your favorite setup from the middle and the left image, I hope all of you go for the left image. Like, it needs to be done in an orderly way. And not only because you don't like wires hanging about, but the thing is, every piece of wire creates a magnetic field when it's in there. And due to the presence of the magnetic field of the magnet itself, they start flapping about maybe if you push a current through, but also these fields of those wires disturb your gradient field itself. So what we took care of, and that's also in the design Sebastian already showed, in some images you could clearly observe that every piece of wire that does not contribute to the coil itself, but is for feeding, of going to the gradient amplifier, you need to have a piece of wire parallel to it that carries a current in the opposite direction. So that's also something you need to take care of in the design. Just a schematic view. So because we divided it up into 4 quadrants, the red connections there, the red lines in the schematic shows you the connection between the different elements. The green and the yellow show you the connections to the gradient amplifier. And it was taken care of that if you follow the current that goes through all these wires, there's always a piece of wire with a current in the counter direction. So in practice, it looks a bit different. Coloring is the same, but here you can see for the Y gradient, for example, that these wires that connect the quadrants meet up in between the segments and are connected together. And this is exactly what makes it easy to get the system out, because you just unscrew those nuts and the wires are free and you can lift one of these segments out easily. And this is what I mean, like putting the wires in when you first put the segments in there, and then you have to put the wire in. It's kind of a fight because this wire has to be put in all around, and then you have to put the other wires next to it. In the 3D print, it is provided for that there are channels that you can put your wires in. So once you tuck them in place, they are solidly placed there and they don't move anymore. Okay, I go over this one quickly. The only thing I want to show you that because it's a layered system, we start with the Z. It's easy to get those wires out and feed them through. But the next shell you put on, the Y gradient, you cannot put the wires out in the same way because the Z gradient is in the way. So there is a secret exit provided there. And if you feed the wires through there, the wires just go in between the next set of rings that carry the magnets. I'm totally happy how it is now. The first time we tried to put the wires through, it was pretty difficult. Did you have a challenge there? We had some fun assembling it. Yeah. Okay. There's due to this experience, also the one in Mbarara we did in Uganda. Small changes to the 3D prints were made to guide those cables out. So the struggle you had with the X gradient, for example.
Maybe I will answer for Reilly. The Dremel is also very
Yeah.
The Dremel is also a very useful tool here.
Oh, you're lucky man. Yeah.
I made some changes, especially on when you are connecting. I don't know how in English power shoe. Use the microphone. Yeah, of course.
Yeah, lugs.
Yeah, I had to do some changes to the 3D printing to fix everything inside. But the most challenging was the X gradient.
Yes. So in the later version of the print, so that's what they do now in Paraguay. There's a tube curved that leads the wire in the correct direction, and so.
For the new magnet, we don't want to have any connections, so just that the cable comes out on one side and that's it. So a little bit out of this experience. So the design is great, but for reproducibility and also to have avoid some other issues, we will just try to have.
Yeah, that's an excellent idea, and that's what I thought this morning when you were talking about the setup of. All the software that is accessible, that you get all these versions about, well, you talked about it. That's for this type of design also really great because you can see what versions are there, because we only had to talk with you guys and with Josh in Paraguay. And then it's already difficult to get a track of what version of what part is where.
And maybe also for the future that it's useful to have that properly version numbered and also keep track of who has what.
Yeah, that's really important, especially because the group is getting larger, but also that ideas from different groups should. I mean, I heard so many things today that are really good suggestions, and it would be great to integrate them all as soon as they become available, right?
Yeah, but that's a great comment, and we should have somewhere in the GitLab pages, we should have a space for what the site actually has, or which things it rebuilt, which versions, etc. I think this would be really important. Yeah. Maybe just in the interest of time, we can go to the next presentation. Is that okay? Because we wanted to squeeze in yes or no? Yeah? Okay, great. So just a very quick overview of OwnTech, what we just discussed. So that's open source world. People are online and give directly a talk on it. So maybe we can just hear what they have, and then we continue to the RF coils. Yeah. Thanks, Wouter.
You're welcome. Yeah.
Okay, can you hear me, guys?
Yep.
Yeah, okay. So yeah, I just jumped into the topic because actually Axel told me that I might present the things that we are doing in France about power electronics. I'm quite amazed by the complexity of the project you are tackling, and having a chance to see this amazing project regarding open source hardware in general and imaging is really a matter of hope for me, and to see that we are always pushing the boundaries of what is doable as a technological common is really great. Sorry, I will try to, yeah, do you see my screen at the moment or not? Yeah.
Could you maybe full screen your slides, because we see both?
I'm trying, but somehow it's not working out. Okay, yeah. Well, it's not, yeah. Sorry. It was working without the screen sharing, and now it's not working. Well, I will go in this mode, and I will try to make it the biggest I can. So we are a project that deals with making power electronics open source as well, because power electronics is a tough topic, and it's present in every possible system in the world. And we need to open up these black boxes in order to tackle the challenges that many integrators will have in the future, both for open source projects and in general to tackle the complexity of the system out there. Basically, I will skip really fast the introduction, because the introduction is about, okay, we need more than ever to electrify our society and to shift away from fossil fuels, sorry. And in order to electrify, we need to electrify everywhere and not only in the north. Basically, in order to electrify and in every possible system, we have really complex subsystems that are power supplies. And in order to tackle the challenges we are facing at the moment, we need to have more and more people to dig into the complexity of these black boxes that are powering our systems. Our main hypothesis is that people learn better by solving real-life problems and sharing their solutions with passionate peers. And as such, we believe that what we lack with regard with power electronics is a way of developing your skills and creating solutions, innovative solutions, through sharing and having like a technological common that would be an open source, reprogrammable power supply, power electronics, sorry. So I will skip really fast, but the problem is really big. In every possible direction, we need more power electronics, and MRI is one of these cases, I guess. And what we do at OwnTech is we are proposing a community-based open source power supply that is compact, versatile, and low cost for prototyping power electronics. So basically, the main goal is, and the philosophy behind it is to try to do, to achieve what Arduino and Raspberry Pi have achieved in both industrial informatics and informatics in general, and to try to translate into power electronics so that we have like the same simplicity of use and that we can tackle different use cases with the same generic hardware. So basically what we propose is a technological sandbox, which means that we have like both an open hardware, but also an IDE in order to program these power supplies, also a unified documentation and a way of monitoring the use case so that we really create a sandbox that permits and enable different players in society, so industry, academia, and makers and fab labs, and we provide them this sandbox in order to foster new ideas that can be in a limitless amount of applications, such as smart grids, mobility, energy storage, and so on, but also have the possibility of enabling new talents for the field, because actually it's quite hard to find talented power electronicists, and we need more and more of these people to tackle tomorrow's challenges. From a technology standpoint, what we propose is a standard and generic module that can be reprogrammed depending on the use case. It has a really wide and broad input and output range. And the goal here is to make it modular in a way that we can have a standalone module or deploy it in 19-inch racks in order to extract more power depending on the use case. Till the point that we can have a full electrical cabinet with generic modules that are synchronized and that will have, like, you will get the same simplicity in mind in order to deploy your application on this electrical cabinet. This is possible because of the small brain inside. So we've developed for that a specific controller that is tailor-fitted for power electronics application, with super high resolution for PWMs and so on, with really fast ADCs that you can be combined directly with the digital outputs and so on. And we've put a lot of effort into making these things accessible for the people. So with a standard software suite that is MATLAB compatible, that you can go and code with the same ergonomics as an Arduino, basically. So that it's an enabler for the people that want to learn power electronics, but also for people that have amazing projects out there and then want to dig in and explore if they can tackle the power electronics part of their project as well. And I will be really fast on the last one. So basically everything is open source. And so basically we make a distinction between the tool, which is what we propose as a sandbox, and the solution. So basically, if you write a text in LibreOffice, for instance, the text you are writing in LibreOffice is your own, but the tool itself, LibreOffice, if you modify it, you have to share back the modification. In our case, it's exactly the same spirit. So if you modify the tool or the technological sandbox, then you have to share back your modification. But what you will deploy in a matter of code and how you will tailor fit it to your application is your own piece of code, and that can be closed source as well. So yeah, as a conclusion, our goal as a foundation for power electronics access is to create and foster a community around this digital power space. And also to disseminate technological and educational content out there to help having more people involved in this specialty. And of course, we want to animate the community in order to foster the organization of an IP, technological IP common, so that we have like more and more functions that are supported by a common and open tool that can be deployed in many different applications. And I think that's it for me. I hope I was quick enough and not interrupting much.
Yeah, thanks a lot for the presentation. Maybe you can really just keep to very short, quick questions. Is there any? If not, I will ask one. how far are you ahead with your development? Like this 300 watt modules, are they finished? Can you right away use them, or?
So yeah, we are now pretty advanced. We are in the pre-production run. So the foundation part that I was presenting is a part of the project that is dealing with opening things to the community and having a way of ensuring that if people will, if people like put some modifications and so on, it will be open source forever for everyone and so on. On the technological aspect, we are at the moment incorporating the company and starting building these modules and selling them online. We have validated many things in the lab, so the communication between the modules, the synchronization, the possibility of expanding the power range with parallel modules and so on. We've experimented a lot in order to see what is the maximal bandwidth of the systems and things like that. And so,
okay,
yeah.
so you basically so there's a company behind, so you have the open source developments, but you also have a product that can you sell it right now, or would it?
We are finishing our pre-production run, so in a matter of a few months there will be available online. Yeah.
How many months?
2, 3, 4. I don't know exactly.
Okay.
We are finishing tuning the machines and so on. We have a lot of problems with the pick and place machines and things like that. So I wouldn't put my hand.
I have to ask.
But yeah, basically.
Thanks a lot. I think it's very, very cool and very interesting. Yeah.
Just a quick question. If you look at your community, what is the majority focus of the people in the community who plan on using and implementing these things?
So we have a lot of people that are envisioning utilizing it. For smart grid applications. So in renewable access and things like that. Also for battery charging and having more and more storage and decentralized storage and things like that. Also, we have use cases in the mobility and electrical mobility, such as e-bikes and things like that. And also, we are developing in the lab at the moment modules that will be not only 300 watts, but 3 kilowatts, so that we can tackle more power demands, basically. More demanding applications.
Cool.
Sorry, maybe one last question, maybe quick. Do you plan to collaborate with people who are also in the same kind of space? Like, for example, Libre Solar, who are building open source solar solutions, developing the Fair Battery project, which is trying to make a redox flow battery, an open source hardware one. Is there any collaboration plan there?
Yeah, so we are collaborating with Martin, definitely, from Libre Solar. We've done some projects together, especially regarding the interconnection between what he has developed and what we are developing, so that they can communicate and then they can tackle smart grids application all together without colliding and things like that. Also, we have a project together with Axel as well. So we have Martin, Axel, and I on board. So we will basically put all these power electronics in an e-bike and open up the electronics aspects of an e-bike, for instance. So this is this kind of application that can be tackled all together.
Thank you.
And regarding the redox, no, not at the moment.
Yeah, thanks a lot for this spontaneous presentation. And yeah, all the best for the project. Sounds like a really cool project.
Yeah, sure. And if by any chance you have like some things in this MRI machine that have like some tough requirements regarding power electronics, maybe we can envision things depending on the specification, of course. Maybe not for the main magnet, because I think like the current demand is huge, but some things that needs high bandwidth and lower power is definitely something that we can tackle. And this is a core thing, because power can be expensive, especially when there is no specific off-the-shelf components that can tackle the goals that you are trying to achieve. So yeah.
Yeah, we will definitely have some discussions. So maybe if you can just write your email address in the chat, and then that we can contact you, and we will definitely have some discussions on that. Thanks a lot.
Sure, thank you. Goodbye.
Okay, so the next presentation will be done by Tom on RF coils.
All right, so I'll try and do it quickly. So there is no definitive answer. Well, there is somewhat for low field, but there is a lot of room still for coil optimization, and also what does coil optimization actually mean? This is definitely not a definitive slide, but I just wanted to share some of the experiences that we had and some of the design choices that we made for the coils on the OSI system. As you can see, this is definitely an iterative process. I've built way too many coils over the years. Laser pointer. Cool. What makes a good coil? Is that different for a transmit coil than a receive coil? Does it matter whether you're high field or low field? How do you go about actually building a good coil? What can you optimize? What does optimize even mean? Are there practical limits? And also, with the good often comes the bad. So we designed a good coil, but in terms of on the receive side, but scanning with it actually turns out to be much more difficult than we realized. So I want to start with sort of describing what makes a good transmit coil. This is, you want a homogeneous B1 field. This gives you nice even contrast. You want high SAR efficiency. So basically the amount of magnetic field we get versus the electric field we get, we want to keep as high as possible. And then we want high efficiency as well in terms of absolute efficiency, which just means the amount of B1 fields. So for those not in the MR word, B1 is basically the amount of the strength of the RF field that we use to tip the spins. We want a lot of it per unit input power because it means we can use cheaper RF amplifiers. So what makes a good high field transmit coil? Well, wavelength can be an issue in high field. So for those familiar in the field, it's actually very difficult to get a homogeneous B1 field as the wavelength of the RF. So at high field, we have higher frequencies, and as the wavelength gets shorter with those higher frequencies, we get standing wave effects in the head. So you get all kinds of weird shading, which comes from the fact that your B1 is no longer homogeneous. At high field, the SAR is often limiting. The SAR increases square of the the magnetic field strength. The B1 efficiency is not hugely, the absolute B1 efficiency is not a huge issue. The SAR efficiency is, but the RF amplifiers, it's you basically have infinite power available to you, which is not entirely true, but it feels like it. So in low field, we have no wavelength issues, so that's pretty nice. We have virtually no SAR. Important to say virtually, this is something that should be monitored. And you can certainly build a coil which is less SAR efficient than is ideal. And the coil efficiency is usually okay. Not too bothered about it. So what makes a good receive coil? Well, you want high B1, B1 minus, which is really truly exactly the same as B1 plus, but we refer to it in a different way. Technically, it's polarized in the opposite direction. Right? So this is where high field loop coils usually come in. And for parallel imaging purposes, we want to have each coil have a unique sensitivity profile. Yeah, we want to maximize the B field. In order to do that, the coil type is an important choice here. So on high field, the choice is kind of made for you by the direction of the main magnetic field, because the magnetic field produced by your RF coils, of course, has to be orthogonal to the main magnetic field. So you're somewhat limited in your choices on high field between saddle and birdcage coils. A saddle coil is kind of or a birdcage coil is kind of the same as a saddle coil. It's two saddle coils. And on the low field side, because our main magnetic field is oriented across the bore, we can actually use a solenoid coil, which is brilliant because a solenoid is the absolute dream coil in terms of efficiency. So coil size obviously matters. A smaller coil is better in terms of B1 field, but obviously you have to fit your sample into it. So there's practical limitations on what you can do here. So you want to maximize your B field. So that's, as you noticed, is really related to the geometry of the coil. And then you want to minimize your losses. And this is a long story, and this is something I can talk about for hours, and I'm trying to contain myself. I'm trying not to bore you too much. And it's also, this is a story that's very different for different frequencies. So high field is very different from low field, and actually midfield is sort of the awkward stage in between. So how do you actually go about measuring the performance of the coil, and what is something that you actually have to consider when it comes to designing these things? So we have this number called the Q factor, which is a nice number because it allows, it's a single number that allows us to quantify the high magnetic field strength and the losses. So basically a high Q factor would imply that the coil is performing well, because either the field it produces is high, or the losses of it are low, or both, ideally. So the quality factor is defined as omega L over R. L is the inductance of the coil. It's a measure of the amount of energy that's stored in the magnetic field. R is the resistance of the coil, and it's a loss term that dissipates energy. And the SNR is proportional to the square root of the coil, of the Q factor. But this is really true only for coils with the same geometry. If you start changing the geometry, you can have two coils with the exact same Q factor that give you wildly different SNR. So that's something to consider. And generally, if you want to maximize your signal to noise ratio, you should maximize your Q factor. So as I said before, if you want to maximize your B field, the solenoid is an absolute champion. It's about 3 times better than any other coil that you can get. The minimum size is set by the anatomy. So we typically use 2 different coils for knee imaging. We use a 15 centimeter long, 15 centimeter long, 15 centimeter, that should say diameter, 15 centimeter long solenoidal coil, and then for head imaging we have a slightly different configuration that I'll probably get back to later. So how do you get more magnetic field from a solenoid? You can create more turns, you can add more turns, and this is something at DC that I think everybody knows from their electromagnetics courses. If you want to get more field from your solenoid coil, you add more windings, and it essentially acts like a current multiplier. So but it also it increases your inductance. It's proportional to the square of the number of turns, but actually your losses are also proportional to the square of the number of turns. Don't ask me the derivation for that, because it feels like it should be proportional to the number of turns, but actually in practice it's the number squared. So actually it turns out that the Q factor of your coil is independent of the number of turns, which is very strange, but it basically means that you can't just keep winding and winding and winding turns on your coil to get more SNR. I tested this. It's one of the many of the coils that you saw before was testing exactly this, and it appears to hold perfectly true. So conclusion is we're stuck with what we have. So instead of trying to generate more magnetic field, we have to address a loss term instead. As I said before, R is the total losses in the coil, but there's many terms contribute to this. So we have 2 predominant loss term categories. We have the coil losses, which are the losses in the material that the coil is made out of itself. And then we have the sample losses due to the conductive sample that is placed inside of the coil. And this is really where the difference between high field and low field explodes, because at high field the sample losses are dominant because the electric field is so much larger, and it's really the electric field that is causing the losses inside of the sample. It's not entirely true, but they are typically the dominant loss terms inside of the sample. So this is also where in high field you tend to go to smaller coils because they tend to penetrate less far into the body, so you have fewer issues with the sample sample losses, and that's also where the coil array comes in. Instead of having one giant coil, you have many small coils, and your sample losses, your total sample losses are lower by having the array. At low field, typically the losses in the coil is dominant, but we're now at a point where we're essentially 50-50 in terms of sample losses and coil losses. So here, large coils are better because then you basically want to get to a point where your sample losses are dominant over your coil losses. And so a larger coil will have larger sample losses. So one way to reduce the resistance in your coil or the losses in your coil is by making the coil cold. So you often see, especially for animal experiments, that people use cryogenic coils. So it's basically a free SNR boost to your system. Well, it's not free. It's not free. It costs a lot of money, a crazy amount of money, but it does give you a lot of SNR improvement potentially. It's also, there's always asterisks involved, and you should never believe exactly what the manufacturer says, but it does boost your SNR significantly by being able to cool your coil. But in the context of low-cost MRI, it's not a feasible option. So I'll now go through the process that we went through to optimize the coil, and all the experiments are done on a 156 millimeter diameter coil and 150 millimeter long. All of it was wound on a 3D printed PLA former. We did also look at different print materials, but it didn't really make too much difference. So if you want to reduce your losses, you can make your wire thicker. So Lukas, the coil that was here earlier used very thick wire, 2 millimeters. Yeah. So obviously this reduces your wire distance, resistance at DC, your losses being, or your resistance being proportional to the radius squared of a wire. So in theory, you double your wire diameter, you get a quarter of the resistance. So we did exactly that. Our initial coil, we used 0.8 millimeter wire. We moved to 1.5 millimeter wire, and our Q factor improved. So that's great, but we expected a 4x improvement in performance. So what's going on there? So this is where the skin effect starts coming in of wire. So at DC, we have this R² relationship, but as it turns out, at higher frequency, the skin effect comes in, and basically your currents are no longer occupying the entire wire, but they're mainly stuck to the surface of your wire. And as the frequency increases, this effect becomes stronger and stronger, and at some point, your resistance becomes proportional to the radius of the wire rather than the radius square of the wire. So that sort of goes a long way into explain why if we essentially double the wire diameter, we're only seeing slightly more than doubling of the Q factor. So you'll also see it even at 1.5 Tesla, where they designed some coils. They use this hollow wire. You say, why do you use hollow wire? Well, it's a lot cheaper than solid wire. Well, it uses a lot less material, so it's lighter and technically cheaper in terms of material costs. And for them, it doesn't matter because the current runs on the surface anyway. So why waste the inner material when you're not using it? And so that comes exactly from this surface current, the skin effect that I'm talking about. So what you can do instead is to use Litz wire. So the idea behind Litz wire is that you use many thin insulated strands together, and because the wires are thin, the skin effect as a fraction of the wire diameter the skin depth as a fraction of wire diameter is substantial. So you're using a lot more of the wire rather than having all the current just on the outside. Each individual wire will have the current on the outside, and in theory, this really helps reduce your resistance. But it does reduce your conductor mass because instead you have all these gaps between, and each individual wire is also insulated. So really the amount of copper that's in the wire is I think roughly about half. It probably depends on a lot of factors. So this is a DC solid wire will definitely work better. But the losses, so there is an optimal frequency, because at higher frequency, other effects start coming into play, which means that the Litz wire also doesn't work out. But actually, everybody has a different opinion on when Litz wire stops being beneficial, but actually we see a benefit from it. So we built a Litz wire coil, and we see that the Litz wire coil is, again, it's not quite a factor of 2, but it's still a substantial improvement in Q factor. So then we also have the sample losses. So Maxwell basically says there is no time-varying magnetic field without also producing an electric field. The electric field causes losses in the sample. The conductivity is frequency dependent. The electric field is also frequency dependent. So you really see why at high frequency that this term tends to become dominant. The E field of a coil becomes the E field produced by a coil increases if the current distribution is not constant in your wire. And this is a little bit of an abstract thought, because your current distribution should be constant, because you can't just magically build up charge in places. But basically, it comes down to, at self-resonance of the coil, you get a very you essentially get a how do I say this? The closer you are to the self-resonance of the coil, the more uneven your current distribution becomes, because basically, if you imagine it like a skipping rope, in the middle you get huge oscillations, but at the end you have no oscillations. It's the same with your current distribution. So you have this very uneven current distribution, which leads to a very, very large electric field inside of the coil. So what this means in practice is that long conductors should be avoided to stay away from this self-resonance. And what you can do is you can actually split your coil and then solder capacitors at the splits, and this helps reset this is a very hand-wavy way of talking about it, but it helps reset the current distribution in each of the segments. So effectively you're scanning with 4 short coils here rather than 1 long coil, and that just helps avoid those self-resonance issues. So if we look at a 45 turn solenoid, which is what we were using up to now, that's 22 meters of wire. We have 150 meter wavelength at low field. That's 52 degrees of phase that we can build up along that wire. So we tested a number of segmentations, and this is important here, that for the unloaded case, which is basically when there is no sample loss no sample in there, you don't notice these effects. But for once you start putting your sample in, that's really where you start seeing the effect of these self-resonance things come in. And actually, I believe if you want to build the highest Q factor coil, which is unloaded, you should actually operate it at the self-resonance frequency. But then you have to keep anything conductive about as far away as you can possibly get from there. So we tested a number of segmentations, and here we see what I mean is we start talking about this Q ratio, and this Q ratio is a bit of a controversial thing, because people always talk about, oh, you want to maximize your Q ratio because it means that you have an efficient coil, and that's not true. You want to maximize your loaded Q value. So in this case, by increasing the number of segmentations from 1 to 3, 1 being a continuous coil, one just having a capacitor, meaning 1 split, and then 3 segmentations, meaning we've split it in 3 locations, so we end up with 4 segments. We see that the Q ratio goes down. I don't care too much about the Q ratio, but because what matters, as I said, is the loaded Q factor. Because if you follow the literature, other people would suggest to use this coil, but that you should use definitely, because it has a high Q ratio, but it's very important that the coil with the highest loaded Q factor should be used. So another way of reducing these wavelength effects is to reduce the number of turns, but the number of turns also affects the homogeneity of the coil. If you have very sparsely wound coil, then obviously you're going to get an uneven coil distribution, because you basically get a bump in your B field at every turn. So there is a limit to how much you can reduce the number of turns, but we have reduced the number of turns on our coil to
one every 7.5 millimeters now, so 20 turns in total. But in both cases, you see that the ratio of the Q factors is greater than 2, and that means that in both cases we are actually sample noise dominated. So people said that Joy is coil noise dominated at low field. No, in this case we are sample noise dominated in both situations. So what does this actually give us? Well, we started off with a coil many slides ago, maybe too many slides ago. Started off with our coil with copper wire. Actually, if you put it inside of the shield, the Q factor drops to 88. So that's where we were, and that's the solid copper coil. And if we now look at a spin echo, same sample in all 3 coils. Again, for all of the coils, the Q factor drops once you put it in the shielded magnet. And we look at the direct signal in terms of microvolts after our preamp. Is that true? No, that's before our preamp. It's normalized to the preamp. We see that the signal strength increases with the square root of the coil factor. So that's great, right? Because we now have the same coil and same coil geometry. We can image the same field of view, but we almost have doubled our signal to noise ratio with relatively little effort. But there are also drawbacks. With every good thing comes a bad thing in engineering. Why do we not want high Q coils? Well, the coil ringing gets long. So coil ringing is basically how long does the RF pulse remain in our coil before it's decayed to basically noise level. So this is characterized by a decay time, so a 1/E time, which is 2Q over omega. Well, omega is fixed because we're at a low frequency, but it is a lower number than a high field, so it's ringing is a problem anyway. But as we increase the Q factor of these coils to very large numbers, this tau becomes very long. And I do have a slide on that. So this can heavily distort your pulse shapes. We also narrow our coil bandwidth. Coil bandwidth is inversely proportional to the Q factor. I think it's omega over Q, but it is omega over Q. So this also can start introducing problems on both the transmit and the receive side. And what's important here is that transmitting outside of the bandwidth can damage the electronics, especially if you're using high power pulses. Because basically the coil refuses to accept stuff outside RF power outside of its bandwidth, and this will get reflected back into the RF amplifier. So this is something that should be taken care of. And on the receive side, you get a frequency-dependent shading in your image as you move outside of the bandwidth. So to show you the effect of the Q factor on the coil, so this is an image on the right. On the image on the left is the input, the pulse generated by the spectrometer, and it's also what we measure on the output of the RF amplifier if we're going into a non-inductive load. And then on the right is what comes out when we use the low Q coil. It's already distorted, but the distortion is not too bad. But this is as we start increasing the Q factor of the coil, that distortion gets worse, and you can see that we don't even really ramp to full power here. So it's a really strong distortion, and you can even visually see the ringing of the coil still 300 microseconds after the pulse has been switched off, and that's the fact that you can visually see it means that you can definitely measure it on your RF signal. But this also affects the excitation profile of your coil itself. So if we take the Fourier transform of the block pulse, which is kind of how we look at the bandwidth of an RF pulse, we get the blue pulse, and then we see that by the distortions of the pulse, we lose those high frequency components, and we end up losing some bandwidth on the excitation pulse. So this is the frequency-dependent shading that I mentioned. This is the same phantom in the low Q coil and the high Q coil. So we see nicely that the high Q coil has more signal if you look at exactly at the resonance frequency of the coil. So we're at 200 versus 120 microvolts. But outside of that frequency range, it falls off much quicker than the low Q coil. So is there anything you can do about it? Well, yes. As it turns out, not only does your signal drop off, but your noise drops off as well. And the noise in an MR experiment should be white.
So what we can do to correct for this is basically we divide our image that we've acquired by our noise profile, and we get a much flatter image back. So this is this image on the right is also more truly reflective of what the signal to noise in the image is actually like, because it's literally your signal to noise ratio. So with that in mind, do we actually get an image image enhancement by using the high Q coils? Well, yes. So this is a pineapple that we've imaged. We have since improved the image quality of all of these images, obviously. But this is, I think, nicely represents the improvement in image quality that we can get between the low Q coil and the high Q coil. So we're at about a factor of 2 improvement now. So as an example of some of the images that we're able to get, these are some, this is a dog that we imaged, an ex-dog that we imaged, and it shows really nice SNR throughout the image. Only towards the end do you start getting signal drop off by the fact that we didn't really put any effort into optimizing the homogeneity of the coil. So this sort of shading and some of the banding artifacts that you see in there come from B1 related issues. So this is with no signal averaging in a reasonable scan time. Also some T2 weighted images on the dog brain with the very weird looking eyeballs. And then we do the same. Obviously, we didn't image the head with a circular solenoid coil. We have a head coil, which I don't know if I have a slide on in this presentation, but it's basically a tight fitting head coil, which has had the same optimization done to it. And we're able to get quite good image quality with good coverage over the entire head. So to quickly summarize the story that I sort of tried to tell you is that coil optimization is very much a field-dependent optimization problem, and at low field, the material selection used to build the coil. So I didn't get into the capacitor choices or anything like that. But all of those play a huge role. So we've actually been able to improve the Q factor even further now. So I think we're about 550 by tweaking further components. We can achieve body loss dominance. This is important. I didn't get into it, but it's when you're improving the Q factor of your coil, you're matching your coil to 50 ohms, and this is something that's very important, and actually is something that's visible on this. If you're matching your coil to 50 ohms and you have a high Q coil and a low Q coil, despite the low Q coil having a higher resistance, the noise is not higher in your low Q coil. The signal is higher in your high Q coil. The noise is the same. The noise at resonance, the noise or at where your coil is 50 ohms, the noise of your coil is as if it's a 50 ohm resistor. And you don't get, so people talk about body noise dominance. When you're 50 ohm matching, you should really say body loss dominance, because it's a loss term which is affecting your signal strength rather than something which is increasing your noise. So you're increasing your signal and your noise stays constant. That's an important distinction there. So we're body loss dominated at low field, because this Q ratio of 2.4 implies that the losses in the body are larger than the losses in the coil. And this loss term now at this point, we're fairly comfortable to say that this loss term comes from the remaining magnetic from the B field itself, rather than the electric field, and that also places a limit to how much further we can push this, because really the only way in which you can sort of decrease our losses is also by decreasing our magnetic field, but that's sort of futile because we want the magnetic field to do our imaging. So there is at some point definitely decreasing return on investment also there. And then we can correct the shading in the image, which is introduced in the received images, which is related to the receive bandwidth, where we can correct for it quite easily by doing this noise correction on our images. So this would be like I think it's a 10-second pre-scan that we do just to measure the noise profile. And that's also a very good way of determining whether you have an extra EMI in your system, because you know that it should be the noise of a 50 ohm resistor. So for coil optimization, we can relatively easily improve the SNR in our images. This can be up to a factor of 2 in phantoms, but in vivo it will be less than a factor of 2, just because we are approaching that body noise dominance. So thanks for that. And again, we have to be a good boy and put the text from the AIM partners in there. But, yeah, happy to answer any questions. And I'll put I forgot that this slide is also in there. Not that I want a second round of applause, but this is also to show that when you're dealing with a transmit and receive coil, probably the easiest way of measuring the SNR of your coil is to look at the transmit efficiency of your coil, which is basically how much power do you need for a 90-degree pulse, because that's an absolute term. You can easily see where your 90-degree pulse is, because that's where your signal is maximum as a function of power. So here we also see that at least the power, because it's related to the square of the voltage, is proportional to Q, and we do see this nicely Q-dependent power optimization here. But this is only when you're driving the coil on resonance. Again, off resonance, you get horrible effects. But yeah, it's a way of a simple way of determining the true SNR.
This was exactly my question. This bonus slide explains it nicely. So you did transmit adjust every time you put in a new coil and looked at the right flip angle at 90 degrees every time.
We do that every time.
Yeah. What was my second question? Did you simulate the coil? Did you want to use the coil with the distributed capacitors? If yes, did you simulate this for your ZAR simulations? Because the E field over the capacitors are the most viable spots for high ZAR locations.
Yeah, but it's quite a local effect, though. It doesn't tend to propagate too much into the body, as long as you keep them away from directly. Don't put them directly on the body. Yeah.
But if you have these distributed capacitors, instead of having them at the edge of the coil, then you have them, like you showed in your picture, at the all of the side of the coil.
Yeah.
So they come in close contact with the...
Relatively close, but you can place them a little bit further away from the body just to prevent that E field coming.
Is there space between the RF coil and the grading coil?
Yeah. Which is why I'm trying to get Lukas to not make the board too small on the next magnet.
I have a question.
Yeah. I'm sure you would.
Do we need automated tuning matching?
Do we need automated tuning and matching? No. If you want to use this in the clinic, do you need automated tuning and matching? Yes. Eventually. For now, I mean, it's not a difficult, we're talking about, especially as you reduce the electric field effects, you're also reducing the frequency shift that you get by introducing a body part into it. So it is relatively stable. You notice a slight difference in head size. If somebody comes in with a particularly big head, I have a particularly big head, we see that there's a slight retuning involved. And also if the magnet obviously shifts a lot in terms of frequency, then it's also important, because for these high Q coils, you have to be really within a kilohertz of the frequency. Even if you're operating within the bandwidth of the coil, the ringing, because the coil ringing, it's a dynamic process, but the coil ringing tends to drift towards the resonance frequency of the magnet rather than of the coil rather than the excitation frequency. You start getting all kinds of weird power optimization issues.
Yeah. So yes.
Sorry. Yes. Eventually. Yes.
I've got a question too. Did I understand correctly that the losses in the sample are dominant to the coil losses? So that means you solved the whole noise problem, because you cannot go any lower than your source is emitting.
I mean, it's dominant in this. They have this binary definition of when a coil is coil loss dominated and sample loss dominated, but obviously it's a spectrum. I think ultimately we can.
50-50 or
It's
so.
right now it's like 48,
okay, but you
52.
There's not much to gain then anymore.
The decreasing returns on investment there. Yeah.
Right,
I mean, ultimately you could go to 100% sample noise dominated, and that would still give you an improvement in performance because, it's the sample loss stays the same, and then you still have 50% fewer losses.
Yeah.
But that does basically restrict you to, there won't be another factor of 2 improvement.
Right.
In
the difference is about a factor 3 or so.
Yeah.
Then that's about it.
Yeah.
Okay.
Yeah.
Thank you.
Thanks a lot, Tom. Maybe we can continue because we're a little bit behind schedule.
We still have some questions. Quick question to segmentation. You put in your coil 3 segmentations.
Yes.
Did you try more segmentations? Is there a limit? Is there an improvement?
Yes, there is an improvement, not necessarily in terms of a Q factor improvement, but actually your frequency stability improves. So when you put the sample in, the frequency shift gets less with more segmentations. But every segmentation that you add, you're also adding losses in the solder joint. So actually what I did was I decreased the number of turns rather than increase the number of segmentations, which is effectively the same thing.
And capacitors, which one?
So ATC. ATC is the best, but ATC is also 60 euros per capacitor. So, if in terms of prototyping, we tend to just use Chemet capacitors with MPO ceramic, the ceramic MPO dielectrics, sorry, and those will get you 90% of the way. So you can actually do your coil optimization and your coil design with that, rather than buying 1,060 euro capacitors and just on your final one. Yeah, but honestly, don't care too much. Non-magnetic because we also have the 70 nearby. But I did test, and most of the Chemet capacitors are non-magnetic enough that you don't see any influence.
Yeah, thanks a lot. Now we continue.
Sorry. One.
No. Well, so we can talk about it.
We can talk later. Yeah. Let's do the next presentation. Markus, it's your turn.
Okay. Hi again, Markus Prier from the Forschungscampus Stimulate in Magdeburg. I can shorten my presentation a bit because there's not a lot to say for TR switches because it's a very simple component. So I make a little bit of promotion for my small tabletop system in the beginning. I can shorten this a little bit. These are the 2 TR switches. This one is for my tabletop system that we want to adapt via the AIM project for the Häuer system. And I already started this because Lukas asked for this a while ago. And this is TR switch for the Häuer magnet. You can look at it. Okay, so let me introduce you to the tabletop a little bit of hardware and software, and then to the RF components. The tabletop system contains of a magnet box. You can put in chemical test tube, and we have the control console, which uses Okra, which is the open source console for real-time acquisition, and we build our own gradient amplifier. You see the console and the gradient amplifier over there. So it's the same as a big system. Size doesn't matter. The big system is for humans, and you got this helmet, and you got the cross sections for looking into MRI images like the water in the brain. And we use chemical test tubes, and we also put water in there, and we have like 3D printed samples, and the water can flow in. And the dark part is the 3D printed sample, and the light part is the stars, the water. So it's basically the same system, just in small scale. And we do teaching courses mainly. It's the purpose for this system. This is MR System Engineering. I teach since 2019. You see students can directly work on MR hardware and software. You see in the background at the window, at the left window, you see David Schote. And on the right picture, you see Christoph Dinh. He was at Neoscan Solutions, and they tested their console for the neonatal MRI, also on a first tabletop system. We also do courses from this year for external stuff. So this year we started with Siemens developers from Erlangen. They learned at our facility how everything in the scanner works, because mostly they are only developing one component. And in a small scale tabletop, you can see how everything is together, and they have to find errors or artifacts and stuff like that. Everything on the tabletop, or most stuff from the tabletop, is open source. So the complete software is open source on GitHub, and the hardware components, or the main components, I put in a zoidmetrographics.org in blog post. So I describe how all the hardware is working. You get a zip file with all the manufacturing files and with material lists. And then also, if it's more complicated, I give detailed image instructions on how to build these components. Please free to check this out. I put a lot of work in this. Not everything is right there, because I focus on parts that I publish. They should really be documented, because most likely when you see open source, it's like, here are the files, have fun with it, and nobody explains how it works. The main components of the console is the red Pitaya. You also want to use it for the Hallbach magnet. I developed the OSI² board, which generates the gradient pulses, and it all gets together in this nice one-unit console. I developed a GUI. This is not based on Marcus or PulseQ. This is a complete UI on Python, which uses the Okra, the original Okra structure, and it got the main window, and you can have a parameters window where you plug in all your parameters, and then you can do spectroscopy, T1 and T2 measurements, also imaging, slice imaging, like from this small sample here. And that's basically what is the tabletop. And now for the interesting part for you, the RF switch. So this is the structure for the RF. The RF, you have your transmit signal, and this gets amplified by an RF amplifier and then somehow transmitted to the coil. And when you use the same coil, you want to also use it for receive. So you have some kind of switch, the antenna TR switch, that guides the received signal to the RX path. And the received signal is very weak, so you need a first stage low noise preamplifier with very low noise. And when it's done, then you can use a normal low noise amplifier for the second stage. If your RFPA has no blanking, we discussed this before on the RFPA topic, when the RFPA produces noise, even if it's not actually sending active signal, then you need a second TR switch, which is a blanking TR switch, where you dump in the receive mode the noise to a 50 ohm dump resistor. This TR switch gets controlled by a pin driver, and the signal for switching is the TX gate, or blanking signal. The blanking signal is by default in low, so in receive mode, and gets high, so 3.3 volts, CMOS, low voltage TDL. We discussed this before, when it's in transmit mode. So let's look at a single stage TR switch, how it works. It's a very basic circuit. It's from the 80s or even earlier, which is a completely passive circuit in the first stage. So you can use it like this. You have your TX port on the top left, you have your antenna port on the top right, and you have your receive port on the bottom. And in default mode, you have these pin diodes. What is it here? You have your pin diodes, and normal diodes have a positive, negative zones, and they are conductive at a certain point. These diodes have an intrinsic zone in between, so they are by default high impedance or non-conductive. So in the range of about like 1 kilo ohm. And when you imagine that these paths where the diodes are blocked, so high impedance, the received signal goes from the antenna to the RX path. To activate these pin diodes, or to make them conductive, we put in 100 milliamps of DC bias. This is done via bias T, and the DC current charges the intrinsic zone, and the pin diodes gets conductive, and the about 0.2 ohms. And you can now imagine that you can transmit signal to the antenna because the path is now conductive. There's noise from the DC bias, but this is not important that much because it's in transmit mode, not in receive mode. So it's in total a semi-active component, right? In one path it's passive. In one mode it is active. So now the transmit signal can go to the receive path, you say, but there is a second pin diode on the bottom. It's also conductive, and 0.2 ohm is like a short to ground. And the piece in the middle, this one, is called pi element, or lambda by 4 transmission line. And this is lambda by 4. It's a phase shift of 90 degrees. So imagine the transmit pulse or wave gets into this path. It gets shifted 90 degrees. This is a short, so you got high reflections here. It gets also shifted 90 degrees. So the TX signal sees itself into this path in 180 degrees. So it's destructive interference. So this short gets transformed to an open or high impedance at this point. And that's basically it. You have to tune this pi element to a Lamo frequency. It's two very simple formulas, and you get the capacitors and inductors in here. And you can also do this via a coaxial wire, but this would be several meters at these low frequencies. And imagine a coaxial wire has about 0.2 dB of loss per meter. So this would really add up. So I do this via lumped elements, as you can see on the small boards. And if you measure over this pi element with the networks analyzer, the throughput is, we have only 0.25 dB of loss. And you can very precisely tune it to 90-degree phase. We also need a pin driver to provide this 100 milliamps of current. And I came up with a very simple circuit for that. So we have a positive voltage. Then we have this regulator, which is a current regulator. It's set by these resistors here to exactly give out 100 milliamps, no matter what the load is. And when the TX signal comes here, it gets cleaned up by a Schmidt trigger and then switches on every time it's high. It switches on this optotransistor and sends this 100 milliamps to the circuit or to the bias T. In receive mode, it's not 0 volts then. I lied a bit when I say it's a totally passive device. What we send in receive mode is a negative voltage. This is an inverter here, and so these optotransistors get switched on in receive mode. So when one is on, the other is off. And with this is on, then the other is off. So in receive mode, we have a reverse voltage on the pin diodes. And this helps to suck out residual charges in the intrinsic zone. Because imagine you have a charged intrinsic zone and you switch it off. The charges will flow in the other direction, but the diode gets more and more non-conductive. So you have this decay. And you will see this when you have a transmit gate. So you have your transmit in here and you switch it off to receive. Then you got this decay in the bias current. And this is a very slow decay. And we discussed this a lot, that we want to have very fast switching from TX to RX. And by this reverse voltage, this sucks out the charges, and we got very fast switching now. And this is basically what it is. So we have a pin driver, we have a TR switch, we need 2 of these TR switches, and basically this is the complete circuit that we use in our tabletop. We have this blanking TR switch, we have this antenna TR switch. This is the first stage preamplifier. We got a cross diode before, that if we have some kind of like ringing or something, that we don't destroy the first stage preamplifier here. And we use a very simple Amazon China preamp for the second stage, because then the low noise doesn't matter that much more. So this is the complete circuit board. We have here the antenna TR switch with the 2 pin diodes. We have here the blanking TR switch with the 2 pin diodes and the 50 ohm dummy load. We have the pi elements here, the conductor, capacitor, and the inductor. And these are a combined inductor between a fixed inductor and an air conductor. And this air conductor you can stretch and bend very slightly, and by this you change the inductivity and can very precisely tune this to exactly 90 degrees with this. It's a very neat trick. And here's the pin driver. This is the 100 milliamp current source, and these are the 2 optotransistors that switches on and off when the transmit gate gets activated. And that's basically the switch. So here are the characteristics. We have 20 dB. So for the RX, we have 20 dB of amplification from the first stage. If we switch in transmit, it gets blocked of about 40 dB. And the otherwise, when the transmit path is in receive mode, is non-conductive, we have very good noise blanking or noise suppression from the RF here. And when it gets in transmit mode, we only got 0.59 dB of loss over the transmit path. We also need to look at the isolation between transmit and receive, because we don't want to damage our low noise preamplifier when we pulse in the high power transmit pulses. So we got about, this is with the 20 dB of amplification. So it's in transmit mode, it's about 40 dB of isolation, and in receive mode, it's about like 80 dB of isolation. The second stage China preamp gives additional 31 dB of amplification. So in total, the system gets about 55 dB of total receive attenuation. And that's basically it. We have a tabletop system that is a completely working MR system. It's very easy to adapt these circuits to other Lambda frequencies. We can use this for this project. We also built a lot of other stuff like RF attenuators, complete SAR monitoring system that are in the NeoScan neonatal MRI. It's a 1.5T neonatal MRI. It's a CE-proven SAR monitor that we can adapt to the system. We have, I've built a DBDT monitor, gradient enable, which is if you have water cooling on your gradients, then you need to make sure that the water cooling is always on, something like that. So yeah, with this, thank you.
Quick question. Thanks, Marcus, for the nice presentation. You mentioned the low budget preamp stage. Did you do any recent noise figure measurements? Can you say something about that? How good is it? Like, I mean, yeah, maybe the gain is amplification is good, but yeah, what about the noise?
So yeah, we tested a few RF amplifiers with the first stage and second stage. It's very frustrating to find matching low noise amplifiers, because the output of the first one has to overcome the input of the second one, right? So the scaling needs to be right. The noise figure of this China preamp, I have to lie, but it's about 2 dB or something like that. So it's like medium low. But for the second stage, it's not that important. We lift the signal from the like nanovolts from the coil to about microvolts or a few millivolts maybe in the first stage, and then we are good with the noise. So if we add noise, it's not that much as if it happens in the first stage.
We could also exchange it.
Yeah, of course, it's free to go. And I also want to exchange it in future, but I don't have the time yet.
So at the beginning of your presentation, you said, "Oh, I like that the TR switch is passive in receive mode because then I don't get noise." And then you lied to us.
Yeah.
You said,
Actually, there's minus 15 volts on there.
Yeah.
So what about the noise?
Yeah, so you can just unplug the cable, right? The minus 15 volts, and just test it with and without. It's a very simple test for the system. We figure out that the bad switching behavior, so when you don't discharge it completely, you have this kind of meta state between transmit and receive, gives much more artifacts in the images than, like loading effects over time. If you make several switchings, you got some kind of loading effects over the image. And this is way worse than the noise that gets added to the minus 15 volt. Because remember, the minus 15 volt, there's no current flowing in the system because it's in reverse direction, so in blocking direction of the diodes. It's only a static voltage you put on. And if the voltage is filtered very good, because I have this, you can see it in the console, power supply filter. When this is really good filtered, then the added noise is not that much of a difference.
Have you compared it to using a passively switched TR switch?
I never used this because I directly get set from, because I built my tabletop system from the beginnings from the Martinus Center tabletop, and they used a passive switch, and they got so many problems in, like, I would say advanced sequences, but not even advanced. So like imagine you have a sequence with slice imaging where you have sync pulses in your RF. You cut off all the, where it goes to almost to zero, then you are so low in your energy that the diode don't get breakthrough. So you separate these sync pulses in 3 pulses. So your 90 degrees is 3 pulses, your 180 is 3 pulses, and you got like these multiple echoes that will overlap and influence each other, and it gives so many artifacts. So this was the first thing we changed, because Thomas Witzer was told like, this is the most critical and annoying piece in the hardware right now.
So for us, because our coils are slightly bigger, we tend to be okay in terms of using passive TR switches. So we'd be happy to also do that comparison. I think it'll be interesting to see.
Yeah, I think it don't gives you any disadvantages. I would say it can just be better. I think so.
Yeah, and I think if Thomas Witzel says it, then it's probably the way to go. Yeah, cool. No, thanks, Markus. Thanks a lot. So we will switch a bit the agenda items. Next presentation is by Jan Frintz, who will talk on the console hardware. And maybe just one little comment. So some people need to leave to get their trains, flights, whatever, probably during the session. I would like to thank them already now. So thanks a lot for coming. Was very, very, very productive last 2 days and today as well. And I hope we can do this more often, and then with more piece by piece, more and more results. And this will be really, really cool. So have a good flight, train, car trip back home. And I'm sure we will meet again. So thanks a lot. And also, yeah, thanks for coming.
Hello, I'm Jan, and I will show you how you could build an MRI console for low field, and it's based on the red Pitaya. And all the documentation you can find here on the link. How is the pointer working? Yeah, here you have a link, and feel free to go there, and there you can find more or less anything I know about it. Yeah, the first slide is for the newcomers we always have in the community, and that's quite nice. And yeah, the console is the part that gets the some description how the MRI sequence shall look like, and it will play out the gradients and the RF signals, and will do the acquisition of the echo. So there's no way around then building or buying a console if you want to build your own MRI. And the RF part is realized with the red Pitaya, and the gradients are with the board we already know from Marcus, the OSI²ONE. Yeah, that's if you take a look at the console I built. And there's another console from Marcus here. So if you want to buy one, you can ask him, or you can rebuild this one or improve this one. Yeah, and let's have a look. What is a red Pitaya? It's a nice little computer, more or less in the size than a red Pitaya, than the Raspberry Pi. Everyone knows, I think. And the hardware is closed source. I don't like, but I understand. They want to make money with it, but it's for a fair price. And
can I just ask, the 12 and the 14-bit were open source, right?
As far as I know,
they were never open source?
No, but they supply you some schematics. They're not complete, the schematics, so some power management stuff or some parts of it are closed source. But you could rebuild the system from the schematics that it's software-wise completely the same. But I don't know whether you're allowed to or not. Haven't dived into the license. But what is really nice is the vivid community around the red Pitaya, and whatever field you're looking at, there are people playing around with it. And it has a big SoC on it, so there's an FPGA and ARM microprocessor on it, and in our system we run a Linux on it, and it's communicating with the FPGA to share some memory, and to the FPGA there's attached some RF analog digital converters and vice versa. Yeah, the OSI² is an 18-bit DAC. We already heard it before, and it's designed by Marcus, who's already here. So thank you for this nice board. I like it. And yes, the third part is a power supply. So for my system, it's really easy. There's one stage from the mains to 24 volt. And from 24 volt to all the different powers we need for the two PCBs. So for the OSI² you need 3 different voltage levels, plus minus 15 volts and 3.3 volt. And the red Pitaya needs 5 volt. And there's some filters on this PCB, but there are not many parts on it. So you can solder it in less than 2 hours, even if you're unexperienced in soldering. Yeah, basically that's it. And the documentation you can find here. And feel free to ask any questions. Yeah. So what do we need to progress on and what's not nice on this console? First, the SD card is inside the console, somewhere hidden. The OS, the operating system on the red Pitaya is like on a Raspberry Pi stored on an SD card. And if you need to reflash it, it's not really handy to disassemble the whole console, then open it, get the SD card, plug it in again. So we want to have it accessible from outside. And I already changed it in the GitLab files, but unfortunately the holder is not matching the cable for the extension, but there's an issue in GitHub, and when I have time, I will fix it. The second thing that's not nice on this console is that there's no dust cover around the red Pitaya connections. So maybe someone can make a nice 3D printed cover plate, or you can put a red Pitaya more inside and have connections to the outside. But then you have more cabling and more connections that are not good for RF and reflections, but yeah. Feel free to give some contributions to it. Yeah, another pitfall that's easy to fall in is if you download some PCB models. So when you want to get finished fast, you're likely to download it from the page of your contributor. And sometimes they link to you to SnapEda or whatever. And the license is not is sometimes that you're not allowed to share it somewhere else, but we want to share our libraries with the projects. So be careful about it. I stumbled upon it and yeah, not good. So we decided to start our own KeyCut library for all OSI projects. So any PCB I will build, I will contribute every part in the library and it will be stored here. And then any PCB can link to one version of this repository, and then anybody can open all the files with only one part library. So I highly invite you to take part in that project. And if you use other PCB tools like Altium or whatever, we can open another repository for that too. But I like KeyCut because it's open source and free, and you all can open the files and change it. Altium is for many institutes too expensive. Yeah, the OSI² ONE is really nice, and thank you again. So you can download some parts of it, but I got confused when I read the license. So basically on the internet page, there's written that we need to cite the creator. So I think nobody will do plagiatism or something like that here. And we like to cite all the creators. And it's only written what I'm not allowed to do, like remove the logos, but it's not written what I'm allowed to do with the stuff. So am I allowed to re-engineer it and modify it or whatsoever? I don't know. And I'm not a license expert, so I'd like to start a discussion here. Nice, I like it. And please send us an email, then we will link to the single source of truth. Yeah.
Yep, that suffices.
Git allow you to already has the licenses. You can just select
as well, yeah.
But Martin will help you. The quick answer to is always no. You're not allowed.
Yes, but I know that the intent of Markus is to put it open source and to provide it to the community. So that was a point where I got confused, but I love it that you will change it or willing to change it, and this will help the community a lot.
I wanted to make a mention, but it's just a geeky note, so please keep on.
Yeah, yeah, and that was it for my part. So yeah. Any questions?
So I can quickly add to the source files. We discussed this before. I asked for this before. The thing is, with the source file, it's in KeyCut very difficult, because if you make a custom footprint or a custom 3D model, it's all linked locally to some folder on your laptop or something like this, and this will be destroyed if you export it to like GitHub or something like that. So even if I upload this, I have to make sure that I add all the custom footprints, that I don't forget anything there. And this is really a pain in the ass, because KeyCut don't track this anyway.
Exactly, that I have one folder with the library, and then if we change the project, we just check out the commit where we know that the parts are right and the history is right, and then we can go and develop there.
But this is not really linkable, because when you download it, then you have to, in KeyCut, address all the, then it makes all like black boxes and question marks, and you have to relink all the like 3D step files for the 3D models of the.
Can't you link the whole library just once?
I don't.
I'm not a
I don't think
KeyCut expert, but in Altium you can.
I can suggest to make a connection to the MNT team. They developed a laptop and their own motherboards and things also in GitLab, and they also wrote some of the KeyCut modules themselves because they also ran into issues. So maybe they can provide guidance.
Can you link it also somewhere?
Yeah. Do we have minutes? Or
Yeah. Yeah, that was a little bit unfair. Yeah. So, well, this is a direct connection. I write you an email. Okay.
One more question. I'm curious about the interface. How is it implemented, and what types of commands does the board accept?
I didn't dive into it because there will another talk about the software, which is called Marcos. But on the GitLab folder, there's also a link to all the stuff and also a quick start guide and so on. So I recommend you to go there and follow the instructions, and there are also bombs with links. So you just need to order and follow the step-by-step guide, and then you.
So maybe I can get a small comment on this. So the OSI² ONE board gets supplied by SPIBus. This has a sequencer in the FPGA Verilog HDL code, and they can manipulate like the SPIBus, and this gets all like addressed in the server, in the C server that runs on the microprocessor of the Red Pitaya, and there you can say like do this voltage at this with this address of the DAC or something like that.
Oh, sorry, I wasn't.
Yeah, we're done. So I'm waiting for the next talk.
Oh, yeah, okay.
No, just a second. Just one comment. So Benjamin was supposed to give the talk on Marcos, but unfortunately he can't. Just this comment, and then to the coming back to the console hardware. And we talked last 2 days about the other fancy consoles that we are working on, but just focusing on this one here. Because this will be, let's assume for now, this will be the console hardware that we will be building together with the system. What else do we need in terms of outputs, inputs, when thinking of the specs?
One thing I would really like to push forward a little bit is using the standard input PyPulseq. Because then we can also compare other hardware pieces, other consoles, and yeah, we have like some standard that we can share.
Yeah.
Because I just know from the console that Jan just presented, I think also the guys from Valencia in the back can probably confirm that it has its somehow own description of the sequence, which works well with the Marcos server. But yeah, as I said, for comparison to other systems, to other consoles, would be nice to have that standard.
Yeah, so
the Marcos
is PyPulseq compatible in principle.
Yeah, I know.
We didn't test it yet.
But then, okay, then we should at least make sure that there is. So from the last time I checked the GitHub repository, it was not clear to me which version supports the PyPulseq format, because the most recent one didn't. There was some. So at least we ran into problems when we tried to interpret the PyPulseq files.
Yeah, this is something we have to check with Benjamin or with Vlad, and talk to them directly actually. So this is still on the to-do list. We cannot fix this probably now, but so assuming that it's PyPulseq compatible, then we have our Red Pitaya, we have our Okra, so we have. We probably don't need more than one transmit channel. We have our to receive channels. We have our TX gate from the Okra. We have our 3 gradient channels, even 4 from the Okra, in case we want to have some extra. So we can specify that. What else? Is there anything else that we forgot? Or maybe also a question to Valencia, like what are you guys? Because you also use the Red Pitaya and Okra One. What are you missing anything, or what do you have that's might be useful for this project?
There is a new Red Pitaya for a few months now that you can daisy chain. So you have a master-slave daisy chaining of Red Pitayas, and then you can have multiple receive ports. So if this is wanted in the
Vlad is
future.
working on implementing this in Marcos. So it should be, I don't know, it's never infinitely scalable, but it is scalable to multiple channels. Yeah.
But
Vlad Nignovitsky, who
I know about this project. I was just thinking. Ciao, Vaki.
Ciao.
I can say bye. On the GPIO pins, this is maybe important on the red Pitaya, that there are some free at the moment. The red OSI² ONE doesn't use all of them, even if it's used the whole connector. But these can be used for external triggering or something like that.
So we have here some GPIOs to the outside. So where we have a better picture there. You see there's a cable, and here you have this little connectors you can plug anywhere, and you get all the signals for probing or some future stuff. What I don't know what you will develop on.
Yeah, can you maybe show the front again, the front panel? Yeah.
So here you have 8 connectors, and you're free to play around.
They're I/O or only I or O?
Wherever you want to connect it to.
Okay.
So that's just the standard DuPont.
It can be used for both, for all of them. Okay.
You can also use it for slow analog stuff. So there's some low frequency analog inputs on the red Pitaya too.
Sorry. Are those connected for TTL outputs? Did you say?
It's connected wherever you want to connect it. I'll show you on the other picture again. So here's the cable coming out, and there are DuPont connectors, so you can plug them anywhere on the PCB.
You can get some TTLs and all that to activate.
It's CMOS. So low voltage.
I say that because, I mean, before you were speaking about if it is necessary to use auto-tuning or not, and we are using auto-tuning, but we control with an Arduino. So if it is possible to do directly with the OSI², it will be an advantage for us. Mm-hmm.
Yeah, that's a good point, yeah.
At the moment, the remaining pins are reserved for a GPIO expander chip. So this can be also even more expanded.
You can connect the cables to one of these connectors. So the one connector of the red Pitaya is connected to the OSI² ONE board, and the other connector here you can plug your external connectors to. And it's you who decide where you plug it in. So.
Do you know, or does someone know if the new red Pitaya is the same footprint?
They did a real mistake when they changed the clock to this 122 point something hertz. So in the newer version, they correct this back to 125, that you got this 7 nano seconds of stepping.
And how far along is the Marcos implementation for the new version?
I think Vlad has retreated into his cave to do the programming, so he'll come out when he's ready, and we'll all be amazed. So just to clarify, Vlad is only working on this, I think, one day a week or half a day a week at the moment.
Yeah. No, just out of curiosity, because if there's one person working on it, and we need to make some decisions now, so it's always risky.
That's true, but I think for now, the immediate, I don't think it's an immediate cause for concern, because the EMI, we're not using the EMI at the moment, and I think it's also very much a personal opinion, and happy for others to disagree, but I think the better option is to shield the body. So then it's also not immediately necessary. I think it's one of those nice to haves, but it's definitely not we don't desperately need.
Yeah. So for the specs, we can stick with the 122 16-bit version, and
Yeah, for now, yeah. The Marcos only works on that version.
Yeah,
that's
exactly.
important to know. It might work on the new one with the 125 megasamples. But again, that's something we'd have to confirm with Vlad.
Yeah.
Because it definitely did break from the 12 and 14-bit version.
Okay, cool.
One question that just came to my mind. Does anyone know how deep the Pitaya was modified by this Marcos build? Like, are we still able to use the network functions of the device? Or like, would it be possible to connect it to some, to internet?
So the data connection to the Red Pitaya is via the Ethernet port on the Marcos. Other than that, it has this flow-based Okra, but it's not really Okra anymore. So I think it was a full break from Okra. But to what extent it was modified, I think Benjamin would know that, but I think the real person with that knowledge is Vlad.
Yeah.
Or the papers. Sorry, there are a few publications now describing the Marcos system in quite a lot more detail.
But it still uses the FPGA Verilog code and a server in C. Is that a question? Yeah.
I don't know. I think
It does use it.
I think so, yeah.
Yeah.
Okay, great. So thanks Jan for the presentation. And then we continue with David.
Yeah. Hello, everyone, again from my side. Really nice to have the whole community in one room. Also, hello to the online people. Today I brought my colleague Christoph next to me. And me, we are going to present Scanhub, which is an open source acquisition platform. And before we go into the details, I would like to show how or where you can find all the stuff that we're going to present. We have an organization on GitHub where we gathered all the repositories that you would need to run the example that we're going to show later. And via this QR code, you get to this page and can access all the repositories and the code. To understand Scanhub, we first brought a diagram which we found in a publication from 2020, and it shows the conventional radiology workflow. So you have a modality, you have some DICOM router, PAC system, and the workstation, and connected to the PAC station are maybe some servers for AI training, AI models, and so on. So it's quite a complex infrastructure. And the thing is now, if we consider different facilities, each needs to implement such an infrastructure. So there is a lot of overhead, but there might be facilities which are not able to afford such an infrastructure, because first the investment is quite a lot, and there are like running costs, there's maintenance effort, and so on. Or there might also be facilities who are just too small to establish such an infrastructure. And even if you consider facilities that have it, it's still hard to compare different facilities or institutes against each other. They might have different or slightly different modifications, and thereby it's also really challenging to introduce standards. We now had the idea to centralize this and merge everything on one platform, which we called Scanhub. And the key components of Scanhub would then have everything you would need to perform such a workflow. So some patient management, acquisition planning, data store, visualization, and also integration of AI workflows. In addition to that, we identified that there are some aspects which have not even been possible without a centralized approach. And these are mainly the scalability, standardization, transparency, and compliance and security aspects. Talking about the scalability, that means, if we want to modify the pipeline, for instance, add new AI models, new modalities, new applications, that's relatively simple because of the modular approach. But also, if we think of maybe computational resources, which become more and more expensive since our AI models are growing, there are more and more parameters to train. So you need quite expensive hardware, and sharing this in the community by cloud computing is quite efficient. The other point is standardization. So as I already mentioned, it's really hard to compare different sites against each other if they have like some different infrastructures. So having everything centralized, we would now be able to introduce some certain standards and apply them to all the different pipelines. In addition, we have full transparency since the code is open source, and we are able to integrate all the different needs, requirements from the community. And last but not least, the security aspect. Just right. I think recently the EU also published some new regulatory requirements, and one aspect of it, for instance, would be the AI model drift that you need to monitor somehow. And how would you do that if you have a model which is distributed over different sites? That's rather difficult. So with this approach, where you have everything centralized, it's much easier to fulfill these requirements. Now I would like to hand over to Christoph, who's talking a little bit about the architecture.
Thank you, David. Also, hi to everyone, also from my side. I'm happy to take you a little bit into the machine room of Scanhub and telling you basically how we approach fulfilling those requirements, high-level requirements David just showed. So before we dive into it, while we're designing Scanhub, we had several key principles in mind. So first of all, the main principle was we didn't want to reinvent the wheel, which I think happens rather too often, and you can actually often observe it. So we want to basically, in our solution here, want to rely on existing open source solutions and standards as much as possible, which allows us to focus actually on our core domain, which is MR imaging and reconstruction and AI, so you will. And we achieved this. The second one, of course, which also was laid out by David, is we want to be as scalable as possible, meaning also scalable on-premise and on cloud setups. So, and how we achieved both is by a strong modular setup, which you can easily guess by just looking at the picture. You see all these different main components there. So it's very modular and also only loosely coupled with an event-driven design. So there you have some of you which are a little bit into this cloud architecture and these new designs. You are having these REST approaches and also these event-driven designs as two main ideas how you can call services across the internet. Yeah, and this modular design allows us to tailor components basically on demand in. And in the center, you basically see the core components of Scanhub, which is study, acquisition, and workflow management. On the top, you see basically ScanUI. This is a UI component which integrates with study management, allows the user to plan, trigger, and review acquisitions or acquired records and images and so on, and do the idea is then basically even doing diagnostics on it in the long run. Both has been written in React. So both has a front end and of course a back end. The front end is written in React and the back end in Python. Scanhub is also designed with the idea to be a multimodal acquisition system with a modularized device integration. Which in the end not only allows to integrate with different MR systems / simulators, it shall also, for example, integrate with EEG, ECG, and so on. So really with being a multimodal platform. Currently, we are working on a spectrum console integration or a spectrum card-based console integration, and as well as a simulator integration using Coma MRI, which we saw also yesterday in the workshop. So we saw some results presented by a colleague. So we spent some time finding the right approach for a flexible performance reconstruction and post-processing workflow solution, which at the same time serves basically and is flexible enough for researchers to try the latest state of the art, and at the same time fulfilling basically the requirements for approved processing steps for running in a medical device. And there we came up with a hybrid approach incorporating MONAI. Since this is a very loosely coupled integration via a message broker, we also allow for other workflow engines, and those can be easily integrated as well. Yeah, and since we aim to have an interoperable output formats like DICOMs or NIFTY, we can dynamically integrate with different PACs and storage solutions, which you can see on the lower part of the. So right, we tested it with OwnTech, but we think since the DICOM web I think is also supported with XNAT, there should be not a problem to also incorporate with XNAT. Just a hint here, maybe you see we also fostered here yellows and blue boxes, and you see basically what we consider part of the technical documentation of basically the system, and part which are neighboring systems, and I documented somewhere else. Okay, and then on the next slide, we will see we decompose our system a little bit further. I will not go into the very detail of every component there. So you basically see that we have a layered design. So we have the Scanhub core domain. We have then underneath, of course, a persistence layer. And what often is forgotten is the governance layer. So talking about OutC and OutN, so basically authorization and authorization and authentication. So meaning, so identifying who you are, but who you are doesn't tell you what you can actually do. So it's good for a system to know that I am Christoph sitting in front, but what can actually Christoph do? Do you have the role of actually accessing those data you are allowed to? So there actually you need to be also quite some work needs to go into this part, which is not so sexy, let's say, in terms of bringing the system forward, but it's a necessary component. Okay, and on the next slide, we look basically on the user journeys. We identified now 3, which we will very quickly run you through. So we have the medical clinical professions interacting with the UI. On the left-hand side, we have the device interface where we want to show you how we integrate with it. And on the right-hand side, we have the researcher developer workflow, how we actually can build up new workflows in Scanhub. The first 2 workflows are going to be taken over by David, and with that, I'm happy to hand over back to David.
Okay, yeah, as Christoph just told, one of our user stories is the medical professional. So here's a quick teaser. Later, we're going to show a more lively demo. So what you can see here are basically 2 views of our user interface. So on the left side, you see how you can basically plan an acquisition. So we implemented an acquisition, a study browser, more or less, where you can specify device, the sequence, and some meta information. And once you acquired your data within this interface, it is stored in the DICOM database. And on the right side, you then have a web-based DICOM viewer where you can show, annotate, and work with the data you just required. Yes, and another part of the system then is the device. Therefore, as we also already mentioned, we are currently about to integrate the first real MRI machine. In general, the device connection is realized as follows. So at Scanhub, we have this acquisition layer where we have a device manager and an acquisition control. And on the device, we have the counterpart. So we call it Scanhub SDK. And there you have to fulfill a relatively simple interface, I would say. So first you need to register the device. You have to communicate the status of the device. And then there are basically two functions at the moment which start and stop your acquisition. And on this console application, we then further, in our case now at PTB, have three components which process the sequence and organize or perform the transmit and the receive of the signals that you send or get from the MR machine.
Yeah, now to the last or to the exciting, very exciting part, I think, for most of us is the development of post-processing and reconstructions. On the next slide, we can see basically, so first of all, how do we actually, I mean, everyone knows how those scripts look like and how we actually come together there and can standardize, quality control those things and so on. So with these points on the side, so we need to find somehow a common standard on how we actually want to go ahead with workflows. And we came across their Monai. They are aiming, which we can actually see on the next slide, that they come actually with a very bold statement. So they want to become the de facto standard for developing, packaging, testing, and deploying and running medical AI applications. AI is just in brackets, so you can actually run every workflow step there and bridging basically the gap between research and clinical production. So you might think very bold statement, but if you look a little bit on the consortium who is leveraging this, you can see on the right-hand side, you have NVIDIA. I think Philips is even also part of it, and they are doing this all under the Apache 2.0 license, and they do this actually also with a technical documentation. So they have SAD, SDD, and so on. So they are doing this rather professional, and they come up, for example, with a own workflow specification language. So, for example, here you can actually see a workflow which is very general described. So you have as an input a DICOM, which can in this case even be a multimodal DICOM, and you have first a DICOM identifier, what kind of modality you have. Is it a CT, an MRI image? Then you can even interfere and bring in processing steps which require hands-on clinician reviewer. For example, if you look at the CT part, there is a workflow for detecting fracture. And so you could actually think about a workflow detecting hydrocephalus and so on, right? And in the end, before actually the diagnostic goes out, you have in this workflow even a approval step included, like from a clinician there needs to say, okay, what the AI said there it was correct, which I think needs to be, it's still the case that the doctor has the last say. Okay. Underneath you see an MRI pathway and so on, and this looks rather complex, but it's actually rather simple and well designed, which we can see on the next slide. So this is, for example, a workflow where you first say, okay, what is the data origin? It could be my scanner, could be our Scanhub. Where is the export destination? It's in the end a PAC system. Is it XNAT and so on? And then you have some templates for your tasks. So you could even invent new tasks in there. And there you have the Monai application, or we have also a Scanhub application there. And then you have even here the endpoint for the clinical review. And then you have actually the tasks underneath where you have the input router, and then you have the MRI detector here in this case, which detects whether it is a T1 image, and then you go further here with a body part analyzer, whether it's brain, and then here in this example use case, when it's brain, it directly goes to the clinical review stroke detection. So this is how they envision and try to be generalized in the big picture, basically all clinical workflows. And then you have these single steps. And in these steps, you have actually these Monai applications or Scanhub applications, so containerizing those applications in a standardized way. and it's rather simple to do though. So it's also very nice. You don't need a very complex cloud environment for this. You can even run this on a local, if you have the Monai SDK there, you can just run it even locally and debug it. So on the left-hand side, this is actually the whole application here for a Cartesian reconstruction, which in the end hands you a DICOM, a package DICOM, and you see most of the lines is actually comments, which is actually I think a good habit. And you will see actually these 3 lines here in the compose are where you see the application, you even say the pip package is what you need for it. And then in the compose part, you see basically what design even a workflow in the application itself. So you will see first you have a Cartesian reconstruction, and then you have the DICOM operator. And the right-hand side is probably too small. It's just for comprehension. You see basically up there is this reconstruction. It's a simple FFT reconstruction, and underneath we have implemented a DICOM packager using PyDICOM. Yeah, and I think that's it for now, and hand it back to David.
Yeah, from this let's say deep dive, I would like to go back to a more high level part of our presentation. Now I would like to show you some demo. So here you can see the user interface in action. You can see how we navigate through our study browser, view a sequence that was just assigned to a new acquisition job. Yeah, you can zoom in, you can check out the details of your MRI sequence, and then you can acquire it. And what you see in the back, which is now in the front, is our simulator. So a very simple piece of software which generates a case base for us. Now we are having a look at the Docker container, and you see that a full DICOM is created. And if we now want to check it out, we go to our DICOM viewer, select the job that we just acquired, and then you have the DICOM there. So the end-to-end workflow pipeline is functional. Yeah, and if you now wonder how you can try it out yourself, this is our installation guide. So it's also rather simple. You have to clone the 3 repositories that I also showed in the beginning. One is for the core, one is for the user interface, and the third one is our simulator device. In the core and UI, you have to execute the Docker compose, and the device simulator is also installed relatively simple. When everything is up and running, your Docker environment would look something like this. So there are a lot of containers, but as you can see, this was running on my local notebook. And yeah, I would say the resource consumption is quite okay. So it is able to set it up locally, use it. But of course, since we have all that container ready, we can also put it up to the cloud. What is, I think, a relatively nice approach. Yeah, and thereby we are at the end. I would like to thank the whole team. Also, thanks to Johannes, who unfortunately could not make it today. Here again, the QR code to our GitHub repository. And in case you have any questions, we're of course happy to answer them. Thanks.
I have one question regarding the Mona step. Yep. Has this to be a Python code, or can it be another programming language?
So you can build up an own Monai step in there, and use not the Monai deploy SDK. The Monai deploy SDK is written in Python, but when you trigger, that's the nice thing behind there. So they have a PyTorch and a graph behind it. And as you saw, NVIDIA is there, so they are kind of compiling this Python thing and optimizing the code in a it's in the end a rather big repository which comes a container which comes out. I think it's about 15 gigabyte, but they are having it then very optimized, which can run really on a GPU cluster and even having heavy GPU use. Right, but you are absolutely free to register any other application. Yeah.
Reload. Yeah, just in case you want to have some more documentation, we also started to document the platform. You find this.
Either you push it or what? So that should now work.
Perfect. Thanks, Martin. Yeah, in case you want to have some more documentation, we started that on a GitHub page that we also link to the repository. You can find all the API documentations, but also some technical documents that we just started. And of course, it's work in progress. But I think it's very important that we started early, and yeah, we're happy for anyone who's who would like to contribute to that.
So I have a question. So this works with the Spectrum cards, I assume. Is that sort of?
That's also work in progress. It's supposed to. So once we have the Spectrum card running, we would like to add a link to that to run, to drive the Spectrum cards.
So in 3 months, when this is all up and running and working, no pressure, I roll up to my hospital, we buy some Spectrum cards, I install this on our system. Is my METC, my medical ethics committee, are they going to have an aneurysm when I try and tell them, hey, this is the software, it does everything, none of it is CE certified? Or what is the real world? What can I realistically expect in terms of sort of that regulatory side in the near future? Because even for healthy volunteers, I would have to get the software approved.
So maybe I can take this. You're using at the moment your own RICO code.
Yeah,
and that you can do that. But you're doing it.
This was on a serious note. This is all specified in the in our medical ethics application. Was also the version control of the software and minimum guarantees, but also that this is definitely not a clinical application. But if it's there's also for our medical ethics committee, something that is developed in-house is treated completely differently from something that is brought in from the outside, even if it's not purchased, even if it's just downloaded, it is treated differently if it's from an external source versus an internal source.
But wouldn't be because the software can still use your reconstruction code in a container,
but it can also
right?
drive hardware, and I think that's the real question.
So to answer this, I mean, we developed this software so far, how we envision a good acquisition software. But what was missing, kind of for technical documentation, especially, was what we discussed like yesterday, the intended use and having basically requirements. And now within this project, we are developing basically a technical documentation file, right? And since we are a part of this project, so I think you could just use the software within the boundaries of this project, not considering us like external.
So it was
internal. Yeah,
it was deliberately. The question was deliberate to provoke a little bit. I think we would have to, even if we buy the Spectrum cards, we would have to redo our METC application technically in order to be able to use the Spectrum cards because it's different hardware.
But no one prevents you to integrate also with OCRA.
No,
or other.
Sure, but I think
the SDK and
As far as I know, there's no limitation in the ISO norm for certifying medical software. There's no specification which programming language you use or a special, let's say, standard like MISRA for other automatic software in the automatic industry. You just have assure some guidelines that you guarantee. So if your software has a certain fulfillment, then it can be specified or
I
considered as medical software.
think Wouter, I look at you because of this is somewhat similar to the patches issue on the 7 Tesla system, and how is that handled in our case? So we have a 7 Tesla scanner, and if you develop software for that, there is now with MDR that's come in, the regulation on that has become significantly more stringent.
Yeah, it's officially like the scanner is CE certified. As soon as you load a software patch, it's not anymore.
Yeah. And then,
so it has to be stated in your application for a medical ethics committee.
And the software has to be examined by engineers and things.
But this software is directly accessing hardware. And in this particular case, if you have the control part separated over PyPulseq, for example, I mean, it's just the image reconstruction part and image viewing.
But I thought you were showing that the data acquisition itself could also be controlled from within the Scanhub environment.
Absolutely, that's the idea, and we have there 2 connections. So one, so also for safety considerations, one is basically for triggering the actual acquisition, and then there's one monitoring connection, which is realized via a continuous real-time or more or less real-time stream, like a WebSocket connection, and it's also underneath HTTPS, I know, so not really, but in there we are monitoring the status, error, and so on. So that's the plan, and then you can have basically SAR monitoring and all those kind of critical things, and this is basically then about to grow into the acquisition control.
Because then that's interesting, because then you lay the onus on safety on the developer of the hardware control logic, and you don't, because you're not touching that, then it's their responsibility to sort that out.
Exactly. So yeah, that's maybe also important to mention. So it's like what all would be presented does not directly control the hardware. It just speaks to a device which controls the hardware. So apart from that, we would have like a console application which processes the PyPulseq sequence and directly speaks to the hardware cards, which replay then some sequences. But this software part only receive like, okay, now do something. It's like a button you press, and it transfers back the data that we require.
And your expectation is that the regulatory people are okay with you sort of.
Yeah, it's about segregation, right? And I think what regulatory people, which I encounter, are very happy about actually segregation. So saying, okay, this console device is maybe a class C, and then all the nicer rollout visualization and post-processing part, we can actually downgrade or mitigate to a class A or B. And we have much less documentation work there then. But also looking a little bit for my researcher heart, so you heard this multimodality, I would like to see that's also at one time going together with electrophysiological acquisition together with MRI. So then we are talking a little bit different, but right now this is the idea to go fast through the door. Yeah.
Is there any more question to David and Christoph?
Are your DICOMs valid? Like, I can upload them to any packs I want without people complaining, because you have such stringent regulation on what a DICOM can be in terms of unique ID and the insane amount of things that you have to go through to get those.
So having we don't have a DICOM conformity statement yet. If you are referring to this statement, what we do to be DICOM conform. So right now you saw this is like a exemplary thing where we just quickly filled in the text for an MR for an MR modality. What we did to be then DICOM conform is running it through a grassroots DICOM, which is also open source. I think most of you know it, and convert it from our quick DICOM and convert it again to a DICOM with P10 headers, so that it's really then DICOM conform to this thing. But it's what's all in the text. No guarantee right now, but I getting a DICOM conformity statement is of course aim at the end.
Yeah, thanks a lot. It's a really cool software, and we are looking forward to.
Well, wait, there was a hint in the chat that there's a section in the IEC regulations on software of unknown origin or something.
unknown prominence, like SOUP or OTS. So yes, so I think we are to this project and hopefully to the whole scanner are not unknown. So we are a part of the system, I hope, in the end. So we would like, I don't know how the tech doc will lay out, but I would think that we have a acquisition software together with it and stable it together, and when we hand it to MDR. But whoever asked this question, so of course in the software architecture design description, you are having an OTS component part, which is like, I think, one of the later chapters where you have the off-the-shelf software and FOSS. And there we need to actually fulfill all the requirements on each external package, and where we also then, based on the requirements and the classification of those components, need to do the testing. But a short answer, I would not consider Scanhub as off-the-shelf or software of unknown provenance.
Okay, yeah. Also welcome from my side. Very happy to give this last talk before your weekend. And we heard a lot about PyPulseq already. And now I will dive a little deeper and talk a little bit about PyPulseq, and especially about the Python version called PyPulseq. And as far as I know, Maxime already presented the PyPulseq idea, and basically, I guess, more or less everybody knows about it. Still, for those who are not familiar with it, a short recap. So the state of the art in the pulse sequence development is that we have to implement our pulse sequences for every vendor, and not just for the different vendors, but also for the different software versions of the same vendor. And this is very complex and especially very time consuming, as probably everybody who worked on the pulse sequence development for one of the big vendors can agree. And it's also a very huge burden for multi-site and multi-vendor studies. And as Maxime stated it, from a computer scientist point of view, what we would like to do is introduce this additional hardware extraction layer so that we can use one common pulse sequence format, and then use this format at all the different scanners from all the different vendors and all the different software versions. And well, in general, this should be possible because pulse sequences are very simple. Basically, it's just like a sequence of different events, RF pulses and gradients that are repeated all over again. And so this is why actually something like PyPulseq can work. And here's a short overview over the framework. So the idea is that we have hardware agnostic, so hardware independent, high-level design tools. First, it was implemented in MATLAB, but now we also have like the Python version, PyPulseq, and also other tools like Toppy. And with these tools, we can also create hardware agnostic sequence files in this PyPulseq sequence format. And just in the very last step, these hardware independent sequence files can be used or interpreted at the different scanners using these different interpreters. So a very schematic view. The PyPulseq framework consists of these three puzzle pieces, which is the programming environment, the PyPulseq file, and the interpreter module. And I will not go into detail of all of them, and especially not in the detail of the PyPulseq file and the interpreter. I will not discuss it all, but mainly focus on the programming environment. Still, to get an idea what PyPulseq is and how the files look like. So the idea in the PyPulseq sequences is that we represent these as a concatenation of non-overlapping blocks. And every block can contain different events, and events can be of different types. So if you have a look at this graphic here, so the first block is the part between the first two dotted lines, as you probably have guessed. And we have a gradient and an RF pulse here. So this is a slice selective RF pulse. And then the next block is just gradients, so rewinder and, for example, phase encoding. And then the third block, for example, the gradient and the ADC. So this is our ADC acquisition. And well, after the fourth block, then everything is repeated again, as we usually do it in pulse sequences. So one important thing or special thing is that gradients don't have to start or end at 0 between these blocks, so we can have gradients that exceed the block boundaries, which is especially helpful if you have more sophisticated or complex sequences. So this is just a very basic sketch of an FID sequence in PyPulseq, so you don't see much in there, but you can get a basic idea of how these sequence for PyPulseq files look like. So the idea in general is, well, of course, it's machine readable, but also kind of human readable. And we have this important table of the different blocks here for the FID sequence. Very simple. The first block has an RF event with ID number 1. The second one has a delay with ID number 1. And the third one is just our ADC with ID number 1. So we have different IDs for the different events, and they are specified at the bottom of the file. I'm not going to show it here. So if you're interested in this, I can recommend to go to the official PyPulseq homepage. So this is the QR code you can scan. There's also links at the end of the presentation. And there you find all the links to the PyPulseq sequence file specification, to the GitHub repositories, and so on. And now to the PyPulseq part, basically, so the programming environment. And I will focus here on the Python version, PyPulseq. Of course, also open source. So if you scan the QR code or go to this GitHub repository, you will find everything that you need. And the nice thing, it's also available on the Python package index. So in principle, you can just install everything using a simple command, pip install PyPulseq, and everything works. You might have guessed that it's not the case as it is. So unfortunately, there are some compatibility problems with some packages that we use, especially the zigpy package. Still uses deprecated D types. They fixed this a couple of months ago, but they didn't release it. So we cannot use the version of zigpy which is available on PyPI. No, it's the warning existed for like a year, and now it really doesn't work anymore. You can limit the NumPy version to an older one, but it's actually kind of complicated because if you install it like this, it doesn't run, and if you try to reinstall an older NumPy version, it also doesn't work. So the way to go currently would be either to adjust the NumPy version during installation, or simply use this pip install and directly from our PyPulseq branch, where we put the zigpy repository as dependency. So this works if you install it from Git. It doesn't work if you want to install it from PyPI, because these direct links are not allowed. So unfortunately, currently, you have to install it like this, or find a workaround, which is actually more messy than I would have expected. But if you use this way to install it, everything should work. And just a few comments on like current developments, or maybe a few words before. So it's basically a community-driven project. So maintainers and contributors are split. It's not too many, but we are split all over the world. And current developments are actually there's an open pull request. This is why I included here to improve the performance. So this is from a guest scientist who's currently in Freiburg, and he managed to speed up a lot of functions. And actually, he wrote me yesterday that this, for his complex sequences, leads to an acceleration factor of about 10 when creating kind of complex sequences. For the average one, still factor 3 to 4. So if it was too slow before, now it's faster. But more important, maybe after this year's ISMRM, we had a meeting at the Emrasont, at the hackathon, and we decided to refactor the whole package. So transition to more modern or professional Python package. currently, more or less all the events are just implemented as simple namespaces, which can lead to many user errors, and it's also not that nice for debugging. So the idea is to switch to data classes, and we tried several things, or I tried a lot of things using the Python data classes, also Pydantic ones, or the data classes from Pydantic. Nothing is really as I would like it to be. So basically we will, I guess, everything or implement everything on our own. But this is the idea, and there's also already open discussions and even a branch at the GitHub repository. So this is something that we plan to do. As always, takes a little longer, and especially takes longer to start this. But I really hope that we can make it soon. Well, when we do this, we also, of course, want to put some effort into more comprehensive CI/CD system, automated testing, reporting, and so on. All with the goal that it's easier for the user to actually use the PyPulseq tool, and in this way also try to help the community grow. So again, if you're interested to contribute, feel free to join the PyPulseq repository. In the discussions, you will also find a link or description how to join our Slack channel. So this is also a way that how we communicate. And last but not least, I would like to just show you a simple example. So I wasn't sure if this is of interest or not, but maybe just to get an idea how pulse sequence programming in PulseQ looks like. This is a mini gradient echo sequence that I wrote from scratch. So basically what you have to do is import, of course, PyPulseq and also NumPy that we use for several things. Then in the beginning, you have to define your system, or especially system limits. So maximum gradient, maximum slew rate, and so on. And then we create a sequence object, define some parameters for our sequence, like field of view, our metric size, slide thickness, and the relevant parameters for our sequence, in this case, flip angle TRTE. Then basically for such a simple sequence as a gradient echo, what we just have to do is define our RF pulse, and this is done in the upper part here. And one nice thing here is that you can actually provide the information about slice thickness under the system and activate this return gradient or Z gradient, and then what you get out is not just the RF pulse, but also the corresponding slice selection gradient, and also the rewinder that you can use later on. Then what we also need is, of course, our readout gradient and ADC and so on. So this is calculated in the lines below, and then we calculate our timing. So we want to have a specific ETR. Of course, we have to calculate how long our delays must be. And then this is the last part of this example. It's adding all the different blocks or events to blocks and blocks to sequence. We assign the right phase area or area of our phase encoding gradient, then add our RF pulse together with the gradients and so on. And in just like 6 lines of codes in this loop, we can add everything that we need to have a running gradient echo sequence. There are some additional functionalities like timing checks, at a plot functionality, and then we can just write the sequence. And this is the output of the plot. So you can see plot of the ADC RF and the phase, and then also the 3 gradients. And looks like we would expect it to be. And in the talk before, we heard about the spectrum card. So this is just like a short outlook how at PTB we would like to use PulseQ also in the future. So this is a direct import or direct import for the sequence, and not using the actual files, but probably just the sequence object from Python, and use this to control the spectrum cards and this the scanner. And yeah, with this, I'm at the end of my presentation. Here are some useful links. So the first one is for the general PyPulseq homepage. Basically, everything else is linked there. But if you want to have direct access to the MATLAB or Python GitHub repository, go to the second or third link. And I can also recommend the PyPulseq tutorials. These are in MATLAB, but they're pretty good. One thing that I forgot, in both repositories, MATLAB and Python, there are a lot of example sequences. The scripts, you can just check the scripts, run them, and then use them at your scanner. And now I'm really at the end.
So I've a lot of questions. I'll try and sort of contain myself a little bit. What you showed, or what's generated in terms of pulse sequences, is all kind of the ideal pulse sequence. So how do you ensure that the translation of what's come out of the PulseSeq or what's generated in PulseSeq, when you translate that into something that the system plays out, you obviously have the pre-emphasis that you have to add on the gradients. You have the B0 corrections, like first order shims or higher order shims if your system have that. How do you deal with all of that? Do you just sort of in the PulseSeq interpreter on the system itself, it sort of it lets the interpreter handles all that, or like how does that work?
So I'm mainly using PyPulseq and the Siemens scanner, so I think it's different from what will be the case for the Spectrum. But they are, like everything like shimming, frequency adjustment is done at the console and independent of PyPulseq. And for the Spectrum card, I guess David has to comment how he wants to do it.
Maybe I can comment quickly on that. So far we plan to really use all the attribute that PyPulseq provides. So there is, you can add some gradient offsets for the shimming. You can also adjust the frequency a little bit by frequency offset parameter. So at the moment we try to cover all these adjustments within the sequence file, so that you really have in the end the signals that you replay by the cards. That's the goal.
So I have,
but can you do like arbitrary pulses?
I think there I have to ask Patrick. So far I experimented with, I tried like sync and rectangular pulses.
It's the same question, right?
No, you can play out or create every kind of SIG or RF pulse that you want. So the ZigPy library is also used because they have some other fancy RF pulses implemented, like all the adiabatic pulses. I also have several that I implemented on my own with both amplitude and phase modulation, for example. So this is possible. And
the good thing having everything in the sequence is that in the end you know what you replayed. So there's no correction on the system, which is some kind of black box and which might differ between different scanners, but you always know what was like the offset, what is, I don't know, frequency offset, and there are so many stuff that you can modify. So
I'm a little concerned with that implementation that you've just done, that you've just described, because I think the whole idea behind PulseSeq is that it's something that you can have the same sequence that can run on different, not only different versions of the same scanner, but different scanners altogether. So once you start adding the sequence, the hardware corrections, like the preemphasis, or if your RF is nonlinear, or your RF amps are nonlinear or something like that, if you start adding that to the PulseSeq file itself, then it's something that can't be translated to different systems. And sort of the secondary issue is what that implies is that every time I change the shimming or I redo the shimming of our system, I will have to generate a new seq file to run that sequence. So this is my personal feeling at the moment, is that it would actually be much more beneficial to have those things on the system clearly documented, and then the sequence file is pure.
Absolutely right. Yeah, yes, exactly. So that's also how we implemented it in the past, right? We separated the device configuration file from the language file, from the sequence language.
I also think that everything which is hardware specific must be done by the interpreter, or and yeah, that's I think that's clear. Nevertheless, I have also some doubts about maybe pulse objects or so, to guarantee that they are really the same at scanner 1 and scanner 2 or A, B, C or whatever, since sync pulse is not a sync pulse. Yes, you can do some classification of these pulse objects, but there is some arbitrariness but in particular RF pulse shapes are critical for you have all these I only want to put some place a little bit of devil's advocate in this. That's at the end I would be lucky if it's really the same sequence, yes. But nevertheless, it would help a lot to have this tool here.
Maybe just a quick comment. So, I mean, thanks a lot for the comments on that. So we are right at the beginning. We need to test what's the best way, but the way we went so far does absolutely not prevent it. So we just did not care for, or we just did not do all these corrections on the interpreter side, but would not be a problem to edit. So yeah, I mean, I totally agree to your comments. Makes sense. So maybe we will go that extra mile and add it to the interpreter.
And then I have another question, which is the directionality of the communication between, kind of how interactive the communication can be between PulseSeq and the local spectrometer environment. If you were to write a B1 calibration sequence in PulseSeq or a Shimming algorithm in PulseSeq, those variables would be shared between scans. Is that something that you would then be able to locally store on the spectrometer? Does PulseSeq allow for that? Say, hey, this is a shared variable now based on. Do you know what I mean? If I run the Shimming algorithm, basically, hey, these are my shim values. I want to use them across all these different sequences. I will store that value on the spectrometer and sort of have that offset. It's sort of a continuation of the question that I had before.
I mean, also completely different, I guess, for the different kind of scanners. I think for the spectrum setup, it should be possible. Probably, well, with like a feedback over this, how you call it, this sequence, the
sequence provider.
A sequence provider, yeah, exactly. Right. So
Yeah.
I guess with the feedback to the system, it would work. I mean, also with different tools for the for the big vendors, it should be possible, but not directly. If you create the data or if you acquire the data at the scanner, I think you cannot directly access it. You have to find a workaround for this. Yeah.
So how does that work for the Siemens system? Just to use an example, because you said you had experience with, or somebody said they had experience with the Siemens system. If you're using, let's say, the higher order shims, how is that integrated into the PulseSeq environment?
Can I maybe just interrupt you a little bit? I don't know. I think maybe we are confusing on two different things here. So I mean, PulseSeq in the first instance, right, was developed in order to be able to get the sequence which you write on your computer onto the scanner. And from there, on a Siemens scanner, it's translated into Siemens pulse sequence object, so into a gradient, Siemens gradient object, Siemens RF object, and so on. And then Siemens does all the corrections on that, right? That's where PulseSeq stops. So anything like with what the shimming effects are or any other optimization of the hardware parameters, that's all done on Siemens gradient objects. Yeah. In our case, I guess we have a special case in the sense that we can continue using the PyPulseq objects. But it doesn't mean that still you will have a PyPulseq sequence, which is basically put on the system, but rather than translating it into our own OSI gradient shapes or something, we're just reusing the PyPulseq shapes, and then we can apply all the corrections we want to do. But it would still, the thing which is put onto the scanner is still a normal PyPulseq sequence, which can be also put on another scanner. So I think we're just using PyPulseq in two spots here.
So you do your preamps and things like that are changes that you would make to, you get the raw PyPulseq file with your ideal gradient shapes. Then you have a sort of translation layer which creates sort of a second PyPulseq file which has all these preemphasis things added onto it.
Yeah.
So, okay.
I mean, then it's not anymore a PyPulseq file, but exactly. Yeah, so this happens on system.
Reusing that.
Yeah. Yeah.
Exactly.
Yeah. But it's technically like something else because then the PyPulseq part is still the comparable part, no? And this would be on system.
We would. Yeah,
could
probably.
be, but does not need to be. Yeah.
But we would use it because it's a well-documented standard if you want, but you could use also something else. Yeah. But then we can at least reuse what PyPulseq has already done.
I have a question regarding the speed. How important is it? Okay, of course, probably, but the question is, how fast is the MATLAB version against the Python version? So,
I mean, all the speed up that I mentioned is just for creating these sequence files in the first place, which you usually do once, right? And to be honest, for all my sequences, this is not critical at all. So creating a gradient echo sequence like this is less than a second. It can take, if it's like really long 3D with for time dimension and complicated readouts, might be a minute, but still it's like something that you do once and then it's created and you put it on the scanner. And so I think this is not a big issue. Still, it is nice that we have like new contributors that try to optimize things and yeah.
So I got a question for those who use PyPulseq on the Pitaya. What is the stepping? So I know from I use the original Oka brand, there's this 10 microseconds stepping. And then if you have the stepping, is the stepping or is it carried out on every step? We discussed this in the morning on the readout window. It's just the plateau of a gradient, so there's no change. The OSI² board has a DUC that is assembled in hold DUC, so it holds the last value. So you can set the whole SPI communication to 0 for the complete readout window, because a lot of these spikes that we see in these self-made images here on these systems come from SPI bus coupling over the gradient amplifier into the system. So is it carried out on every step, or are there some kind of implementations to have real pauses in the stepping?
Yeah, I think that's definitely a detail which Vlad could answer. I think that's not specific to PyPulseq, right?
Yeah, I think it's PyPulseq, Marcus, and this Flocra thing comes all together.
But I mean, PyPulseq in general doesn't, I mean, I think you can provide a raster time, but it does not raster your gradients in the final raster, I would say, which is replayed from the scanner. So for instance, if you have a trapezoidal gradient, you just store like 4 values, like the rise time, fall time, flat time, duration. Yeah, correct me if I'm wrong, but it's like basically just a description, and the rastering is then done by the console application.
By the interpreter then.
Yeah, like I mean, for the Marcus case, this would be the Flocra interpreter. It would probably be the translation between this very high-level gradient description and the Marcus format. In our case, with a spectrum card, we really, I mean, we have a defined raster of, let's say, 20 mega samples per second, and then we calculate every single point that we want to replay.
Okay, it's not done in the PyPulseq.
No, it's not done in the PyPulseq file.
I mean, in PyPulseq you can define different raster times, but this is not what is played out at the scanner. Like, yeah, but it can still be used to reduce, I don't know, file sizes, because you don't need a RF pulse to be sampled with 50,000 samples. 200 is enough. Right?
The one signal I really missed in your signal where you displayed all your signals, like the gradient pulses, the ADC window and stuff. For me as a RF developer, the TX gate, so the blanking signal, is the most critical signal in the scanner. Because if you have no TX mode and you send an RF pulse, you destroy basically the coil and the TR switch and stuff. Or the RF amplifier has blanking, then it's not that critical. But does the TX gate signal also get created in the PulseQ file?
No, it's not in the file. It must be handled by the interpreter, right?
Yeah, maybe I can also comment on that quickly, because I just implemented it. I mean, you have basically some delays provided by an RF pulse that basically give you the hint where your transmit window needs to be. And then it's just a digital signal that you program. And yeah, but in general, it's not generated by PyPulseq, but it's intrinsically included in the RF description.
That has to be hardware config file.
Yeah, because you have like these pre-TX gate and post-TX gate switching times.
It depends on your hardware configuration, so it needs to be a hardware.
But this is, I mean, this can be configured by the system, the PyPulseq system. So there you can provide some values, some minimum values, which have to be set, and thereby you then define the window.
I'm fine.
Okay, so yeah, thanks a lot, Patrick. And we're actually done with our agenda. We have one more point, which is more discussion. And then the closing. I would suggest I do the closing now for the ones that want to leave, because the remaining discussions will be probably more specific to the system. I think it would be nice if we can discuss some things that we just started also, but then to basically fill some technical specs. I think we are all a little bit out of energy, so that just in half an hour or so would be nice. And then, so I thank you very much for attending. I think it was really, really nice. I think we should repeat this definitely. And do this more regularly. Again, if you want to stay, feel free to stay. I'm sure we will later go for a beer or so. Yeah, Martin says yes. So you're also invited to join, or for some food. That's also good. Yeah, and thanks a lot for coming, and looking forward to continue this nice work that we just started on the system. Thanks. And thanks again, Martin, for organizing this. I think we can grab a coffee and then we can have some discussions, maybe like some